Hi everyone and welcome back to my channel. So today we'll start a new topic, that is computer organization and architecture. This is especially for students who are preparing for GATE from EC branch or from CS branch, or who are preparing for placements in digital VLSI domain. So because computer organization and architecture is being asked there, so this is also important for those guys. So what syllabus I will cover? I will totally focus on GATE syllabus, okay, GATE EC syllabus. But obviously I will also focus for the students who are preparing for digital VLSI role. Okay, so I will focus on those students as well, which questions are being asked in placements. So I will focus on that mainly, like gate level questions are asked. So in this video, this will be a part 1. In this video, what things I will cover briefly, let's discuss the syllabus of EC and CS. What is the difference between those two? So in EC, in computer organization architecture, we have machine instruction, addressing modes, ALU, data path, control unit, instruction pipelining. Okay, and in computer organization architecture in CS branch, they have already this is already inclusive, and extra thing what they have pipeline hazards, memory hierarchy, cache memory, main memory, secondary storage, IO interface, interrupt, and DMA. So this is the extra portion. Okay, this portion, right, this memory hierarchy to here DMA mode, all these things are extra. So obviously this is required for placements, but for GATE aspirants who are preparing from EC domain, they don't need this. So this will come later on, and this will come in a condition. I will talk about the condition. Okay, so like this video will cover what? This video will cover everything: machine instruction, addressing modes, ALU, data path, control unit, and instruction pipelining will be covered in a separate video. Okay, that I will discuss about later on. So this will be covered separately. Okay, later on. Not in this video, separately. Now main thing is, like, this video will cover all these things. Okay, so many things I'm doing for you guys. So I have just a few requests for you guys, because if I do this much of amount of hard work and you guys don't give this enough value, then that will be very demotivating for me. So I just want to ask few requests. First one is, obviously, like this video. If you have enjoyed this content, you start at least study the lecture 1, then you will realize what is the difference. Okay, how am I teaching? At least study the lecture 1, and if you are liking the video, then please do hit the like button. Then comment that I am waiting for part 2. I am waiting for part 2. That is your comment, because part 1 will cover this, part 2 will cover the instruction pipeline. So if you want the instruction pipeline on YouTube, then you have to comment I am waiting for part 2. And if you want all the notes will be there on my LinkedIn. You can go and link to the LinkedIn post will be there. You can go on the LinkedIn and like that post and repost it. Okay, so these are few things. I'm not even telling you to share in spam in WhatsApp groups. I'm not telling you, but just give a like and comment. Okay, and obviously if you're new to the channel, please do hit the subscribe button. Okay, that keeps me motivated to bring more videos on YouTube. Else what's the point of bringing this many videos on YouTube if you are not valuing the content enough? Okay, so these are my few demands, and I think you can do this. Okay, I think you can complete these demands. So this is the part 1, and if you want the part 2, I mentioned these things you need to do. So let's start with the books. What books should you buy? So if you're studying from me, then you can avoid buying books. Okay, but if you want to have more in-depth knowledge, if you want to get more, if I have taught some topic and if you want to learn that more in depth, right, then you can purchase books. But what I will cover, right, I will study strictly according to EC syllabus. Okay, so it may so happen I'm not going too much in depth of a particular topic, and that is not required actually. For CS guys, yes, it is required. For EC guys, it is actually not required. So I will not go too much in depth there. So if you still want to learn that concept too much in depth, you can purchase the books. So if your basics are weak, right, you can purchase this book, Computer System Architecture, from Maurice Mano. Okay, this is for the basics one. If your basics are weak. If you want advanced topic like pipelining and all those things, this book has the advanced topics. Okay, like pipelining. Okay, pipelining, addressing mode, pipeline. Yeah, this was correct only. Yeah, like this book is from Computer Organization, Carl Hamesher, and other two names. I cannot pronounce those two names correctly, so I will not pronounce that. Okay, and this third book is mainly for question practice. Okay, third book is mainly for question practice. If you are studying from me, no need to purchase any book. Okay, so this is for questions. from David A. Patterson and John L. Hennessy. Okay, so these are few books. If you want to purchase, you can. But if you're studying from me, you can go through this video. That should be more than enough for EC and for digital VLSI roles. Okay, so yeah, let's start with today's lecture. First lecture. So lecture 1 will be basically introduction to computer organization architecture. What does computer organization architecture actually mean in real life? And we'll understand few components of digital computers. What are few components of digital computers and different CPU architectures. So we learn what are different types of CPU architectures basically. So like I mentioned already, like in COA, right? The syllabus is mainly divided into two parts. One is architecture, one is organization. Okay. So what does architecture and organization means? So I can give you an example. I will obviously go to more precise examples later slides on the later slides. But let's start with basic things. Once you you have a house, right? You want to build a house. So first you architect the house. How you architect it? First you decide how many rooms there will be, how many bathrooms there will be, what is the height of the house, like will it be 3 floors, will there be 3 floors, 4 floors, how it will be, will there be any rooftop, like all those things. So that comes under architecture. You're mapping the particular home. Okay, next is the organization part. Now where will your kitchen lie? Okay, how will the pipes go from water, how will the pipes go, like water flow, how will the bathroom pipes go, where will the lighting be, all those things, right? All those things are organization, because that is after the home has been made. So you're organizing stuff now. Architecture is architecting the house. Okay, then organization means you're organizing things. Where will this TV lie? You can again next time on, you can move this TV on bedroom. Do you want your TV to be in the bedroom or the living room? Okay, so that's up to you. So you can again change it. Okay, so organization, obviously you can change it, but architecture you cannot change. Architecture is like it follows a common architecture. Okay, so I will come to more examples, don't worry. So if they are divided into two parts, what comes under what, which topic comes under architecture and which topic comes under organization? So under architecture we have CPU design, ALU, instruction set architecture, addressing modes, memory hierarchy and data format, then pipelining. Okay, and in organization portion we have input IO devices, data path design and performance. Okay, so these are the few things that are bifurcated between organization and architecture. So architecture is designing it, then organization is mainly implementing. So this is something we design, architecture is design, and this is the implementation basically. Okay, so that is the basic difference between architecture and organization. Okay, so your EC syllabus mainly follows the architecture. It doesn't have organization portion. Okay, mainly it has the architecture portion, your EC syllabus. Now let's understand with few key analogies, as I explained just a few minutes ago, that think of architecture as the blueprint for a house. What rooms, windows, utilities it has, while organization refers to the actual construction and materials used, bricks, wiring and plumbing. Okay, example, while architecture specifies that there is a, like if I want to talk in computer terms, right, while architecture specifies that there is a register to store a value, the organization decides whether the register is implemented with flip-flops, memory or another method. So you know, right, registers actually store data values, ones or zero. Basically we store bits, right? Our computer, everything is in binary, 1 0. We either store 1 or 0. So how will I store that? How will the data go to that register? That is decided by organization. But architecture decides how many registers I will have. All those things architecture will decide. Okay, so this is another analogy. There is another analogy. Okay, now car design and manufacturing analogy. Architecture, that is like design and concept of the car. It defines what the car should be, its functionality, features, purpose. So like what type of engine it is, whether it will be electric, hybrid or it will be only internal combustion, basically which the cars which are which consume diesel or petrol. The maximum speed, fuel efficiency, passenger capacity and safety features. So these are a few architecture things that we, before even like manufacturing the car, right, before starting the manufacture, we decide all these things beforehand. Okay, now like example is like a Tesla Model S is designed to be an electric car with autopilot feature, a long battery range and a sleek design. So these are all the parts of cars architecture. Now what is organization? This is like actual manufacturing and assembly of the car. It involves how the car is built, the materials used. Will the body be aluminum or lithium? Like how will the battery be? Will it be lithium ion or will it be some lithium polymer battery or some other type of battery? So there will be battery, that is for sure. That is architecture's task, that yes, there will be a battery. The capacity of the battery will be 10,000 mAh or whatever the capacity is. But how will it be? Lithium ion or will it be lithium polymer? What will it be? What will it be? Okay, that the organization will decide how you organize stuff. The placement and wiring of the components, engine, battery, sensors, how the systems, brake, steering, autopilot are physically connected and are operate together. Okay, how the electric motor is connected to the battery, how the sensors and cameras are placed for autopilot, how the brakes are engineered, all this comes under cars organization. So these are few analogies. Okay, so now we will do a question, and with the help of that we can understand this concept of organization and architecture further. So this question is only for those students who are from electrical or electronics background. If you're from CS background, you can avoid this question. You can skip this question. Okay, you can skip this portion of the video and you can just continue from the next portion. Now we have to design an electrical system with a transfer function that has a constant gain of 0.5 for all frequencies. So if you have studied electronics and if you have studied analog electronics, then I know you are very good, because you have studied from us, and you know analog electronics is best from Prefusion. So we have to design a system that has a transfer function and it is constant with 0.5 gain for all frequencies. So what components can I think of? There can be two ways I can design. I can design with the help of op-amp, or I can simply design with the help of a voltage divider. There can be two ways, right? So that is what is written over here. This is electrical block, and I'm giving it an input voltage, and the output voltage that I should get, the voltage gain that I should get is 0.5. So basically my criteria was VO over VI equals to 0.5 volts. This was my requirement. Okay, they didn't tell me how to design and all those things. That's already up to me. So I can go two ways. Obviously there can be infinite ways. I'm just cherry picking two ways here. I'm picking two ways. One is with the help of resistors, another one is with the help of resistors and op-amps. Okay, obviously there is some advantage and disadvantage of picking any one, right? There is some advantage or disadvantage. So that is that we'll discuss on some other day, but there is some advantage and disadvantage. So here it is a voltage divider, right? So what will be the VO in terms of VI? So from this particular, if I use this particular circuit, it will be VO over VI. It's simply like a voltage divider. It will be R2 divided by R1 plus R2. This is my VO over VI. And here, what is my VO over VI? So this is a bit tricky actually. So I can like name a voltage here, that is VO dash. Okay, this is a voltage VO dash. So my 0 minus VO dash divided by, like I'm applying the virtual ground concept here. It is a negative feedback op-amp, so I can apply the virtual ground concept plus here. This is actually not 0, this is VI, right? So this node will also be VI. Okay, sorry, this node will also be VI plus VI over R1 equals to 0. So I can write here that my VO dash by R2 equals to VI over 1 by R2 plus 1 by R1. Now this right, I can further write this down, that my VO dash, I will take another page actually, that would be better. My VO dash equals to VI 1 plus R2 over R1. This is a standard result that I know you guys remember, but still I wanted to derive in front of you just from the scratch. So, but actually I'm not interested in VO dash. I'm interested here, right? VO. So what is VO actually? VO is actually VO dash into R4 divided by R4 plus R3. So it will be actually VO by VI will become R4 divided by R3 plus R4 into 1 plus R2 plus R1. Okay, this will be my result. Obviously, I can manipulate my register values to get the value 0.5 because what I require is 0.5. I can design anything. So that is where organization comes in. If I choose architecture 1, I can have this register as 1 ohm, 1 ohm, and like this values. Still, I will get V over Vi. Like you can solve it. You will get V over Vi as half. Or I could have had some other registers as well. Still I would have gotten the same result, but this architecture remains same, that yes, we are using simple voltage divider concept, 2 registers only. The architecture remains same, but the exact register values are changing. So this is the organization portion. How am I using the register values? Okay, but here in architecture 2, again, if you just cross check the values, you will get that your V over Vi, if you put all the values, you will get again this is not ohm, sorry, 0.5. Okay, so here also again I can change the register values, and again I will get back 0.5 ohms, doesn't matter. So organization will change, but architecture won't change. I'm using a op amp and few registers. What is the difficulty? If I use this architecture, right? If I use this architecture, what is the problem? The problem is I cannot get a gain greater than 1. So at a later stage, you have to design for the future as well, right? If the designer tells you, okay, now I require this particular block to work as a not just as an attenuator, as a voltage amplifier, as an amplifier as well. If it has to work as an amplifier, I can never get a gain greater than 1. Not possible. In this simple resistor divider circuit, is not possible because it is causing a loading effect. Not possible. It is causing a loading effect. But is this causing any loading effect? No. This op amp has infinite input impedance. So this, if I place a Vi here, it will not cause any loading effect. So this is not causing any loading effect. And if I want a gain greater than 1, yes, I can get, because I have this particular term, right? This term will always be less than 1, but this term can be greater than 1. This term is always greater than 1. But here in this term V over Vi, this will be always something less than 1. It can never be greater than 1. So if you want to future proof your design, you will choose architectures 2. Okay, but it depends, right, on the use case. This time I told you I may need a gain 1. Sometimes may need a gain greater than 1. Sometimes it may happen that architecture 1 is suitable, but this time architecture 2 is suitable if I want to have a gain greater than 1 in the future. So, but can you change the architecture? Changing architecture is very, very difficult. Okay, you have to change the chipset and all. I can change the organization, right? I can change how these registers value are, how these are placed. I can change that, but I cannot change the architecture. Changing the architecture will be, again, I have to think again, design the system again. Okay, so that is the difference between organization and architecture in electrical analysis. In the electrical analysis, I talked about that because CS guys, they already know, they are from CS background. For if you want to understand it from the perspective of electrical and electronics background. Okay, so these are the formal definitions of computer architecture. Computer architecture focuses on the functional behavior of the computer system, involves design and implementation of various components of the computer. Just hold on, we'll check one thing. Yeah, this one. Then computer organization focus on the structural relationships between components, how they are related to each other, deals with the operational attributes that work together to fulfill the architectural applications. I can change around the attributes of the particular register, right? Register values, I can change all these things. I can change. So that is the work of the computer organization. So here in computer architecture, what we do is we mainly design stuff. We don't implement it, actually. We design. So first of all, I will design CPU. Okay, I will design the CPU block. Then I will design the memory block. Memory means RAM, ROM, all those things. Then I can design the IO devices. How the IO devices will be there, I can design those things. So I am just designing all those things, but I am not talking about the interaction, how they will interact with each other. Okay, the interaction portion will be taken care of by the organization portion. So this is CPU. Okay, how will CPU interact with memory? How will CPU interact with IO devices? How will IO devices interact with memory? So all these back and forth communication, right, and all the other things are taken care by the organization portion, and computer architecture defines the design basically, not the implementation. This focuses on the implementation. Okay, implementation, and this focuses on the design. Okay, so that's basically it, okay, about computer organization and architecture. So with the help of this much knowledge, can you solve this question? Okay, pause the video and try to solve this question. So let's read the question. Which of the following elements are part of computer architecture? Addressing modes, CPU design, architecture, right? Yes, CPU design is actually part of computer architecture, and addressing modes is also, because computer architecture we design the how the addressing will work. What do you mean by addressing modes? Don't worry if you don't know all this, we will learn in this particular series only, in this particular lecture only. If you know, that's a good thing. Addressing mode means, what does the address means? Is it an effective address? Is it an address of the memory, or is it a address of the operand? What is operand? What is memory? Don't worry, I will teach all this later on. If I teach everything now, everything will just be a mix and match, right? We cannot study systematically. So I am teaching you everything systematically. Okay, so yes, CPU design and addressing mode is actually part of computer architecture. It is correct. Next one, instruction set and data format. Now, is instruction set and data format part of computer architecture? Yes. How? Like, I would design the instruction first hand. Like, what instruction the CPU will support, right? What type of instructions? Okay, it will support. I will already design it before computer architecture. How they are implemented in the system, that is defined by the organization. So yes, instruction set and data format, all this will be defined by the computer architecture. Yes, this is also correct. Secondary memory and operating system. Operating system is an outside thing, right? Like in your PC, you can install Windows XP, you can install Windows 7, you can install Windows 11, you can install Windows 10. Okay, there are so many things you can install. OS is independent, right? And secondary memory is also independent. How you have your what do you say, this pen drive, right? You have this pen drive. So this pen drive, is it dependent on the architecture of the CPU? No, right? It is not dependent on the architecture of CPU. Yes, it has to support few things, but it is not exactly dependent on the computer architecture, right? It's a separate thing. So no, it is like secondary memory and operating system are not part of computer architecture. So option 1 will be correct, 1 and 2. Okay, and don't worry if you could not understand this. We will obviously, this subject is there to understand computer organization and architecture. Okay, so all this will be cleared at the end of this particular series, and that day you will say that I have understood everything about computer organization and architecture. Okay, so let's first understand few components of digital computer. Okay, these are few basic things you know, but you have to be smart. You are engineer now, you just cannot basically say what is CPU. CPU is central processing unit. You cannot say that. Okay, if the interviewer asks what is CPU and you say CPU central processing unit, you will be kicked out of the interview. You need to say technical terms. What does CPU exactly do? What is inside CPU? What operations it performs? What is the responsibilities of the CPU? It is not central processing unit. Yes, it is, but that is the full form. Okay, so CPU has two things inside it. One is the control unit, another one is the arithmetic logic unit. What does the control unit do? It directs the flow of the data between CPU, memory and IO devices. Basically, control unit, what it does is it sends signal to everything. Look, if let's say let me give an analogy. So your house has a senior member, right? He controls everything. That person controls everything. If he says we'll go out at 10 a.m., you follow his rule. So he actually tells you what to do. Okay, he tells you what to do. So control unit is that particular unit. That person tells you what to do exactly at that particular second. What to do? It will direct ALU to perform addition or subtraction. Okay, it will send some signals. It sends some signals that the ALU understands. Okay, if I have got this, let me code it. Let me say 101 and 110. If the control unit sends 101, I'm not talking why it will send, when it will send, all this will be discussed, but let's for hypothetically understand that if the control unit sends 101 signal, ALU understands, okay, I need to perform addition. If the control unit sends a signal 110, ALU understand I need to perform it's a movement of data. Okay, so these are few control signals that the control unit will send. Okay, so this is the task of control unit. What is the responsibility of arithmetic logic unit? As the name suggests, it performs arithmetic and logical operations like addition, subtraction, all those things, right? Arithmetic operations. Executes logical operations like comparison and or. Okay, so ALU generally ALU can take two inputs at a time. Okay, so new architectures can be some other thing, but generally ALU takes 2 inputs at a time. And this is the block diagram. Basically, I have a CPU, and inside CPU there is CU and ALU. Okay, and these two are the core units of a computer, digital computer. Okay, these two are the main units of a digital computer, which totally runs the whole system. Okay, so I hope you understood the control unit and ALU. Don't worry, there is a particular chapter on control unit. We'll learn about that. Okay, there, if you couldn't understand now, but just try to understand this basic thing, that control unit directs what to do, which thing to do what. Let's say it will direct this particular earbud whether it should be turning on or turning off. Okay, just like I press the button, right? There is a button here. If I press the button, it will turn on. If I press the button again, it will turn off. So that pressing of the button is the control unit. That is what the control unit does. It directs the other things whether to turn on or off, whether to send data or receive data. So that is the task of control unit. Okay, and ALU is just, it performs arithmetic and logic units. You give it 2 inputs, it will perform some arithmetical logical operations depending on the type of the control signal sent by the control unit. Okay, so this can mean add, this can mean subtract. Now another component is memory. So if you have ever build a PC, or if you know a bit about computers, you know there is a RAM, ROM and secondary memory in a computer system, right? What is RAM? RAM is basically a primary memory component. Primary memory, also known as main memory, and in our case this will be only the memory. Okay, we will not talk about secondary memory. Whenever I speak memory, this is I'm talking about primary memory. Okay, whenever I'm speaking the memory, I'm talking about primary memory. This is the memory that I'm talking about. Okay, so there are 2 components in primary memory. One is RAM, another one is ROM. RAM is random access memory. It is temporary volatile storage used during active processes. So basically what happens, whenever a process is running, right, it has to store some data. It needs some data, right, to perform some operations. So where it will store? It will store in the RAM. That's why whenever you see your computer, sometimes your computer gets lagged, because sometimes you have too many applications open, right? Too many applications are opened in your computer, and what will happen, your computer will become slow, because every program is accessing the RAM, and RAM has limited space, so it will not be able to give all the programs space, right? First it will give some program A, let's say Chrome, then it will give some program B, let's say Microsoft Word, then Microsoft PowerPoint. So that's why then your program becomes slow, because your RAM is not enough. Then you hear this, that maybe your RAM is very low, you have to increase the amount of RAM. Let's say 8 GB RAM you have to increase 16 GB RAM, so all the programs can store their temporary memory. So that is the task of RAM. When a program runs, they store their memory, they store their data in the RAM. What is ROM then? ROM is read-only memory. It is non-volatile. You cannot delete it. Once it written, it will be stayed there. Okay, it will be written there. Non-volatile storage containing essential instruction like bootloader. So your CPU, right, it needs to have few things that is inbuilt to it. Okay, it should be independent of the external things like OS and all those things. So those things and few hard-coded instructions of the CPU and all those things will be present in ROM. Hard-coded things which are CPU dependent, those will be present in the ROM. You cannot mess with that, you cannot edit that, you cannot change that. Okay, you can only talk about RAM, but you cannot change anything in the ROM. ROM is fixed. Once you design a CPU, it is fixed. ROM, but for the particular CPU, firmware for the particular CPU is fixed. Okay, so basically RAM stores the current instructions. It stores the current instructions. Okay, and what about ROM? ROM actually stores the CPU instructions, inbuilt instructions that the CPU already has. Okay, inbuilt instructions while designing CPU. Okay, and what is secondary memory? It is there for long-term storage like hard drives, SSD, DVDs. Like these are, we already know this, like secondary storage is this, right? Pen drive. This for use for secondary storage. It is not inside the computer. and this is not even inside the ROM of the computer. Okay, so this is used for long-term storage. So whenever I'm talking about memory, I'm always talking about primary memory, RAM. I'm always talking about RAM. Okay, unless until specified. So in computer, right, data has to be stored somehow, right? Just like your like houses, like you have a colony. Inside colony there are many apartments, and inside each apartment you have a house, your own flat, and that is your address basically. So data also needs to be stored in a structured manner. So that is what organization does. So here memory also needs to be stored in a structured manner. Generally we store memory in two formats. One is byte addressable, another one is word addressable, which I will teach you later on. But if you just take a brief overview of the memory can be stored like this. If it is byte addressable, it can be stored like this, right? First byte will be stored here, and one more thing I didn't mention this, that our computer can only understand, it is very dumb. Our computer is actually very dumb. It can only understand 1 or 0. Okay, so our computer or CPU can only understand 1 or 0. Okay, and what do we call this 1 0? We call this a bit, right? Single bit. And this bit, when I store, I cannot just store a single bit, right? That will be just so much waste of space. What we do is we store chunks of bits. So we had made a nomenclature that 8 collection of bits, right? 8 collection of separate bits will be called a byte. Okay, so 8 bits. Don't worry, I will teach this later on as well, but for now just understand this. 8 bits will be called a single byte, 1 byte. Whenever you see 8 bits, 8 bits meaning I have 8 fields, right? 1 2 3 4, just hold on, 1 2 3 4 5 6 7 and 8. So this can be the 0 1, this can be 0 1, this can be 0 1, this can be this is 1 2 3 4 5 6 7 8. Okay, so these 8 bits, right, will be as a whole, we can take it as a byte. Then there is a term known as word that we will learn later on. Don't worry about that. So for now, just understand this in your head that 8 bits means 1 byte. Okay, I know this basic thing you know, but many students don't know, so I have to clear everything. So just like your houses, you have some location, correct? Your house has some location, like near near some supermarket, some famous statue or something. Okay, anything. Your house will have some location. Just like that, this memory will also have its own location. Else, how will I identify what is which memory is this and this memory? How will I identify difference between byte 0 and byte 11? The location of this will be 0 0 0 and location of this will be 0 0 5. Okay, so I have to locate these things. So to locate also, these are known as address. Each memory will have a address associated with it. Okay, it's just like integer, right? It is very simple. It's not like your numerical alphanumeric address, location address, like real life. It's just a numeric address. Okay, this will be 0 0 0. This will be then 0 0 1. This happens after we pass 2 bytes, right? This is the here. This is memory address. So there are many type of byte addresses. We can address it byte according to byte, or we can address it according to what. I am not going into that right now. I'm not going into that. For now, understand this byte address. Okay, so this is first byte. If first byte has been caused, then I will be here, right? So what is the location of this? The location of this is 0. This one, 0x1. Okay, this was the first location, that is 0 only, and the location of this byte 1, is 0x1. What is the location of byte 2? I'm not talking about this left hand side. We'll ignore this for now. Location of this byte 2 will be 0x2. Location of this byte 3 will be 0x3. Why? Because I'm increasing every byte. And this is byte addressable. That's why this is also increasing every byte. So this is byte 0, then byte 1 will be location 0x1, byte 2 will be location 0x2, and so on. If it is byte addressable, then the location will increase each byte. As I pass each byte, the location counter also will increase by 1. I hope you understand this analogy. Okay, so that is one thing. And we'll learn about this memory address as well later on. Don't worry about that. Okay, each of these particular things, right, is also called a cell. Okay, in a memory, each of these things is called a cell. Each of these like bytes are also called as cell. And if let's say some organization, some type of organization decides to store 2 bytes at once, because that is the organization of that particular PC, right? Why? This is a like this is a 32 gigabyte USB. I can have 64 gigabyte USB as well, right? So it's my wish how I choose to store things. Okay, so it's the users which, like users, not users, organizations, like how the people decided, the organization, that do they want to store the data in 2 bytes or single byte. What is the advantage of storing the data in 2 bytes? Obviously I can store more data, okay, because I have more bits, I can store more information. If I am storing only a single byte, that is a disadvantage, that I cannot store more data. But what is the advantage? Advantage is I can access the data faster, because every time when I try to access it, I just need to access 8 bits, not 16 bits. So the number of lines, all those things will increase. What do you mean by lines? All this I will explain, don't worry, just I'm giving you a bit of analogy. Okay, so let's now solve a like question that came on GATE 2006 according to this concept. And it's okay if you could not understand this question, you can solve it later when we will discuss about byte addressable memory. Okay, that time also you can come back to this question, revisit this question again. So let's read this question. A CPU uses 24-bit instructions. So just by reading the statement, I understand that at a time CPU like has 24 bits. In a particular instruction, it has 24 bits. So how many bytes it has? If 24 bits is there, right, it will be how many bytes? It will be 3 bytes, right? Each byte is 8 bit. Okay, so 8 into 3 will be 3 bytes basically. 8 into 3 will be 24, and that will be 3 bytes. And a program begins execution from address 300 decimal. It begins at execution from 300 decimal, right? Which of the following values can be valid program counter value? Okay, so if you don't know a program counter, that is totally fine. I will tell you what is program counter. Program counter stores the address of the next instruction to be fetched. Okay, program counter stores the value of the next instruction to be fetched. Don't worry if you couldn't understand, you can revisit this question again after studying the byte and word addressable memory. So starting address of the PC will be 300. Why? Because this was initially this instruction was supposed to be fetched, so that's why the PC has starting address of 300. But it is telling which of the following can be a valid program counter. The CPU supports 24-bit instruction, so each instruction is 24 bits long or 3 bytes long. So if the starting address of PC is 300, then again the next instruction can be present where? The next instruction can be present at 300 and 3. Why? Because it is byte addressable. They have told us it is byte addressable. So each instruction is 3 bytes. It is not possible that the next instruction will be 302. Starting address of the next instruction will be 302. Not possible. Why it is not possible? Because each instruction is 3 bytes long. I cannot have a 2-byte instruction, but it is specifying that the previous instruction length was only 300 from 300 to 301. That is only 2 bytes. Which is not possible in this architecture. My CPU strictly follows only 24-bit architecture. Okay, so not possible. Okay, so now what can I say is that as it supports 3-byte architecture, my PC value, right, will always be a multiple of 3. It has to be a multiple of 3, like 303, it can be 303, it can be 306, it can be 309, anything, right? However many instructions I have, it can be anything, but it has to be a multiple of 3. But I can divide it by 3, I can divide by 3. So if I take the what do you say, modulus, that will be 0. Modulus with 3, that should come out to be 0. Okay, so which of this actually is giving me 0? So after 300, right, I have to do what? Modulus of what? The finishing address? No, modulus of number of instructions, because first I will add by 3, then like if I have 1 instruction, if I have 2 instructions, it will be 306, if I have 3 instructions, it will be 309. So 300 plus n times the number of instruction into 3 should be equals to the final address, right, of the program counter. Like after this particular instruction, 1 instruction has been ended, it will be this value, right? It should be equals to the final address PC value, next instruction value. Okay, so I will put all this, right? What I have to do, I have to do by hit. I have to go by hit and trial method. I have to put all these values here. Okay, and n should be strictly a integer. N should be strictly integer. So PC value can be these things. I will put these values here and I will check which one is matching actually and which one is giving n as integer. So for option A, if I choose, so n is coming out to be PC value is they have chosen as 400. So it will be 100, like PC value they have chosen here, option A, PC as 400. So it will be 400 minus 300 divided by 3, right? N into 3. So this will come out to be 33.3. Not possible. N is an integer. N has to be integer because number of instructions will obviously be a full value, right? It will be an integer. It cannot be half instruction. Half instruction is nothing. There is nothing like half instruction in CPU, in computer organization or in computers generally. So it has to be integer. Again, if I choose I'll choose the wrong options first. B. If I choose option B, here it is telling me PC can be 500. Can PC be 500? That I will check. Here from here, what value of n I am getting? 500 minus 300 divided by 3. So it is 200 divided by 3. So it is 66.67. Again, the same thing, right? N has to be an integer. N cannot be a floating point number. N has to be integer. Okay. Then option D. Here my PC value, they are telling me in option D, my PC value is 700. If I choose my PC value to be 700, what is my n equals to? N equals to 700 minus 300 divided by 3. So again from here it is 400 divided by 3, which is 133.33. Again, n is, I'm getting n as floating point, which is not possible. Okay, n has to be integer, right? N has to be integer. So obviously option C is correct. If I check option C, right, PC they are telling me it is 600. Okay, so n will be equals to 600 minus 300 by 3, which is equals to 100. So I will have 100 instructions, 124 bit instructions or 3 byte instructions. After that my PC value can be take 600, right? PC value will be 600 after 3 byte instructions. So it is a valid program counter value. Okay, others were all invalid because they were not actually like integers. The values of number of instructions was not coming out to be integers. Okay, so this is possible, this is correct. Integer, this is correct. So PC value will be 600. This is a valid program counter value. 600 is correct option. Okay, so yeah, this is the basically solution of this question. And it's okay if you could not understand few things, just go with the flow, right? Go understand what I am telling you right now. Okay, all these things will be clear at once later on when we will learn this, what is program counter, what is byte addressable, all these things. Just why I wanted to take this question right now, to give you a feel, yes, you can do the questions. The questions are not that difficult if you are able to understand the concepts. That is the important point. Only if you are able to understand the concepts, that much is enough. Okay, so next is input output devices, input IO device, right? So components of computer, we have IO devices like this USB, TV, monitor, keyboard, whatever, right? Whatever these are, printer, joystick, these are all IO devices. Okay, this we will not talk about much here. Another thing is system buses. This is a very, very, very important thing. I know you don't know about this system buses thing. What is system buses? Basically, each and all components, right, need a medium to communicate. You have the PC, you have the keyboard, you have the monitor, you have your joystick, you have so many things. They need to communicate. How will they communicate? Through system buses. So there is, what does bus mean? Bus means transport, right? It takes you from point A to point B. So that is what the task of system bus is. It collects data information from point A to point B. Okay, sends and receives data from point A to point B. We'll see from the picture as well, we can understand this. It is a collection of communication lines that connect the components of a computer system. It just connects the components of a computer system. It is the communication lines. Types of buses. So types of buses there are mainly 3 types of buses. One is address bus. Address bus is mainly used to carry memory addresses. It is unidirectional. Why it is unidirectional, I will explain that. Okay, so then we have data bus and control bus. So what we can do is, address bus is actually, it carries memory address only. It carries memory address only, and it is unidirectional. Why is it unidirectional? It is unidirectional because from the CPU I always go to access the memory of some address, right? I always go like from like I can give you an analogy, if I can think of some analogy, is that this USB is connected to my PC, right, or this phone or something. This USB can never go and check CPU, hey, how are you? But my PC always checks, goes to some location in this particular USB and takes the value. It cannot be other way around, that this thing is controlling the CPU. This thing cannot control the CPU. That's why it is unidirectional, because this is a storage device. I will, like, yes, I can take the information to this, I can paste information to this, but I can only go to the location, right? Read or write, read-write operation is other thing, but my CPU will always access the memory location. This USB will never access the CPU. That is not possible. That is why my address line is unidirectional, because CPU will always access memory. No other thing will access memory, right? CPU requires the access of memory. Access memory, that is, it needs address. Whether it will be a read or write operation, that is some other discussion, right? That is some other discussion. Read or write means it is just copying from the value. Okay, whatever this USB had, I am copying it to my system. Or write means I'm writing to this like USB, right? That is other discussion. But I'm going to the location. My CPU will always access that location, not the other way around, that that location is accessing CPU. It cannot work like that. So that's why address bus will always be unidirectional. Data bus transfers data between components. It will be bidirectional. Why? Now I have reached that address, right? What can happen? I can take the data from this USB to my own computer, or I can store the data from my computer to this USB, to and back and forth, right? So that's why it is bidirectional, because either I can read, that is copy the data from this USB to my system, or write. Either way I can do, right? That's why data bus is unidirectional. Now control bus carries the control signal. So this is the third type of bus which carries the control signal. Now who will tell to read or write? Someone has to tell, right? Someone has to tell this USB, hey man, you are supposed to only you are supposed to only give read. So I will be only reading from this memory, I will not write. Okay, so someone has to send the signals. The control unit sends the signal through what? Through the control bus. So you have the control bus for this specific purpose. So control is very, very important. It is a very, very important thing. So control bus carries control signals, that is either read or write, okay, or what kind of arithmetic operation I want to do. All these signals, the control bus through, like, it will be sent through the control bus. Now it can be unidirectional or bidirectional. Okay, there can be two things. Control bus can be unidirectional or bidirectional, because sometimes I need some input from other things as well. Okay, to change the control things, to control other things. So it can be bidirectional. It is not like CPU will always control other devices. Sometimes I need control back. Okay, it's like other devices will control the CPU. That can happen. Okay, that we'll understand later on. Now how these things are sent. So mainly we can have single bus. If I have only single bus for address, right, data will go serially. Right? First 0, then 1, 2, like that. But if I have multiple buses for address bus, data can go parallel. So that is the one thing, the advantage, like disadvantage of a single bus. If I use only a single line, right? Single line, data flows serially. If I have multiple lines, then that will be advantage, right? So that is what happens. That's why it is written, it is a collection. collection of communication lines because I will have multiple lines, multiple data lines, multiple address lines. They are all working in parallel to make the communication more fast. Okay, that's why to make communication fast, I use multiple lines. Okay, I don't have space here. We use multiple lines. That's why it is known as a collection of communication lines, right? Not a single line. Okay, so this was about the here. So you can also see like address bus is always unidirectional, right? Address bus is always unidirectional, and like CPU, the address bus will always go in like out from the CPU and it will access the memory, and other buses can be bidirectional. So here let's take an example. Let's take a very simple example. I have an address bus and I have a CPU and I have this many addresses. I want to access this many addresses. So what will be the best possible number of address bus lines? How many address bus lines we need? Okay, how many address bus lines we will need to access the memories, right? If I have a single address bus, I can only access like a single bit, right? Now I have 3 bits. If I have 3 bits, if I have 3 address bus lines, okay, 3 lines, depending on the value of each line, right, whether it will be 0 or 1, like 0 or 1, 0 or 1, 0 or 1, depending on the value of the address, like at that particular line, I will go to that particular address, right? So I can parallelly send data in a single clock cycle. In a single cycle, I will put 101. That means this like CPU will go to address 101, that is here. It will directly go to here. Okay. So generally we do this, that how many number of address lines we require, minimum number of address lines we require. Obviously we can define it with 4 address lines also. It doesn't matter. The MSBs will be 0 only. But minimum how many we require? 101 to perform an operation in a single cycle. I want to perform it parallelly, right? I want to perform it parallelly. So I need 3, right? 3 address lines I need to for this address bus. So 3 lines should be sufficient. So that's how we find out the number of address lines with the help of bits. The number of bits I see, how many individual bits I have, total how many memory I have, how many different memory cells I have. These each individual box are called cells. How many cells I have? If I observe correctly, I have 8 cells. I can write this better manner. How I can write? This can be written as 2 raised to power 3, right? So this 3 is something familiar to me. This 3 is this, right? So obviously, whatever you will see, right, in your computer things, it will always be a power of 2. Why? Because our computer stores in bits. It can be either 0 or 1. There can be 2 outcomes. As there can be 2 outcomes, so everything in your computer system will always be a power of 2 raised to power n. Okay, so here what you can see is that if I want to find out the number of address lines, if you want to find out the number of address lines, you can develop a formula. It's okay, you don't need to remember the formula, but from here I can observe the number of address lines, right? Number of address lines will be equals to what? If I take the log base 2 of this particular thing, I will be able to get to 3, right? That will be my result. If I take the log base 2 of this, so it will be log base 2 of what? Number of memory locations. The number of memory locations we have. How many we have? 8. 8 into log base 2 is this. And we'll choose the upper value. Like, what do we mean by upper value? Let's say number of memory locations I have 7. What is the log 2 of 7? It is, I'll just calculate this quickly. Log 7 log base 2, it is 2.8. Now you tell me how many bits, minimum bits I will require to basically properly function of the address lines. How many minimum bits I will require? I will require 3 bits. Why? I cannot choose 2, right? Why I cannot choose 2? 2 can only define 4 address lines, 4 combinations, right? 0 0 0 1 1 0 and 1 1. 4 is not sufficient. I will have to choose 3. If I choose 3, it can define 8 address lines, but I am only using 7. That is fine. It can define 8 different locations, but I am using only 7. That is fine. Other one will be empty. Doesn't matter. So you will not choose the lower one because that is not the minimum one, right? You have to choose the higher one so that you can at least describe your system. So always we choose the upper bound of this. Upper bound means 2.8 we got. So we'll choose upper bound, that is 3. We will require 3 address lines. Even if we have 7 different memory locations, we will still require 3 bits of address lines, right? So that is about the address lines system bus. Now let's learn about another component known as the cache memory. So what is cache memory? Cache memory is the high-speed memory located inside or close to the CPU, stores frequently used instruction and data for quick access. Okay, so it is just a memory. Okay, but what is the difference between the cache memory is that it lies between the main memory, the RAM, and the CPU. Few things CPU requires multiple times. Whenever a CPU turns on, right, it does few processes. So if it is stored in the cache memory, it will directly access the cache memory. It is a very high-speed memory, so it will not take the CPU much time to access the data, and it can perform tasks in a fast manner. Okay, so that's why cache memory is there, which few instructions which are used repeatedly, those instructions are stored in the cache memory so that the CPU can access it very faster and your CPU can work fast, right? So those things are stored in cache memory. So yeah, these are the few things about cache memory. Like this is also a topic in GATE syllabus, cache memory. Now, memory operation, there can be 2 types of memory operation, right? As explained earlier, CPU can either read or write to the memory. So I will just explain what happens if the CPU goes to read the data, right? How will CPU read the data? I'll just give you a brief overview. So first of all, you have to read the data, right? So CPU first of all needs the address of that particular memory location. So CPU sends address of memory location on the address bus. Okay, it sends the address on the memory location on the address bus. Also tells the also control unit knows that we have to read. So control unit will send CU, then CU will send a read signal, and then the CPU will automatically read from that particular location. Okay, CPU reads. For write, what happens? Same thing only. Data goes from the CPU to the memory. Okay, so for read, data goes from the memory to the CPU. Here, data will go from the CPU to data. So CPU, first of all, CPU again sends the address here, right? CPU sends the address. Then after this, control unit sends a write signal. It will notify the peripheral device that we want to write onto you. We want to write to this memory device. CPU will send a write signal. Control unit, not CPU. Control unit will send a write signal, and then the CPU will simply write the data. And where that data will be? That data will be in the data bus. This will be in the data bus. Okay, this thing. This will be in the data bus. This will be in the address bus. And this will be in the control bus. Okay. So I have given you the example of all the 3 buses. So I have already explained this formula. This formula is very, very important. You can remember this formula if you want, or basics also you understood, right? How I derive this formula, that is also important. That much should be enough. The number of address lines will be equals to log base of 2 of number of memory locations. Okay, or the length, this is also known as the length of address, length of address. Okay, is equals to this same thing only, just in bits. If it is byte, you will convert it into bytes because 8 bit equals to 1 byte. So you can simply convert it. This will be in bits. Okay. So that's how you basically solve this particular thing. This is a very, very important thing. You don't need to mug up the formula. Just try to understand this conceptually, what it means. Okay. So that was about the memory read and write operation. Here also I explained the same thing only, that the CPU sends a memory address via the address bus. CPU generates a read control signal to the instructor memory via the control bus. Via control bus. Then the memory retrieves the data from the specified address and sends it back to the CPU via data bus. And same thing for the write, only just data will now go from CPU to memory. That's it. Okay. So yeah. Now we have other components known as registers. So these are present inside the CPU. Okay, this is not present inside the RAM. This is present inside the CPU. Inside CPU we have few registers. Few are general purpose registers. These are high speed small memory which can be accessed by the CPU. So we have few general purpose registers which used to store temporary storage during computations of the ALU. ALU will add, subtract, all those results can be stored in general purpose registers. Okay, and we have few special purpose registers. What are the special? By the name itself you understand it has something special, right? So what is a special thing? So first special purpose register is accumulator. What is accumulator? It stores the intermediate result received from the ALU, sometimes used as the input to the ALU as well. So whatever operations the ALU performs, then it will give out some result. And where will that result be stored? Result will be stored in the accumulator. And we have a architecture where the accumulator is itself is an input to the ALU. Okay, so we'll see that architecture and there we'll understand what do we mean by this second line. Next, program counter. At the starting of today's lecture, right, we talked about program counter. What does program counter do? Program counter holds the address of the next instruction. So obviously your instruction also will be stored somewhere, right? It will be stored somewhere. So your CPU has to access those instructions. How does it know which address it needs to go to access that next instruction? The program counter has that information. Program counter holds the address of the next instruction to execute. Current instruction is already executing. The next instruction is present where? In the memory location, whatever is stored in the program counter. So that is the task of the program counter. Then another register we have is instruction register. What does instruction register means? As the name suggests, it stores the instruction that has to be executed. It stores the current instruction that has been executed. So what happens basically, whenever my CPU performs some operation, right, some program, it has to perform some program. So first of all, it will go and look at the memory location pointed by the program counter, because program counter know where the instruction is. Program counter knows where the instruction is. CPU will send those signals. It will go to the location. Then it will see some instruction in that memory location, right? Here, in this memory location, there is some instruction. This instruction will then be stored in the instruction register. It's not like I will directly perform this instruction, whatever is written in the memory. No. CPU doesn't work like that. CPU only listens to very specific person. Just like you will only listen to your mother and father, right? You will not listen to anyone else. Okay. I mean, just giving you an analogy. Like if someone tells you, we want to meet, I want to, it's like a date, right? Blind date. I want to meet with you. Will you trust that person so much? No, right? If it is if it is something known, if it is someone known to you, you will definitely trust that person and you will go to that location. Okay, just like CPU also doesn't trust the external things. It only trusts internal things. Okay, so CPU will not directly perform the instruction whatever is written in the memory location that is pointed by the program counter. What it will do is, whatever instruction is written over here, it will first of all store in the instruction register, and CPU only performs the instructions that is written in the instruction register. It does not listen to anyone else. Okay, it does not listen to anyone else. So that's why instruction register is a very, very important register. It stores the current instruction that has to be executed. Okay, so next we have few registers known as the here, right? One thing I forgot to mention is that we call operands. What do we mean by operands? Operands are the contents of the memory, contents of a particular memory on which we are performing some operation. Okay, these are operands. Basically, like, let's say I have an instruction, go to memory location 3 and 4 and add those two values. So what will be operands? Operands will be the contents that are present inside location 3 and location 4. These are my operands. Okay, so I hope you understood the meaning of the operands. So ALU, what does ALU does? ALU has two inputs generally. Okay, and let's say this is location R dash R0, R3, and whatever the content that is present inside R0 and R3, those will be operands, and then ALU will do some operation on the operands and then store the result in accumulator. So that's why, like, the name came operands is from the operation. Name came operand from the operation. Okay, so there are few more special registers known as, first of all, this is known as a stack pointer. If you have ever studied about stack, right? Stack is basically nothing. It is also a data structure of a memory. What happens in that is that stack follows last in first out. Okay, so what does stack means? You can take the hint from the analogy that stack of books. So if I have memory like this, right? Memory like this, 0 0 0 0 0 1 0 1 0 then 0 1 1. Okay, so what will happen is, if it is a stack data structure, right, what will happen if I place something, I cannot access the content directly. I cannot access this content directly. This 0 0, I cannot access this content directly. If I have placed something here, right, let's say some content is there, some x value is there, right, or some a value is there, and this is b. If I want to access this b, right, I cannot say that go to location 0 0 0 and access this. No, stack has only two operations. One is push, another one is pop. So push, as the name suggests, I'm pushing something into the stack. So if I write push a or push c, what will happen is it will go at the top of the stack. It will go at the location pointed by the stack pointer. Stack pointer points to the top of the stack memory. Stack pointer is currently pointing to here. It will go to this location and it will point to this top of the stack, right? It will just point just above this top of the stack and it will push this value. Now C will be temporarily stored here, right? Now again, stack pointer SP will increase, right? Previously stack pointer was pointing here at the top of the stack. Now my stack pointer will point here. Okay, stack pointer also value will increase because the top of the stack itself has changed, right? Because I have pushed some value. Now if I write pop, right, pop A, let's say, I cannot directly pop A. What I will do first, if I want to perform pop A, right, first I have to perform pop C. That is, first let me get this out, then the stack pointer will come here, then I will pop A. Okay, so that is a disadvantage of stack pointer. It has advantages as well that we will not go into right now. Just the basic understanding of stack pointer we need to understand. If you want to read further, you can search in Google what is stack pointer. You will understand that. Okay, basic thing is stack pointer. In our case, it just points to the top of the stack memory. Basically, it has the location of the top of the stack. This much you need to get into your head. Then we have flag registers or program status word. If you have studied microprocessor 8085, you will be familiar with this particular thing. So whenever the ALU performs some operation, right, we store few flags of that particular result. What do you mean by flags? If the result is 0 non-zero, if the result is 0, that particular flag will be 1. If it is non-zero, that particular flag will be 0. If we have carry or not, carry means this, right? Simply 1 1 plus 1 1. How will you add 1 1? I will have a carry. This will be 0. I will have a carry here 1 1 1, and this also will be 1 only, and again I will have a carry of here 1, correct? So this carry flag tells whether there is a carry in the particular arithmetic operation or there is no carry, or few logical things, whether the result was false or true. Okay, so we have a particular place in the memory that stores all this information, whether it will be 0 or non-zero, whether there will be a carry or no carry, okay, and a few other information. So all these things are stored by the program status word register. So it is also present inside the CPU. All these things, right, are actually present inside the CPU. Now we are talking about inside CPU. CPU has very less, like if you have seen processor, right, they are very small, right? So obviously we have very less amount of storage there, but these are very, very important things that the CPU needs instantly. That's why we store it inside the CPU itself. Next is the accumulator. So what is the accumulator? Okay, these were the few things, and next is the memory address register. As the name suggests, it stores the memory address for data instructions. So it stores the address if the CPU want to access the address for data or instruction, and as the name suggests, memory data register stores the temporary holds the data that needs to be transferred to or from the memory. Okay, so memory data register stores this, and memory access register stores this basically. Okay, it holds the data temporarily, whatever data that needs to be written or that is being read from this particular USB or something, right, or any location in the RAM or something. So CPU has very specific things. It only trusts very specific people. It does not trust everyone. Okay, so that's why these are very close to CPU. It only trusts these things. Okay, so I hope you understood the address. Address stores the address. Data stores the data. Simple, right? Simple thing. So like here I have gone into the accumulator in a more deep manner. Just hold on a second. I will drink a bit of water. So I have drank a bit of water. So now I will further discuss about those components which I explained previously, right? So accumulator, as I told you, accumulator is used to store the result of the ALU. It can also act as an input to the operand. So generally ALU has two input operands. Operands, I have already explained what is operand. The things which we are performing the operation on. Okay, we can have this ALU as well, which can take input from the accumulator itself. One of the operand is the accumulator itself. Other operand is the some other memory address or register, something, right? Instruction register, something. Okay, the output is always stored in the accumulator. That is fixed. The input can change. Output will always be stored in the accumulator. Result will always be stored in the accumulator. The ALU typically accepts two input operands at a time. Like in accumulator based architecture, like there is one architecture named accumulator based architecture, which I will teach you in this lecture itself. That will take one of the input as ALU and one of the input from memory or register. Okay, and then again after that operation is performed on those two operands, and then it is stored in the accumulator again for further processing. Okay, so this is specifically for accumulator based architecture. This is not for every architecture, specifically for accumulator. Just hold on. Based architecture. Okay, so yeah, that you can see the block diagram. We can have accumulator which is totally separate. It just stores the result, or we can have this system 2 which is accumulator based architecture, which can act as input to the ALU as well. But one thing is fixed, that the result will always be stored in the ALU. Next I talked about the program counter, right? So like here we have, like I have explained in more brief manner what is program counter. So the program counter holds the memory address of the next instruction to be fetched. So if program counter address is 0x4, currently some instruction is getting fetched, right? Let's say this instruction is getting fetched. So the next instruction, CPU knows that if I have to fetch the next instruction, if I have to get the next instruction, I will go to this address 0x4 that is present on the program counter. Then I will put this particular contents of this address inside the instruction register, and then CPU will take the instruction from the instruction register in the next cycle. So we'll talk about cycles and all those things in upcoming lectures, but for now I hope you're getting the analogy. Think of program counter as a bookmark. Just as bookmark keeps track of the page you are on, the program counter keeps track of the next instruction in the program. When you finish reading one page, execution of an instruction, you move the bookmark to the next page, update the PC to the next instruction. Because you have finished the page, right? You will move your page there, and your bookmark will also be moved in the next page, right? So that is basically the analogy between program counter and a bookmark, page bookmark. There is another thing known as interrupt. So if you skip to a new chapter or jump or branch instruction. Basically what jump or branch instruction means is that program counter is pointing 0x4, but somehow inside the current instruction itself there is a provision to change the value of the program counter. Instead of it being pointed to the next instruction 0x4, I will change the value of the program counter to some other value, let's say 0x1. So now the program counter is pointed to 0x1. So as soon as the current instruction will be, execution of the current instruction will be finished, now I will go to this location for my next instruction to fetch the next instruction. Okay, not in 0x4. So that actually I skipped something, right? I did not follow sequential law. I skipped something. So that is known as the jump or branch instruction. So just like if this chapter is very boring, it's not very enjoying, you can skip that, right? You can skip a slider. There is slider inside the YouTube, right? You just simply skip this particular chapter, then go to the next chapter. Okay, this chapter is very boring, you don't want to understand this chapter, you skip on to the next chapter. You will go and start with a new chapter. So that is just basically what jump or branching means. Okay, so I hope you understood this particular concept, and we'll study a bit about jump and branching later on. Now, instruction register, as mentioned, it temporarily stores the current instruction that is being executed by the CPU. The instruction register is like a recipe card you are currently reading while cooking, right? So you are reading the instructions while cooking, right? So it holds the specific steps instruction you are working on right now. Once you finish the current step, you move on to the next recipe, next instruction fetched by the CPU. So let's say I am cooking like chicken, rice and all, any other dish, right? Any other dish. So first I will read the recipe for chicken kofta or something. Then I will read a recipe for rice, like South Indian thali rice or something. Okay, so I move on to each, that is one instruction. Okay, that recipe is one instruction. Then I move on to the next recipe, that is other instruction. So now each instruction will have some small steps, right? Like putting this much amount of table salt, putting this much amount of sugar. Those small steps are actually called micro operations. So instruction can be a very big instruction, right? I can tell you to write down the I can tell you to what I can tell you to write down an assignment on control systems. What topics have you studied in control systems? Or like this is a very electrical specific example. I can tell you to what you have done today. Write it down. So for like that is a instruction. What you have done today, write it down in a notebook or something. For that you have to perform few micro operations. First you have to get a pen. Then you have to get a notebook or the diary. Then you have to think what you did in the whole day, process that, and then you write it point wise. Okay, then you submit it to me. So there are very micro instructions. So CPU actually performs the micro instructions. It breaks down the bigger instructions into micro instructions and it performs that. Then it submits it. Okay, so we will learn about micro instructions in the next lecture. So that is just a basic overview about the program counter. So I hope you understood the analogy, right? So what happens? My instruction register is here and control unit is here, right? So what actually happens is that instruction register is directly connected with the control unit, and control unit exactly tells who to do what. It controls, right? There is a boss, your manager is there, right? Control unit is like a manager. Now, does your manager perform all the tasks? No, right? Your manager does not perform all the tasks. Your manager just gives you tasks that you perform. CPU is just like that employee who just listens to the manager. Your manager tells you to submit this by today end. Okay, perform this fix this code by today and submit it to me. Okay, so manager controls you. Manager controls you that you need to perform this task, but the task actually has been performed by the ALU. Okay, but there has to be some control unit, right? So that is what the control unit is, and control unit gets from the instruction register. Instruction register is basically the owner. Okay, owner of the company. So owner actually tells what do the owners want. They want more profit, they want more revenues, or they want to sell this, or they want to take their company in other direction. So instruction register has that information stored. Okay, it is just like the owner. And control unit is just the manager. Okay, it controls everything. Okay. So that is the analogy that I wanted to give. Stack pointer as I explained, right? This is a stack like data structure. Okay, if you don't know stack, it's okay, totally fine. This is not that important, but if you want to learn stack, you can just Google stack. What is stack? memory. That much is enough. It holds the memory address of the top of the stack. This is the top of the stack. If I want to push something into the stack, then again stack pointer will be incremented, and if I want to pop something out of the stack pointer will be decremented. Okay, so just like here they're given, again it is the same analogy as the bookmark, like marker on the top of the stack. You can read all this. This is one thing, and another important thing is stack pointer follows the last in first out. Okay, last in first out. This is definitely very deep actually. Its stack pointer follows the last in first out structure. Okay, it follows the last in first out structure. That is very important. There is another data structure known as queue. Queue follows the first in first out structure. Okay, this point you can understand why it is last in first out, because I popped a value 1 at the last, right? I popped it, then I want to take out some value. Which one will be popped? I pushed a value 1 in the stack memory. Which one will be taken out from the stack memory first? This one value, right? This one value, whichever was pushed in last, that has been popped out first. So that's why last in first out. Okay, so now this is the flag register that I was talking about. You have a memory that is in the CPU that stores all this information, right? Whether your flag is 0 or like whether you have a carry after the arithmetic operation, whether you have a 0 or non-zero. So flag register is just like a dashboard warning system in the car. After performing an action like turning the car, applying the brake, the dashboard shows the status indicator, like your fuel is low or engine is overheating. You have some indicators in the car right in front of you. Fuel is low. If it is below some value, it will tell you, it will indicate you that your fuel is low or your engine is overheating. So it's just like that. This flag register is just like that. It flags few specific things. Okay. So yeah, this is about the flag register basically. So now let's understand the address register. So whenever you do these kind of things, right? So before that I just forgot one basic thing is about the stack pointer. Here I told you, right, whenever you add something or push a item into the stack pointer increments its own value. Why? Because stack pointer will always point to the top of the stack. The top of the stack has been changed because you have put something in the value, put something in the stack. So stack pointer will be SP plus 1, and if you pop out, if you take something out of the stack, right? So this memory has been emptied now. So now the top of the stack has been changed. This is the top of the stack now. So obviously stack pointer will be reduced by 1. Stack pointer SP will become SP. Actually we mark it like this. It will become SP minus 1. Okay, that is what your stack pointer will become. Now if I want to give you an analogy, if you have ever coded in your computer, if you do these type of statements, right? If X is greater than Y, how does the CPU check this? CPU goes to the flag register. CPU goes to the flag register and checks if X is greater than 1. So these type of things, right? If X is greater than 1, then you make flag equals to 1. Okay, these type of things, what we do is similar to the concept of flag register. Okay, or if you want to check if X is greater than 0, you just want to check if X is greater than 0 or not. So that can be checked on the flag register. CPU can check it directly on the flag register whether it is positive or negative. So this kind of information generally is stored in the flag register. Next is the address and the data register. As mentioned previously, whatever the CPU, right? CPU doesn't directly talk with the main memory. It has its own memory and address register. So it gets the address from the address register. It gets the data from the data register. That's the basic thing. Okay, that's the basic thing. Okay, so yeah, I hope you understand. Address bus will always be in this direction. It will be always unidirectional. Data bus will always be bidirectional. Okay. Now there are few architectures of digital computer, right? So we have few architectures, there can be many as well, but a few of which you should know, basic idea you should have is the first one is the accumulator based architecture. So accumulator based architecture is ALU. The ALU uses a single accumulator register as one of its input for operations. I have explained this previously as well. This is the accumulator based architecture. Then we have register based architecture. ALU directly operates on the data stores on the general purpose register. So CPU has some GRPs, right, as explained previously. So it will take, the ALU will take the input from those two registers. Register memory based architecture. The ALU can operate on data stored in the register as well as the memory location. ALU can operate both. It can it can take data from the register as well as the memory locations. Okay, that is stored in the RAM. Complex system architecture. It involves multiple layers of abstraction and often combines various types of architecture for complex computation. Like it combines many architectures. We will not discuss about this. Next is stack based architecture. It is not used currently. Stack based architecture means the ALU takes input from the stack. Okay, a stack based architecture uses a stack data structure for executing instructions. We don't use it. Not currently used. This is very old architecture and very slow architecture. That's why we don't use it. That's why you don't need to study this. Don't need to waste any time on this. Okay. So yeah, what is accumulator based architecture? As I explained, right, one of the inputs will be accumulator. Uses an accumulator as a dedicated register for intermediate results. The ALU takes one operand from the accumulator and another from the general purpose register. Let's take an example. This operation, right? Add R5. Add R5 means what? I have only given R5, right? You will say, sir, you have only given me one operand, that is R5. I will add R5 with what? I will add R5 with accumulator, because it is already, like, this is accumulator based architecture CPU. The CPU already knows other input is in accumulator, so it will take the other input from accumulator. So R5 plus accumulator, then again it will store it to what? It will again store it to the accumulator itself. It will again store it to the accumulator itself. Okay, it will add R5 and accumulator. It will again store it to accumulator. So one input is the accumulator itself. Next is the register based architecture. Next, if you see, it will take two inputs as general purpose register. So if I write this instruction, add R1 R2, what it will do is it will add R1 R2 and then it goes to the accumulator, and then I have instructed it to store in R3. So basically R1 R2 is used as input to the ALU, then the result, first it goes to the accumulator, then it is stored to R3. Whatever the result of accumulator we have, that will be stored to R3. So this is the core principle that we do. Okay, this is register based architecture. Next is register memory based architecture. So in register memory based architecture, what we do is we have two things, like this memory, right? This actually will be memory. Okay, this is not correct. This should be memory. So this, right here, memory means any memory in the RAM or something. It is not directly connected with the general purpose register of the CPU. It can take input from the, our ALU can take input from the memory, and then it will give output as accumulator. One of it will be register, let's say R1 or something, general purpose register GRP, and other one will be some memory. It will take the value, one of the operands from the memory itself. Then is complex system architecture. This architecture allows the ALU to operate on operands from general purpose register, memory locations, or combination, anything, right? It can take, like, these things are fixed, but here they are like flexible. They are they are not modular, right? They are not fixed, so it can support that advanced thing. Okay, so we'll not study about this. Like, it is same as the previous ones, but it has both. It can take input from the accumulator as well. It can take input from the memory as well. It can take input from the register as well. That's why the name complex. Okay, then is stack based architecture, that we don't use. Basically, we take the input from the stack. We will not study about this. Just for your own understanding, you can go through this. You can read this. Okay, so if I have an example, I will like give you homework. Okay, this example, you try to write down the steps, individual steps, what the CPU will do. Basically, that in your notebook, try to do. In the next lecture, I will explain all this. If I have this operation to perform, what individual operations or micro operations, like individual operations, the CPU will perform in stack based architecture, in accumulator based architecture, in register based architecture, or in complex instruction set architecture. Okay, so there are 4 architecture I taught you. Just as a homework assignment, you do this. Try to understand how the CPU will work. So I will just give you an example. In stack based architecture, right, what it will do, first it will pop the values from the top of the stack. So the top of the stack will have 2 values, right? So I want to perform, it will have 4 values actually, P, Q and S. I have P, Q, R and S. So first I will pop this, then I will pop this, then I will do the multiplication operation, right? Multiplication P, Q. then again I will pop this, then again do multiplication RS, then I will add the two results, and then again I will push in the top of the stack. So that is what stack architecture it will do. So like you can like write down in a notebook what each architecture, how each architecture will perform, how many instructions I need to make. Don't watch the notes, okay? Don't cheat. So yeah, that's it basically for this lecture. And in the next lecture, we'll learn about different instructions and different micro operations. Thank you for watching, and I will see you in the next lecture. Hey everyone, and welcome back to my channel. So today we'll start with the continuation of this computer organization architecture lectures, right? So in the previous lecture we learned about basics of computer organization and architecture. We learned about few instructions. We learned about different architecture, right? And at the end I gave you homework this question. So this operation was required to be performed in different types of architecture. So I have like I've got a table. So in that table I will exactly explain in each architecture what is happening. So in stack based architecture, right, we generally use the push and pop method. We don't use anything else. So first what do you do? So each steps, right, these steps are actually known as micro operations. This is what we will study today. Each small little steps are known as micro operations. Okay, so first I push the value P from the stack, then I push operand onto the stack. I have to push the values on the stack, right? First I push the values P and Q on the stack. It is on the stack memory. Then I apply the multiplication. I multiply the two variables P and Q. Then again I push the value R and S on the stack. Then I multiply R and S. And the stored value, right, it is already stored in the stack itself. Then I add the two values, both the multiplications, and then finally I pop the value X that is stored in the stack memory. Okay, so these are few, like I'm just giving you an overview table. Obviously it will not exactly work like this. There are multiple internal things that will work. I'm just giving you an idea how it will happen basically, okay, in stack based architecture. So overall in stack based architecture, number of instructions will be 8, and if each instruction is 1 byte, then I will have total 8 bytes memory used by the instruction, because I have to write a code, right? That code will be all these instructions. Okay, so each total memory used by the code will be 8 bytes. Okay, if I assume like one instruction is of 8 bits, just assumption, just giving you an idea, nothing concrete. This is just a hypothetical situation, nothing concrete. Okay, so next is single accumulator based architecture. If my one of the inputs of the ALU is accumulator, then actually I just need to load one of the variables P. Okay, the P is loaded into the accumulator, and if I write the instruction multiply Q, the ALU or the whatever CPU will automatically understand that other variable is the accumulator. So it will be simply P times Q. Other variable is inside the accumulator, which is stored as P, right? P times Q, I will store the value at some register T1. Okay, then again I will load R in the accumulator. Then again I will use multiply R with the accumulator. Multiply S. So R is already in the accumulator, and if I write multiply S, it automatically understands that it is multiplying R times S. Okay, then I will add with T1, because when I do this instruction, right, multiply S, what happens? It multiplies S with R and stores the result in accumulator. And then next time if I write the instruction add T1, then what will happen? I have already the T2 is already stored in accumulator. T2 is what? R times S, right? T2, or currently accumulator has what? Currently accumulator has R times S, and T1 has P times Q. I just need to write add T1. So automatically the other variable is in accumulator, right? So automatically R times S plus P times Q will be generated in the ALU, and again it will be stored in accumulator. And if I want to store it some other register, because I have X, right, my final result was X, so if I have to store it in X, so I will move the value of register accumulator register to X. Okay, so the result will be stored in X. If I write store X, that means the other variable result is stored in accumulator. Automatically it will transfer from accumulator to X. Okay, so here just a hypothetical situation, the number of instructions is lower, it is 7. So it will take lower memory, 7 bytes. So it's a saving, right, of memory and space. So that is the trade-off that you need to do. Few things stack based architecture is good, few things single accumulator based architecture is good. It depends on the situation. Okay, next is general register based architecture. Here what we do, we simply have general purpose registers, right? First of all, move R1 move P to R1, then what do you do? Multiply R1 with Q directly. We can do this directly because one of the inputs of the ALU is general purpose register. So this is the general purpose register, and other operand I am getting from some other place. So it becomes R1 into Q. Okay. Then this is then again I move this result, right? Whatever result I got in the accumulator, I move it to some other place. Like okay, this is stored in R1 itself. This can be stored in R1 itself. Then what I do is I move R2 to R. Like the value R I am moving to register R2, and the multiplying R2 with S. Okay, so R2 currently has R times S. I am storing it some register R2. Okay, so I am using two register basically here. So first of all, what I am doing, I am moving R1, P is going to R1, right? Then I am applying this instruction. This instruction basically means multiplying R1 with Q. Whatever is present in R1, that is getting multiplied with Q. So this will do P times Q. And where it will store the result, as it is a register based architecture, it will store the result automatically in R1. Okay, I don't need to specify anything. It automatically knows it will store the result in R1. Okay, it is stored. Next, I will use the register R2. Now R2, again I am taking R inside R2. Then what I am doing is multiplying. R2 has S, R2 has R, and I am multiplying it with S. So it will multiply R times S, and it will store in R2 itself, right? Then what I'll do, I'll just use this, add R1, R2. Now this is just a hypothetical system, like register based architecture can also have different instructions. I'm just giving you an idea, that's it. R1, R2, right? So R1, R2, what it will do, it will add R1, R2 and store the result in R1. It will just store the result in R1. Okay, and then I can move from R1 to some value register X, whatever they want to store. Okay, so these type of based architecture are there, which you can just get an idea. So in complex architecture, right, it can be anything. It can be anything. I have chosen reduce instruction set. I could have chosen complex. Actually, it should have been reduce instruction set. That is my mistake. This should have been R actually. Don't worry about this right now. RISC, we will talk about this later on. For now, we can skip this because this is not that important. Okay, you will understand this later on in the ending of this computer architecture portion. What are reduced instruction set computer? Okay, so basically they have lower number of instructions. Complex instruction set means they have very huge number of instructions, and to decode the instructions it is also very difficult. That's why the name complex. So in reduce we have lower number of instructions. So every time we have to apply something, we have to give more number of instructions. That's why the memory uses is more than this general register based or the single accumulator based. Okay, just an example, nothing else. So this is okay, this we can understand. Now let's come to today's topic or today's lecture, right? So today we'll first of all understand about micro operations, and then we'll understand what does a machine instruction consist of. So micro operations are low level operations performed on the data stored in the registers within the CPU. These operations are fundamental steps in executing instructions. Like each single operation, right? The minimum, like just like atoms. In atom, fundamental, what are the fundamental elements? Fundamental elements in atom. In atom, fundamental elements are what? Electron and proton. Up until now, whatever research is done, we have found out that these are the fundamental elements, right? We cannot reduce it further. Okay, and just like that, computer architecture also, micro operations are the fundamental operations, like very small tasks. Let's take example, right? Here I have taken an example. You can read. Micro operations are like steps in a recipe. Each step represents a small precise action. Like you have to make some salad, right? To make a salad, you have to chop the vegetables. You have to heat the oil. I'm just giving you an example. And all these things, right? Small tasks. So micro operations are small tasks. Because a program will have huge number of instructions. And instructions will then have its own step, right? And in that each step, it will consist of each small micro operations. So that is the important part. Micro operations are the fundamental small steps that the CPU takes. Okay, in each cycle. Okay, so I hope you got the got the idea. What are different types of micro operations? First is register transfer. So there is a bit of language. Don't worry, you don't have to learn anything new. It is self-explanatory. You will understand just by seeing it. Register transfer. involves moving data from one register to other. So if this kind of thing is written, right? If this kind of instruction is written, what does it mean actually? The contents of R2 is copied to R1. That is the meaning of this. So this is self-explanatory, right? You can understand this. And sometimes what happens is they write it like this as well. This is also written sometimes. R2 is stored in R1. So contents of this is also written on the right hand side. Either way works. Either way, there is no language, there is no like hard foundation that this will be the like rule for writing micro operations. There is nothing like that. Okay, they can define it anyhow. You will understand. You will, by while reading the question, you will be able to understand what is this instruction doing. You can observe, right? Whatever R2 is going into R1. So contents of R2 is going into R1. This is a micro operation. What about arithmetic operation? Performs arithmetic tasks like addition, subtraction. So if I do these type of things, right? I am adding R1 plus R2, then I am storing it in R1, correct? Add the content of R1 and R2, then store the result in R1. So this is also another micro operation. Okay, nothing new here. This is also another micro operation. I'm just adding R1, R2, then I'm storing the result in R1. Okay. Then we have memory transfer. So just this is register transfer. Data is transferred between registers. We can have memory transfer as well. Whenever I write M and bracket, right? That means I'm accessing the memory. That's it. Whenever I write M 2000, so I am accessing the address 2000. I'm going. There is some memory, okay, and there is some address known as 2000. I'm going here and accessing the content 1234. There is content 1234. I'm accessing this. Okay, so I hope whenever I write M bracket 2000, M bracket 1000, 100, that means I'm accessing the memory. Okay, so memory transfer can also happen, right? Like read operation. R1, like the value of the M bracket AR. AR means the whatever address specified by the AR address register. AR is the here is the address register, right? AR meaning address register. So MAR is this: load data from the memory address specified by the address register. It will copy the contents whatever is present. Like let's say assume AR is 2000. So I'll go to 2000 and I will see 1234. I'll copy this 1234 onto the register R1. Okay, general purpose register R1. What about write operation? So this is just the opposite, right? I will do whatever the contents is present in R1. I will copy the contents and go to this memory location and store it. Let's say R1 has 5. So I will store the value 5 on this location 2000. Okay, that's it. That is store the content of R1 into the memory location specified by AR. Now control operation. What are a few control operations? Like includes control specific operations like incrementing the program counter. So program counter, right? If I change the value of program counter, obviously it changes the next instruction location, right? That is the thing that program counter points to. So if I am incrementing program counter by 1, that is also a micro operation, a small operation, right? Fundamental operation. Can I break it down even further? No. Can you break it down? No. You will say, sir, I will add half, then half. There is nothing like half, okay, in computers. So increment the program counter to the point to the next instruction. This is also a micro operation. So let's take an example. For the following micro operations, what will be the final content of the register R4 if the content of the memory address 2000 is 3, all numbers are in decimal? So pause the video and try it for yourself. Okay. So they are telling me memory location 200 has the value 3, correct? So if I just draw the memory, you don't need to do it every time, but as you are starting out now, you can slowly build up pace. So in a memory location somewhere 2000, I have value 3. Okay, this is the memory that they are talking about. And they are asking what will be the final content of register R4. We'll talk about that later on. So first, what does this mean? This means this is M bracket 2000. So this means go to this memory location 2000. This is the address. See the contents 3 and store it in register R3. So this first one, in first micro operation, R3 will be equals to 3. That is the first that is the result of the first micro operation. Then in second micro operation, it is telling me store whatever there is in R3 in R4. So R4 also becomes 3. Whatever content there is in R3, same content you copy in R4. Then next is R4 plus R3, right? R4 plus R3, store it in R4. So you first add the two things and then store it in R4. itself. So I will add the 2, it will be 3 plus 3, 6, and I will store it in R4. It is equals to 6. Okay, so the answer will be simply 6. Was this difficult? No, but this was a gate P by Q. Okay, so like similar question only, just with a different like variant of it. So we have, again, I'm doing the same operation. At 2000 I have 3 value, right? So I can copy this. At 2000 address I have a content that is 3. So then what I can do is I go to this memory location and then store it in R3. So R3 will be again same, only 3, but this time what I'm doing, I'm subtracting R3 by 2 and then storing it in memory location 2000. Okay. Okay, so R3 minus 2, I'm storing it in 2000. So 3 minus 2 is 1. So 1 is getting stored in 2000, correct? So previously there was 3, now it will be 1. So now memory location 2000 has 1. Next I am adding R3 plus memory location 2000. You have to understand that I am not changing contents of R3 here. R3 is still 3. I am just doing a ALU operation. I am subtracting from R3 2 and then storing it in memory location 2000. I am not changing the value of R3. R3 is as it is. So R3 won't be changed, right? Memory location has changed, R3 won't be changed. So R3 plus memory location 2000 means what? It will be 1 plus 3, that is 4. So my R4 will simply become 4. So answer will be 4 this time. This will be answer. Okay, so I hope you understood the point. So let's do a simple, like this was just a building block. Let's do a gate PYQ. So this came in gate 2003. Let me just hold on. If we use internal data forwarding to speed up the performance of the CPU, R1, R2 and R3 registers, and M100 is a memory reference, then the sequence of operation will be. Now there are a few fancy words, don't stress. Okay, what does it mean? Basically they are telling me that we are using internal data forwarding. What does it mean? It means that if I use my internal registers, right, which are present in the CPU, that will speed up the performance. So each time I go and access the memory, accessing memory is slow. What does it mean actually? So I have this peripheral device, right? This USB I have. So I copy something from here and then paste it to my CPU. That will actually always take more time than if some memory is internal to the CPU. If I copy and paste, okay, if it is directly connected, there is some line that is directly connected, that will always be high speed. Okay, so that is what it is telling here. Obviously anything external will take more time than its own internal thing. Okay, just like your cloud storage, right? If anything is inside your phone, if you copy and paste that within your phone, that will not take much time. But if you want to upload it to the cloud or upload it somewhere else, that will take huge amount of time. It is something external. Okay, I hope you understood the analogy. So it is telling me I need to perform the same operation but with better speed. Why it is slower? Because how many times here am I accessing the memory in this particular micro operation? Pause the video, tell me in the comments below how many times I am accessing the memory. In the comments below, tell me. Here actually I am accessing it thrice. Why thrice? Once here I'm going to this location 100, then again I'm going here location 100, then again I'm going here location 100. Okay, so I'm accessing it thrice. I need to reduce it, okay, and perform the same operation. So then like I need to reduce it, okay, and perform the same operation only, just to speed up the performance. So let's first see the result of this. What is actually happening here? So whatever R1 the value R1 I had, I am storing it in memory 100. So I have this memory 100 actually. this box I have. Okay, this is 100. Let's assume that R1 is equals to X, R2 equals to Y, and R3 equals to Z. Okay, and M100 initially it was W. These are all initial values. Now, what is this micro operation telling me? It is telling me whatever the contents of R1 there is, that will go to memory location 100. So R1 had X, so now I will have X in this location, right? Initially I had W, but now I have X. Next, memory location 100 is going to R2 now. Now whatever the there is in memory location 100, that is going to R2. So now R2 is becoming X. Whatever there is in like memory location 100, store it in R3. So R3 also becomes X. Okay. Now I need to replicate this. Basically all the registers will have X. Memory location 100 also will have X. How will I replicate this? So have I taken a page? Yeah. So let's see the first option. It is telling me whatever the contents of R1, store it in R3. So in the option A, it is telling me that, I'll just copy this. Okay, I cannot. Whatever the contents of R1 I have, store it in R3. So R3 will be X, and R2, whatever there is in R2, store it in memory location 100. So R2 had Y, so it will be Y. No, right? It is not correct state, because here, right, everything will have X. Everything will have X, but option A is not correct. It is not even giving me the correct result. So obviously I cannot exchange this instructions, micro operations. Let's see option B. It is telling me whatever there is in memory location 100, store it in R2. So again I will copy this thing only. Okay. Whatever there is in memory location 100, okay, whatever there is in memory location 100, store it in R2. So R2, I will just do one thing. I will copy this again, right, for option C and for option B as well. So option B is telling store the value of memory location 100 in R2. So memory location 100 has W, so R2 will be W. Then whatever I have in R1, store it in R2. Again I will store it in R2. So again I will change it to X, and this also change it to X. R3 also changed to X. But again, memory location 100, right, it doesn't have X. It should have X. So this is not again giving me the correct result. Let's check the option C. In option C, value of register R1 is being stored in memory location 100. So memory location 100 will be changed to X, and value of register R1 is being stored, value of register R2 is being stored in R3. Again, this is wrong, right? Why? R2 value is being stored in R3. So again, I'm not getting X everywhere, right? This is wrong. This is the wrong result. Let's check the option D. Let's check the option D. So in the option D, R1 value is getting stored to R2. R1 value is getting stored to R2. Then R1 value is getting stored to R3. And R1 value is getting stored to memory location 100. So it is giving me the same outcome as the question. Okay, but what is the problem here? What is the problem? No, there is no problem, but what is different here? The difference is, tell me, comments below now. Now tell me how many memory access I'm doing. How many times I'm accessing the memory? Only once. Okay, I am accessing the memory only once. Memory access only once. Now this is the difference between a good programmer and a top class best programmer. Okay, so the best programmer will know exactly how to do a particular instruction. Like I could have written this and this. Which one you would have chosen? Okay, if you would have chosen this, it is doing the same task, but it is taking more time. Why? Because I have to access the memory more times, 3 times to be precise. I'm going outside and accessing the memory, right? But here I need to access the memory less, only once. So this code will take less time than this code. Okay, so that is the difference between efficient code and just a normal code. Okay, I hope you understood this difference with this analogy. So obviously in computer language we write code in C, Python, Java, okay, all this in our compilers, right? But actually our computer, it doesn't understand this. It doesn't understand this simple language, right? Int, num, all this, it doesn't understand. What it understands is ones and zeros. So what happens? We have a compiler and an interpreter. Okay, interpreter, what it does, it converts the high level into assembly level language, and then compiler then finally converts into machine level language. Okay, if I remember correctly, I don't remember the definitions exactly. Okay, so obviously there is an internal converter. So this is the code, this is the program, right? Initially there was a block diagram. Program, this is the program, this is the whole program. Now what our compiler or interpreter does, it breaks the big program down into small micro instructions. Those micro instructions are nothing but ones and zeros. Okay, because those are individual instruction of the control unit. So control unit will send signals, control signals. Those are individual control signals. We will study this when we will study about the control unit. Okay, so our compiler or interpreter, it basically converts everything into zeros and ones. We cannot understand this zeros and ones, but computer can. We have this, and there is a translator that translates all these things. Okay, so like this is a program, but inside a program a lot of micro operations will happen, right? And a term known as instruction cycle is present. So what is instruction cycle? Instructions are generated as machine readable commands derived from high level programs. These instructions depend on the architecture of CPU and the supported instruction set. Okay, so if you take the example, you have an Apple MacBook and you have a Windows PC or laptop. The way you code in Apple, like in Python or C++, it is the same in Windows as well, but their internal architecture is different, right? So the way compiler will convert some code to machine readable format in Apple, it is different in Windows. That's why you have separate apps for Windows and Apple, iPad and Android. You have separate apps, right? The reason being, the compilers are different. They change the codes differently because the machines are different. They understand different languages. I understand Spanish. You understand French, right? Those are not the same thing. There needs to be a translator. That's why there is a different apps for different OS. Okay, just giving you an example. So obviously what compiler does, it converts these high level languages into zeros and ones, but in different formats. There is formatting, right? It depends on which OS I am in or which architecture I am in. Okay, so it all depends, right? Compiler will generate according to the architecture. Compiler will generate according to architecture. Okay, it can be anything, right? Register based architecture or accumulator based architecture, it can be anything. So what happens in the instruction generation, we'll understand this. High level language programs written in high level language such as C, Java are translated into machine code by the compiler. The compiler generates that match the instruction set architecture of the target CPU. So compiler, it will generate according to the architecture of the CPU, and there is a term known as instruction set architecture. What does it mean? It is set of instructions that is present, that is supported by the CPU, that the compiler will already know. So it will only provide those types of instruction to that particular architecture, to that particular CPU. Okay, then there is architecture specific instructions. Yeah, sorry for the interruption. Actually, I had an important call. So as I was explaining that high level language, they are independent of the computer architecture. Okay, but the compiler is dependent. It is machine dependent. How it will convert the language, the high level language, to a machine readable language, it depends on the machine or the architecture, and that architecture is defined by instruction set architecture, which talks about what type of instructions are supported by that particular machine. So compiler only converts to those particular instructions which the CPU can understand. And what is architecture specific instruction? The type of instruction generated depends on the CPU architecture. Like there can be many architectures as well. Here I am just taking one example: register based architecture or accumulator based architecture. It depends how the compiler will generate the code. So how does instruction gets generated? That is what I am discussing here. So first you write the high level language code. So this is the code that you write. Okay. Then what it does is your compiler actually converts it to machine readable format, right? Architecture specific instructions. Then what happens? Then opcode generation happens. What does opcode generation means? In like it is happening simultaneously. Actually, all this is happening simultaneously. The compiler assigns an opcode or operation to each instruction based on the operation. Okay, let's assume like whenever you design a instruction set, right? You designed an instruction set architecture. You had 4 instructions. Let's say add, move, subtract, and multiply. Okay, you had these 4 instructions. So how will you define it? You have to number it, right? That means you design 0 1 0 0 1 0 1 0 1 1. Okay, so you have 4 different this instructions, right? So you have 4 different instructions. So you can assign any one of them. Okay, and then your instruction set architecture is done. So if next time you want to perform add, right? You want to perform a plus b. What your compiler will do? Your compiler will actually convert this plus to 0 0. How it does, that is internal thing. We're not getting into that. But your compiler basically does this. If I am doing a plus b, it will assign it. Compiler understands, okay, it is doing addition. Addition means the opcode for it is 0 0. Your CPU will understand 0 0. That means it is addition. So then it will generate 0 0. Okay, opcode will be 0 0 for that. Only instructions supported by the CPU's instruction set architecture are generated by the compiler. Unsupported operations are either simulated using multiple instructions or flagged as errors. So you can divide your bigger instruction, right? Bigger program into smaller instructions. If you cannot divide it, then it will be flagged as error. There will be a compiler cannot be able to convert it. So let's see an example of this, then we'll understand. Let's see this, right? In simplified computer, the instructions are this: OP, RJ, R1. What does OP means? It means perform RJ, OP, RI and store the result in register RJ. Okay. OP means what? OP means operation. Any operation. I can replace this OP with add. If I replace this with add, what does it mean? It means perform RJ add addition of RY. You add RJ and RI, then you store that result in RJ basically. You simply store the result in RJ. Okay, that is what this add does. Then OPM RI. OP value perform value OP RI and store the result in register RI. Value denotes the content of the memory location M. So if the register is not given, right? If a memory location is given, let's assume add 2000 RI. What does it mean? It means you go to memory location 2000 and you add the contents of that with the contents of RI and then you store the result in RI. This is self-explanatory, right? But I'm just reading it out so that you can also understand this. Move MRI. That means move the contents of memory location, whatever there is, to RI. Move RIM. Move the contents of RI to memory location 2000 or something, whatever the location they will give. Okay. So these are the instructions. Now let's read next. The computer has only 2 registers and OP is either add or subtract. So OP can either be add or subtract and computer has only 2 registers. Let's do R1, R2 and our computer can only add or subtract. So how many bits in the opcode do I need? Only 1 bit opcode will be enough. 0 means add, 1 means subtraction. Okay. So let's read this then. Consider the following basic block. T1 is A plus B, T2 is C plus D, T3 is E minus T2. So what I am doing is, first of all, I am adding two values A and B and I am storing it in T1. Okay, then I am adding two values C plus D, then I am storing it in T2. Then again what I am doing is I am storing the value E minus T2 in T3, and then I am storing the value T1 minus T3 in T4. Okay, these many things I am doing. Yeah, sorry for the interruption, my recording got cut. So as I was explaining this, that they want us to find out the minimum number of move instructions that the compiler will generate while converting this high level language into a low level language. Can you pause the video and try it out by yourself? So the compiler will read each step and convert it into low level language. So when it comes to this step, right, T1, A plus B. So first I have done few assumptions. I have memory location MA, MB, MBC, MD. They can be sequential or they cannot be sequential. Okay, they can be anything random locations, right? They have values A, B, C, D, E. Okay, or everything is in a memory location as mentioned by the question. Now what I can do is simply convert each lines. Okay, if I convert each lines, so first it is T1 equals to A plus B. If T1 is equals to A plus B, that means what? If T1 is equals to A plus B, that means if I am at, like, what I am doing, first I have to move a value MA to register R1. Then I can simply perform this addition MB and R1. These two operations I can perform, right, as explained here. So first I will do this, that it will add the contents of MA, like it will copy the contents of MA into register R1. Then I will add what contents of MB and R1, and I will store the result in R1. That is a small micro operation. So now I do it. Next, what it is telling. So this is done, right? This line is done. Next micro operation is what? Again, I have to do this, repeat this same process. I have to store T2 in some other range, right? So again, I will repeat. Again, I will do move. This time I will store MC into register R2, and I will add MD into register R2. So whatever the contents of MD, I will add it to R2. See, already I have C inside R2. So this will be what? C plus B, D, right? So now from this line, I am getting R2 equals to C plus D and R1 equals to A plus B. Remember, you have to convert according to the flow of the program, according to the flow of the high level language. You cannot mess up with that. You cannot make your own code. Okay, that is like a separate thing. Okay, whatever the program has told you, you will convert those exact lines. Okay, exactly that. Next is T3. T3 is what? Basically whatever I have in T2, it is subtracting with E. So I can perform a subtraction operation, right? If I do this operation, that's sub ME and the contents of R2. So what it will do, it will subtract ME from R2 and then it will store that value. Okay, so I will do that same operation, right? I have subtract operation that is allowed. Okay, so I can store that. So again it will be stored. Do we have subtract operation? We have subtract. Yeah, we have subtract operation. So now it will be stored. R2 will be simply E minus C minus C minus D. Okay, next what I will do, I will do T4. T4 is equals to what? T4 is equals to T1 minus T2. Basically it is subtracting the registers, right? So I will do subtraction of R1 R2. So it will become like the result will be stored in R2, right? The result will be stored in R2, the last register. No, it will be stored in R1 itself. So it will be stored in R1. So R1 will be equals to R1 minus R2. So it is A plus B minus E plus C plus D. Okay. So your R1 is this, right? Your R1 is this. Now you got all the values. You have to store this in the memory, because in the question itself they have told me I have to store this in the memory. The final value of the component should be in the memory. So if I want to store this, what I will do, I will apply another move operation. That will be some memory. Okay, not like this. That will be this, right? It will be R1 and memory X MX. Okay, something like that. MX is somewhere around here. So I'll store the value. So how many move operations did I require? 1, 2 and 3. So I needed 3 minimum move operations. Move operations. Okay, why did I require 3? You can have a counter argument that I could have done this a plus b minus c, right, in less number of operations. I could have done it. You're correct. Actually, you could have done it in 2 move operations. You're correct. But I will not do like that, because that will change the instructions. That will change the high level language. We cannot change the high level language. The compiler will only generate line by line. Okay, it will only generate line by line. You cannot change these high level instructions, because if some smart people has thought of that, if you have thought of that, then you cannot do that. You cannot change the high level language. For the people who are not able to understand, skip it. Okay, for the people who are able to understand, sir, I'm able to figure out a way where I can only use 2 move instructions by changing this a plus b funny business, right? But you cannot do that. You cannot change the high level instructions. That is not allowed. Okay, so minimum number is 3. Minimum number required is 3. Okay, the compiler can only convert high level language, whatever is written in the high level language, line by line into low level language. That's the only job of the compiler. It cannot generate instructions by itself. Okay, it cannot do that. So generally, a instruction, right, has 2 kinds of structure of instruction. It has a operation code, opcode, that defines what operation it needs to perform: addition, subtraction, division, multiplication. And another part is operand. Operand means to which content it needs to apply those operations, like addition, multiplication, to x, y. Okay, that's why it has 2 parts. An instruction is a group of bits that tell the CPU to perform a specific operation. It includes information about the operation to be performed, also known as the opcode, and the data or the memory locations involved. Which operations, like which additions, which values I need to add. Okay, that will be provided by the operands. So instruction code consists of 2 parts. One is the operation code, or also known as the opcode. Another one is the operand. Operation code or opcode specifies the operation, addition, subtraction. Operand specifies the data or memory address. Example, R1 and R2 are the operand and plus is the opcode. Okay, I hope you understood this point. It is the plus is the opcode and R1 R2 are the operand. Okay, so now this, right, this instruction, this is the instruction that I was talking about in the previous lecture. A CPU follows a 24-bit instruction set. Okay, so it can take each micro instruction, right, each micro operations 24 bits. So this length of this particular thing can be in multiple of 2, basically 8 bits, 16, 32, 64. You have heard, right, 32-bit processor, 64-bit processor, just like that. It is the length of this smallest instruction. Okay, so it will always be a power of 2. It will always be a power of 2. Now let's take an example. If I have like 4 operations: addition, subtraction, and an OR. Addition, subtraction, and an OR. What should be the length of my opcode? Minimum length of my opcode. Maximum can be anything. What should be the minimum length of my opcode? The minimum length of my opcode can be add, subtract, and an OR, right? The minimum length will be simply 2 bits. 2 bits is enough. Why 2 bits is enough? Because I have 4 different states, right? I can denote each state like this one: 0, 0, 0, 1, 1, 0, and 1, 1. So only 2 bits. With the help of 2 bits, I can define 4 different operations. So your opcode, the minimum length is 2 bits. So this is one example of instruction set architecture. This instruction set architecture, ISA, actually supports 2-bit opcodes. So I have designed my own CPU. Okay, so that can be the length of opcode. And your operand, right, if your ISA is of 8-bit, total 8 bits, 6 bits can be left for the operand. So what we do by the operand, that also we'll see later on. Don't worry about that. Okay, so these are few elements of machine instruction. First is operation code. Opcode indicates the operation to be executed, represented by the binary value, commonly referred to as opcode. Source operand code, and like this machine's instruction, right, this operand can have many things. It can have, this is done, right, this is we have understood. Next part is source operand reference. So where will the source operand be? Identifies the input operands required for the operation. So from where it will get the input operands. This is the source operand reference. Result operand reference, where it will store the values. It specifies the location where the operation result gets stored. next instruction reference. In a instruction code, the next instruction reference can also be present if a branch type instruction is there. Okay, directs the processor on where to fetch the next instruction once the current one is executed. So branch, if I have a branching, right, we'll understand branching later on. So if I have branching, this also includes the next instruction. So the next instruction can be fetched from this particular information. So a machine instruction can have so many elements, it can have so many things. Okay, let's take a few examples. Okay, so the ISA is the collection of all instructions supported by CPU. It defines the set of instructions that the CPU can execute. Now you don't have to worry what does move, does LDA, load. Previously we had to worry about this. Now you don't have to worry. Gate will specify exactly what does move means, LDA means, load means. But few things you should have basic idea, you should know by beforehand, right? So but still they will provide you. So gate will explain what each operation does, instruction does. So what does this instructions do? Although they will be explained in the like gate will explain this, but let's see what this each instruction does. So let's take for example add, subtract, and or. So these are very simple, right? Just if you write add R1 R2, the contents of R1 and R2 will be simply added and the result will be stored in the accumulator. Okay, that is the example. What are these machine control? Halt, push, pop. Halt actually is a mnemonic, like a short form for stopping the program. So you have a program, right, that does few tasks like instruction 1, I1, I2, I3, I4. You have 4 instructions. Then how does this, if you know that this chunk of program has been done, we send a halt instruction I5 that is equals to halt. That means the CPU has, like, this program has been executed, you can execute next program. So that is what halt does. Now this is a architecture, this was used in microprocessors 8085, but now things can change. Okay, I'm just giving you a basic example. Next is this iterative type examples. Like if you have done programming, right, I think if you remember, you have done this kind of thing, right? For I equals to 0, I less than equals to 100, I plus plus. Then what you had a few lines, bunch of instructions, right? Let's say I1, then I2, then I3, and so on. So this is just the same. In machine level, they don't have this high level language, right? So what it does is it points the program every time we do a loop. What happens? I have, let's say, instructions, right? This is the address of instruction. Let's say 1000, then 1001, then 1002, then 1003. So this is I2, I3, I4. Okay, so I have 4 instructions here, and what I will do is in this 4th instruction, it is inbuilt that I will change my PC value to, just hold on, I will change my PC value to 1000. So every time I come here and I will go back here, but obviously there will be some limit. I will only repeat for I less than equals to 100. I will do this, I will repeat this for I less than equals to 100. Okay, and so this is also like branching is included, but it is repeating the same instructions. But in branching, what happens? In branching, in 5th example, what happens is we directly jump to some other instruction and then again come back. We come back actually. In branching, what happens is, this is the loop, right? This is the loop. In branching, what happens? In branching, actually, we don't come back here. After doing this, right, the PC goes to somewhere else. What we do is, when we are in this instruction, right, when we are in this instruction, let's say I3. Okay, what I will do, I will change my PC value to 2000, some hypothetical system. So I will go here, then again I will have some instructions, I10, I11, this is 2000 address, I12, I13. Okay, so then again I will do all this address, right? Then this last instruction I13 will tell me that branching has been finished, like this particular program done. So what I do is I actually stored, like I was supposed to start from here, right? 1003. After finishing this, I store this value somewhere, save, then I finish this program, then I again come back here after finishing this. I recall the value, in some register I have this address stored, so I come back here and then again I start from I4. Okay, it is not like I'm repeating the same instructions over and over again. So loop and branching are two different things. So these are just, I'm giving you a brief overview. If you have done programming, you will understand all this very easily. Okay, now let's do few questions. First of all, this question, like the terminology of this question is very difficult, so don't worry, I will explain the question to you. You just try to solve after me explaining the question. Okay, no need to read the question, I will explain the question, because the terminology is very big and you have not studied everything to understand everything. Okay, so here consider a new instruction named branch on bit set. So we have a new instruction that is named as branch on bit set. It is just like addition, add, subtract. Its mnemonic is BBS, just like mnemonic of addition is add. So I have a new instruction that I have developed, or they have developed, known as BBS. What it does, like what is the instruction notation? BBS reg pause label. So it is BBS reg pause label. Okay, it jumps to label if bit in position pause of the register operand is operand reg is 1. Now what does it mean? Let me take an example. So if I write BBS reg, let me name R1, pause, let me name 2, label can be anything. Okay, label can be 2000. Okay, so like let me take 8-bit system, so each data is stored in 8 bits. Okay, so R1 has the value currently, I will have 1 2 3 4 5 6 7 8 0 1 0 0 0 0 0. Okay, and what they should tell us is I read the question again. Like one thing is missing. It's register of 32-bit wide. The register is 32-bit wide and bits are numbered 0 to 31. Okay, bit in position 0 is being the least significant bit. So the least significant bit generally lies on the right hand side, right here. So they have mentioned that this is the bit 0. They have told us that each register is 32-bit wide, but I will assume for it to be 8-bit wide for our understanding. We'll do this later on. 32-bit wide, I will do this later on. So they are telling me that bit in position 0 is being least significant bit. So this will be the 0th bit. This will be 1 2 3 4 5 6. I'm taking example. I will take the 32-bit example later on. Okay, so what does this statement means? BBS R1 to 2000. This means R1, check the contents of R1. So this is the contents of R1. Go to position 2. Position 2 is this. Okay, and check if this bit is set or not. Set means what actually? Set, if you know, set means if it is 1. If it is 0, not set. Not set means what? It is 0. Simple as. So I am go to R1, contents of R1, go to this location R1. This is my R1, and I will check whether the bit in position 2 is 1 or not. Currently it is 0, so it is not set. So I will not jump to this location. So this third operand, right, it specifies where I need to jump. It is a branching type instructions. It tells if this bit is set, a particular condition is met, then I will jump. Just like this particular statement, if I equal 1, then do this I1, I2, I3, I1, do I1, I2, like these are all instructions. And if it is not equals to 1, then don't do anything. Okay, only if this condition is satisfied, then I will do it. Then I will do anything, else I will not do anything. It's just like that. So here it can be 2000, it can be R1 as well, R4 as well. So go to R4 and you move your PC to there. Okay, so that is what the instruction does. Okay, I hope you got the point. Now let's read it further. Consider the following emulation of this instruction on a processor that does not have BBS implemented. So if a processor does not have a BBS implemented, but I want to implement a instruction like this without implementing it, how will I do? So you want, like, what do? We make a program, right? It doesn't have that particular instruction enabled. We make a program of it, right? Let's say if you want to always like have a instruction, like we make functions, right? Add 100. If you want to make instruction like this, add I 100, what it does, it always adds I with 100. You want to make an instruction like this, right? But it isn't in your like compiler doesn't support instruction like this. What do? You make a function. You make a function that, how do you make a function? If you know something, you make a function int add, it takes in value I, okay, int I. Then what it does, it makes a new variable x, which is I plus 100, and then you return I, so return x, or what you could have done is directly returned I plus 100. Okay, so your program, your compiler doesn't understand this particular add int I, right? Add I, but you will make that. You will make a function like that. So here also we are making a function, BBS. We're implementing a function even if it's not supported in the CPU. We're implementing it by making a function, by mimicking the same thing. That is what it is telling us here. So temp, it is telling me temp, the value, like a value is being stored in temp, that is reg and mask. So we are ANDing reg with mask, and that and then I'm storing it in temp. Okay, we'll see what is the advantage of this. Branch to label if temp is non-zero. If temp is non-zero, then I will branch. Basically, if bit is set, if this temp bit is set, then I will branch. That is my task. If this bit is set, then I will branch. Okay, branch. I will, like in BBS, what happens if that particular bit of that position is set, then I will branch. So temp tells me what? Temp tells me whether the bit in that position is set or not set. That is the task of temp. Like in my new CPU that does not have BBS implemented, that is how I'll understand. If temp is set, I will branch. If temp is not set, I will not branch. But I need to have a mechanism that can check the temp, right? That can basically check that, like, how do I calculate? Okay, that I have to take into account. Now, the variable temp is a temporary register. For correct emulation, the variable mask must be generated. What? So how do I generate mask so that it checks exactly that position of this reg in which I need to check, right, whether the bit is set or not. So let's understand one thing. This is what? This is left shift operator. What does left shift operator do? So left shift operator, right, if I have a value like this 0 0 0 1 and I left shift by one position, this one means one position, then what happens? All the bits will be shifted by 1, and the last bit, like whatever bits I have shifted by, the last few positions will be left, right? They will be simply replaced with 0. So this will result in 0 0 1, and the last bit is left, right? Because this 1 has been shifted to the left hand side, so this last bit will simply be replaced with a 0. That is what left shift means, shifting all the bits on the left, and right shift means shifting all the bits on the right. Okay, so let me check. Like I have to implement, what my task is, I have to check whether a particular bit on the position is set or not. My task is, the stem provides me whether the bit is set in that position or not, in that position. Okay, so how do I check? Let me do all the options, then I will check, right? So let me take the first option, not first option, let me take the second option. Okay, second option, what does it tells me? It tells me mask is, first I will take the simple thing, 8-bit. I will then tell you for 32-bit. Let me take the simple thing. Okay, 8-bit only. So this will be 0xFF, left shift position. So let me choose values for position. Let me choose position equals to 2 again. Okay, so what is my mask equals to? So what will be my mask equals to? Position is 2, and let me choose reg equals to 1 0 1 1 0 1 0. Okay, 0 1 0 0. Now what it is doing is, it is simply like, what is this? This is 1 1 1 1 1 1. This is just simply hexadecimal to binary conversion. This you can do. Okay, then I am left shifting this by 2. So if I left shift everything by 2, all this will be 1 1 1 only. Last 2 digits, right, I have left shift. So last 2 digits will be set as 0. Okay, now if you know anything about programming, this is not how you implement the mask. Actually, mask only gives me the information of that particular bit. So I will give you an example. Let me, before solving this question, right, I will give you an example. What does mask do? What does mask do? Mask actually gives me the information of a particular bit. I will show you an example, right? If I want the information of the second position, or the 0th position. So what I'll do, I can implement my mask like this of 8-bit CPU 001, and if I AND this thing with the register, right? So reg has some value. Reg has some value. If I add this with mask, okay, what it becomes, what it will do, it will make 0 all the other bits just except the last bit. It will add 1 and anything is that particular bit. So 1 and x will always be equals to x. It will depend on x. What is x? If x is 0, then answer result will be 0. Then result will be 0. If x is 1, result will be 1. So mask gives the information of that particular bit. Mask gives me information of that particular bit. Okay, if I want 0th position information, I will place the mask, I'll place the 1 bit at position 0 and all other bits will be 0. That is the task of mask. But here am I doing something like that? No, right? I'm not doing right here. In mask, I'm storing everything, right? All the ones are there. It will give me information of all these bits. I don't want the information of all these bits. I just want the information of position bit. That is the second position. That is I want. Okay, so I don't want information of all this bits. Okay, I don't want this. So this option is not incorrect. This option is not correct. Okay, let me check the option C. In option C, what we are doing, we are directly storing the mask as position. Now, is this correct? We are storing the mask as position. Is this correct? So ultimately what we're doing, we're ANDing the mask, right? We're ANDing reg and mask. So if I store position, right? So position is 2. So like I will copy the situation here again. It is telling me, like, if you AND this with mask, right? If you like do reg and AND here, reg and mask, this will give you information about all the bits that I don't want. Now what am I doing here? Here I am directly storing the position value in the mask. Is this correct? This is again not correct. What the mask will store now? The mask will have, like, position is 2, right? So I will store the binary of it. What is the binary? 0 0 0 0, then 0 0 1 0. Okay, so I am storing the binary of it, right? Which is again incorrect. If I AND this, if I do mask and temp, just I'm thinking 32, I'm thinking 8-bit processor. Don't think about 32-bit now. Every time break your question down in smaller bits, then you will go to the higher bits. Okay. Temp and mask. This does not give me information about the position 2-bit. What is the position 2-bit? Position 2-bit actually is this one, right? This is 0 position, this is 1 position, this is 2 position. So I want information about this. If I'm AND this with my register, what it will do? It will make it 0. I need to like extract the bit position 2, right? But it is making it 0, then it is storing it in temp. So it is not the correct answer. So again, C is wrong. Like this, you can eliminate D as well. What is D doing? So D in D, we are simply storing 0xf, right? We're storing everything all once. Now if I AND with this, like 0xf means what? Like the last bit is 0 actually. That means like if 0xf is given, then again this is wrong. Why? Because this is just ANDing 0, not 0, sorry. No, this will be actually, no, if this is f, right? So that means initial bits are 0. 0, 0, 0, 0, 1, 1, 1, 1. So what it is doing? It is simply, if I AND this with some reg, right? I will store the information of all the last 4 bits, and all the first 4 bits information will be gone, right? So again, this also repeats the same statement here. I don't want information of all these bits. I just want information of position 2-bit. That is my priority. So if I check now option A will be obviously correct. That's why I'm skipping it. If I check option A, what am I doing in option A? In option A, mask is equals to 0x1 left shift pause. So if I just let me take an example again. Pause is 2, and what is this? This is 0 0 0 0 0 0 0 1, and I want to left shift by 2. If I left shift by 2, this one will be here once, and then this one will be here, right? So it will be left shifted by 2 values. Everything will be left shifted by 2 values, correct? So this will become 0 0 0 0 0 1 0 0. This is my mask. And now if I AND it with reg, right, what will be stored here? Only this bit will be stored, right? Whatever the bit position, what is this position? Second. If I 1 and x will give me x, correct? 1 and x will give me x. So whatever the value, like in position 2, let's take example that reg has x bit. If it has x bit, if I AND it 1 and it with 1, then I will get back that same x again, same x, right? If it was 0, 1 and 0 is 1 and 0 will be 0. 1 and 1 will be 0. It all depends what is x. So it all depends on reg. If that bit is set, then I will, then this is marks, then my temp, right? This is the temp, right? This thing is the temp. Then my temp will be 1. If this bit is not set, then my temp is 0. So that is my task. That was my task, right? To implement a instruction set like that. Then what I will do, I will code like check if temp is 0. If temp is 0, don't branch. If temp is 1, branch. So my task is done. So this temp exactly tells me the information about only the second position. So obviously from here option A will be correct. So like I just wanted to say, we have just started and you don't know everything about computers. So that's why I have explained the question. I'm explaining everything. It's okay if you are not able to solve this question by yourself. You will be able to solve this question when you have studied everything about computer architecture. Everything is interrelated. So that's why teaching these subjects is very, very difficult, because everything, like sometimes one question uses some other component of the subject, right? So it's very difficult for me to like at once explain everything, because that will then be only theory. We won't be learning any questions, but we need to learn questions as well. So that's why I'm trying my best to replicate whatever I can. So then you can apply the same principle for 0 to 31 bit. It will not change. Okay, you can do example. You can even take example for 4 bits. Take example for 4 bits, write it down, understand it by yourself. Then you will be able to understand that what exactly this does. If you have ever studied bit masking or bit manipulation, you will be familiar with this concept. If you are lagging in this concept, you can go search bit manipulation or bit masking. That will clear your concepts more. Okay, so this question was pretty good. I have tried to do my best while explaining this question. Let's read another question. Okay, so let's read this question again. If you are not able to solve this question, it's totally fine, because again this has some relation with upcoming chapters. But if you are able to, it's good. Sometimes you have to go with your intuition, right? Sometimes you have to go with your intuition. Let's read the question. Consider the following sequence of micro operations. So all these are micro operations. MBR, PC, value of PC is being stored in MBR. So MBR is what? MBR is what? MBR is also known as memory buffer register or memory data register. Okay, memory data register. This is also known as MDR that we studied. That is memory data register. It is also sometimes called as memory buffer register. So value of PC has been stored in MBR. Fine. Then MAR, X value is being stored in MAR. So MAR, memory address register, is being stored in MAR. Okay. Some X value, some Y value is being then loaded to PC. So the next instruction that the CPU will fetch has been changed. It is not sequential. It is some random value. Okay. And when we do it, it seems like there is a jump like instruction. Because whenever I change the value of PC, it seems that I'm not following this sequence. I'm going to some other instruction. Okay. Then MBR is being loaded to memory. MBR is being loaded to memory. MBR means the value of the previous PC, right? PC previous. So memory, let's say memory 1000 or some address I'm storing it in. It is PC previous. So I was supposed to go to this instruction, but I am not going to. I have changed my PC and I have stored this previous PC in some memory. Maybe for later use. Maybe I want to take it back later. Which one of the following is a possible operation performed by this sequence? Okay. Instruction fetch. Instruction fetch happens when the CPU loads the instruction. How will the CPU load the instruction? CPU will load the instruction like how? When some the instruction, right, or memory data register is going to IR. CPU loads instruction on IR. So is there any IR here? There is no IR. So obviously this is not instruction fetch. Don't worry, we'll learn about instruction cycle there. Instruction fetch, instruction decode, instruction execution, all this we'll learn. Don't worry. Okay. So instruction fetch is not possible. Now, what about operand fetch? Operand fetch means I am loading the operands from the memory to my own registers like R1 or R2 or some other register. Am I loading anything from the memory? Am I loading anything from the memory? No, right? I'm not loading anything from the memory except here. So this is again I'm loading, I'm not loading anything from the memory. Nothing is coming from the memory to the PC. Okay, I am not loading anything from the memory. I am not loading anything from the memory. This happens when a instruction like move R1 to 2000. Okay, like data movement, right? I'm loading something from the memory. Yeah, it is not happening. Am I loading some operands from the memory? No. So I'm not doing any memory read. So this is again wrong. Okay, conditional branch. So this can happen. Okay, this can happen. In conditional branch, there is a possibility. Conditional branching means what? I will check a condition. If that condition is true, I will move to that. Right? I will move to the new instruction. But am I checking any condition here? No. No condition is being checked. Yes, I am changing my PC. PC has been changed. Okay? That is correct. So I am doing some type of branching, but am I checking the condition? If I equals to 0, then only do this. Am I checking here? No, I am not checking. I'm directly going to some other branching to some other value. I'm directly changing PC. So no conditional branching. So I can take this here. No condition checked. And another thing about branching is that I'll teach you later on as well. In branching, this is a bit of theory that you should know. In branching, we only, this is a very important point, right? We only update the current PC value. We don't store the previous PC anywhere else. So if previously I told you, right, that in branching that we store the previous PC, I was actually wrong here. This is not the case. If I mentioned here, right, in this, actually what we do, we just simply branch to some new instruction. We don't come back. That is for interrupt. Okay. So I will talk about interrupt here. We don't store the previous PC anywhere. So this is about branching. And in interrupt means I'm interrupting you, right? I'm interrupting you. Okay, let's say you are speaking something. I interrupt. Hey man, you are wrong. Then you will address my interruption. Okay, then even you will continue. So what interrupt does is, in interrupt, the CPU has been interrupted. That's why the name interrupt. In interrupt, we update the current PC. So basically we will tell the CPU, no, you don't have to do this instruction. You have to do some other instruction. You go to that instruction, that program, update the current PC and store the current previous PC in some memory, for like continuation, to continue operation in memory for CPU, for CPU reference after the interrupt has been finished. Don't worry, I will teach about interrupt cycle in the next lecture. I am just giving you an overview. What does interrupt do actually? So what happens is, CPU, let's say I am that person, right? So you are doing some task. Okay, you are doing some task, you are finishing some project. Then you got a phone call from your friend that, man, Mondol sir has asked us to submit this new assignment by tomorrow. Okay, else he will detain us all. He will fail us all. So you were doing some project, okay, of some other sir, let's say Ram sir. Now Mondol sir has given you some new project, right? And it's very urgent. So what you will do is first finish the project given by Mondol sir, okay, within 2 hours, 3 hours, whatever it will take, because he will fail you. Then after that task is finished, you then again come back to your Ram sir project. Okay, you finish that. So in between you had an interrupt. Okay, you had to do that particular task. Then again, once it's finished, you come back to your previous task. That is exactly what is happening. Current PC stores the PC of the sequential instructions. Let me give you a few examples. I1, I2, I3, I4, and let's name this as I11, I14, I15. Okay, so what happens? My PC, it will do instruction 1, then instruction 2, then it will come to instruction 3, and instruction 3 specifies that there is an interrupt. That interrupt specifies me to go to I11. Okay, so here what happens? Although I should have gone to the next, PC currently stores this I4, but that will be cancelled. I will store this I4 address somewhere else in memory, and the PC will be updated to the I11 address. So my CPU will next do the I11, then I14, then I15. Then again, I will retrieve back this value from memory to PC. So again, my CPU will ask PC what is the next instruction. So PC will tell yes, it is pointing to I4. So I will come back here. So that is the whole cycle. Don't worry, I will explain this in interrupt cycle. It will come. Okay, so here obviously it is not conditional branch. First point is there is no condition being checked. Second point, branching, we don't store the PC value anywhere. We don't store the PC value anywhere. We just directly update the PC value. Directly update. But in initiation of interrupt service, we store the PC value somewhere so that we can use it after the interrupt has been finished. So option D will be correct. Okay, option A will not be correct. Okay, so this is how we do it. So it's okay if you could not understand few things because everything is interrelated. So it's not possible for me to explain everything in single lecture. It will take some time. So now we will finally come to bit versus byte versus word. Okay, so what does bit versus byte versus word means? Bit means a bit is the smallest unit of data in a computer. It can represent two states, 0 or 1. We already know this. I will not stress on this much. Byte is a group of 8 bits. So generally, obviously, a bit, right, is very small thing. So explaining that using that as a unit will be very, very difficult to us because in our computers, how many gigabytes we have, gigabytes of data, megabytes of data. So that's how we define the storages, right? So bit is a very, very small number. It cannot store, it can only store 2 information. So that is not enough for us. That's why. Okay, so that's why we have this byte, and then again we have another thing known as word. So what is word actually? So a word is the number of bits that the CPU processes as a single unit. Your CPU is 8-bit processor, 16-bit processor, 64-bit processor. So it specifies the length of what? Length of each micro instruction. It specifies the length of each micro instruction. So if it's a 16-bit architecture processor, it will have 16 bits. They will be defined each micro instruction will have 16 bits. So CPU will understand what it needs to do accordingly if one bit is 0 or 1. Okay, so that is the difference between bit and word. Okay, so this bit and word actually is used to store in computer, like how we store the data, that is also it is used to. So let's read a bit more. The fundamental alphabet, just like if you take the example, right, your atoms, if each atom has protons and neutrons, so we don't say that one atom and one electron, one proton, right? Electrons are there in thousands, in millions, right? 6.23 into 10 raised to power 23. So they are in huge numbers, right? So just like that, bits will be also in huge numbers in computers. So the fundamental alphabet of digital computers consists of 2 symbols, 0 and 1, collectively known as bits. A group of 8 bits is referred as byte. The term word denotes the group of bytes processed together as a unit. So if my computer is 16-bit processor, I will say one word will be equals to 2 bytes. So this is not fixed actually. Yes, 8 bits equals to 1 byte, that is fixed, but how much the one word will be equals to, that I don't know. That depends on the computer architecture. If my computer is 32-bit, right, then what will be one word equals to? One word will be equals to 4 byte. If my computer is 64 bits, one word will be equals to this is 8, right? 8 bits, so 6. One word will be equals to 6 bytes. No, not 6, sorry. It will be 9. One word will be equals to 9 bytes. 8 bytes. Sorry. One word will be equals to 8 bytes. Okay. So that is the difference between word and byte. I hope you understood. Now how do we store large data in computer? There can be 2 ways. Like I cannot store bit by bit, right? So how much information can a bit consist? Only 2 information. So that is not acceptable, obviously. I store data in chunks. So I told you previously, right? We call this cells. I store data in chunks. So I have a complete 1 byte data. So there can be 2 types of memory storage. One is byte addressable, another one is word addressable. So let's read it. In a computer system, memory can be either byte addressable or word addressable. If it is a word addressable, then word size determines the unit of data processing. So data, like when I say give me, go to memory location, like store in HTML R1, go to memory location 2000 and store that value in R1. But how many bits I will copy? How many bits I will copy? Because in memory location 2000, from 2000 to how many bits I will go and I will copy that value to my own system R1. How many bits do I need to copy? I don't know. That will be specified whether the computer has byte addressable or word addressable. If the computer architecture follows byte addressable, then if it is byte addressable, then I will go to memory location 2000 and I will copy 8 bits. Okay. If it is word addressable, so for example, let's take one thing. I have a 16-bit system, right? 16-bit system. If it is 16-bit system, then one word will be equals to 2 bytes. Then if it is word addressable, how many bits I will copy actually? Tell me in the comments below how many bits I will copy if it is word addressable. I'll totally copy 16 bits. I'll totally copy 16 bits. If it is word addressable, I will totally copy 16 bits. If it is byte addressable, I will copy 8 bits. So you can observe, right? There is a huge change. How many bytes I will copy? How many data lines I will need? In byte addressable, I will only need 8 data lines because I am copying 8 bits at once. In word addressable, how many data lines I will require? 16 lines. So everything is interlinked. I hope you understand, right? The architecture. So it depends. You have to plan everything from the start. Okay. So they are addressed like this as well. So in byte word addressable, right? Address will be like this will be 0, this will be 1. So each word will increment the address by 1. Each word. In each word, how many bytes I have? 2 bytes. Okay. But in byte addressable, I will increment by 1 with when I cross each byte. This has 8 bytes. This has 8 bits. This has 8 bits. So once I cover this whole 8 bit, right, so it will have 8 bits like this, 8 bits, 8 information. This is done. Then I will move on to the next starting address 1. This will also have 8 bits. Then I will move on to the next starting address. This will also have 8 bits. So all these are incremented by 1. Okay. Because they are stored in chunks of bytes, 8 bits. Here, how they are stored? They are stored in chunks of word. Or currently in my current example, this is just an example, one word is equals to 2 bytes. Or it is equals to 16 bits. So I will have 16 bits here. I finished this chunk of data. Then I will move on to the next data. So this will be index 1. So I will increment by 1. Each time I pass 16 bits, I will increment by 1. The address will be incremented by 1. Why? Because they are stored as a group of 16 bits. And here they are stored as a group of 8 bits. Here as word addressable, here as byte addressable. Yeah, sorry for the interruption. I just had to drink a bit of water because my throat was literally getting dried up. So as I was continuing, so let me give you an example. So let's take in byte addressable, what will be the address? Like I will just write it down here. Address of 0th word. Okay, 0th word. Or I can say first word. And if I just copy this thing, right, just copy it, this thing, this will be second, third. Okay, let me give you another different perspective. Second and third. And here, what is the address of first, second, third word? In which case, in byte addressable and word addressable. Word addressable. So here, if it is byte addressable, right, my system is 16-bit computer. Okay, so if it is byte addressable, the address of first word will be here. It will be 0. It is fine. What about the address of second word? What is one word equals to? One word equals to 2 bytes. So my one word will be finished 1 byte, then 2 bytes second. So my address of second word will be Actually 2, it will not be 1. Location of second word, so it will be 2. Location of third one, similarly, third word, right? Again, I will finish this one word, 1 byte, then 1 byte. So all of this is finished. I will come to here. So it will be 4. It will be 4. What about address of first word in word addressable? It will increment by 1 every time. Address of first word is 0. So this is same. Then address of second word is here in the first index, right? First row, yeah. That was 0th row. And address of third word will be in the second, sorry, the third row, technically in the third row, basically here. Okay, so it is incrementing by 1. So there are advantages and disadvantages to this. So I need less number of address lines here. Why? Because my address is increasing slower, here address is increasing faster. I will require more number of address bits. So these are here, I will need more number of address bits. Okay, but here I will need less. Here less required. But what is the counter argument to this? Here, right? If let's say you want to only store 10 bits of data, like you want to store 10 bits, right? You have some task and you just require 10 bits. You don't require all 16 bits. So if only 10 bits are required to store, okay, or let's take an example, like I will take a better example, 8 bits. 8 bits are required to store, and you are using byte addressable, or word addressable, not byte addressable, word addressable. Then what will happen to the other 8 bits? Because I told you, right, your memory will store data in chunks. It will store in groups. It's not like you can do one thing that, okay, as I am storing information in 8 bits, what I will do, I will store the 8 bits in the first word, then I will store the next 8 bits in the half of the second word. No, a word is a single quantity. It's a single entity. You cannot break it down. If I am telling you one word, it gives me information about that particular quantity. Okay, so you cannot break it down. If you want to store the next 8 bit, right, then you cannot store it in same word. You have to store it here in the next word. So lot of data, lot of bits get wasted. If I have less number of things to store, lot of data gets wasted. Lot of bits get wasted. What is the example of this? If you ever have done C, right, and if you have initiated a variable char x equals to 2. Okay, so what is this? This is actually like a char in C. Generally it requires only 1 byte of data. If your memory is word addressable, obviously I cannot, like if I have multiple chars, I cannot store one of the char here, one of the char here. No, it cannot be like that. If one char is here, that's it. Then I have to store the next char here in the next word. So a lot of data gets wasted. So we don't want this. So that is a disadvantages of word addressable. Sometimes it depends what type of things you are using. So all this is hypothetical, and this is example. I'm just giving you an example. Okay. So in technical terms, what do they call this phenomena? They call data fragmentation, or sometimes we get fragmentation error. So a lot of errors like this happens sometimes. Okay, so this was the difference between word and byte addressable. So I have given you how many lines also. I have given you that information as well. Okay, I hope you have picked up that thing. So pause the video and try to solve these questions. This one, then this one. Okay, obviously don't worry if you are not able to solve. I will solve, because these are the first few lectures. I will give you hints. Obviously this needs to be at the top actually. So let's solve this question. So here the capacity of a memory unit is defined by the number of words multiplied by the number of bits per word. So total capacity of a unit, capacity of a memory, or I will write this later. Total capacity is defined by the total number of words, how many words present in that particular memory unit, multiplied by the bits per word. So per word, how many bits are there? So exactly what is this? This is giving me the total number of bits present in the memory. Total number of bits present in the memory. They're telling me how many separate address and data lines are needed for memory 4K into 16. So here they have given me memory, capacity of memory is 4K into 16. So from this information I can directly emulate that number of words will be 4K and bits per word will be 16. They are telling me how many address and data lines I will require. Basically by address and data lines they mean how many address bits and data bits I will require to in this architecture to explain everything, okay, to for this architecture to be implemented. So one small thing you should know, 1K in computer systems, right, is generally denoted, like we denote K with 1000, but 1K in computer systems is denoted by 1024. Okay, this is 2 raised to power 10. So this is just a notation. So total number of words, how many total number of words I have? Total number of words is total number of words is, this is 2 into 1K, not 2, sorry, 2 raised to power 2 into 1K, that is 2 raised to power 10 is equals to 2 raised to power 12. So this is the total number of words that I have, okay, and it is word addressable. So here, right, if I copy this particular part, the question is telling me that my memory has memory like this, memory like this, and in between it has total how many 409, this will 4095 because it is starting from 0 to 4095. Total how many address locations, how many words I have? 4096 words. Total I have 4096 words. I have total 4096 words. So if I have total 4096 words, how many address bits I will require to define 4096 words? How many? This is what? This is 2 raised to power 12. So I will require how many? 12 address bits. If you want to direct calculation, what you can do, you can take the log of this value. If I take log base 2 of 4096, I will get 12 bits. So for address bits, I will require 12 bits. And for data lines, how many data lines I will require? So data lines, right, it defines how many bits is inside a word, this bit per word, that is given 16. So how many data bits I will require? So each word, right, each word has how many divisions? 1, 2, 3, 4, total 16 bits. So how many data lines should I have in the bus? The system bus should have how many data lines? Simultaneously, if I want to transmit data, 16 lines it should have, right? It will send either 0 and 1 on those 16 lines. So data bit should be 16 bit long and address bit should be 8 bit long. So option A, not option A, sorry, option C will be correct. So even if you don't know anything about memory, still you are able to solve it. Okay, because they have given in the question, they have given what this 4K into 16 means. This is standard. This is how we define a memory. How we define a memory? A memory is defined like this. Okay, I didn't want you to just mug up the formula. I didn't want you to do that. I wanted you to understand this conceptually. Okay, so generally the capacity of a memory, okay, or ROM memory size, capacity of memory, this has been written later on as well. It is defined like this: 2 raised to power m into n, where m is the number of address lines and n is the number of data lines. Okay, so these are the two things that you need to understand. Like, I didn't want you to mug up this formula simply. They have defined in the question itself. They have explained what does this multiplication means. So please read the question carefully. Gate will give you all the information. Okay, let's do another question. This is the 12th question. A processor can support a maximum memory of 4 gigabytes, but the memory is word addressable. A processor can support maximum memory of 4 gigabytes, but the memory is word addressable. So now I know what does memory means. And it can support a maximum memory of 4 gigabytes. So 4 gigabytes, its memory size they have given me is 4 gigabyte. 4 gigabytes. This equals to 4 into 10 raised to power, 2 raised to power. 2 raised to power. How much giga means actually? Actually giga, if you know, 1 giga is what? 1 giga is 10 raised to power 9. So actually, in our case, right, generally 10 cube is defined as 2 raised to power 10. So this is 10 cube raised to power 3 So this will be 2 raised to power 30. So just be careful with that conversion. This is my memory size, right? And I have 4 gigabytes here. So this will be equals to 2 raised to power 2 into 2 raised to power 30 bytes. Remember, this is in bytes, right? This is gigabytes. Whenever this is capital B means bytes. Small b is bits. Capital B is bytes. Okay, that's why capital. Okay, I hope you understood this difference. This is 2 raised to power 32. Next, what they're telling me, it is word, memory is word addressable. Okay, the size of the address bus of the processor is at least how many bits. Okay, a word consists of 2 bytes. So one word is 2 bytes. One word is 2 bytes. So the size of the address bus of the processor at least must be. So how do I define the size of address bus? So it is word addressable, right? So how is data stored in the memory? It is stored in words, chunks of words, right? This is one word. Again, I'll copy this previous one. This is already copied, right? So this I can directly paste here. Stored in words. Okay. Now if it is stored in words, how many like bits does each word consist of? Each words consist of 2 bytes. Okay, they have mentioned in the question, they have told me each word is 2 bytes. Now they're telling me how many address bus do I need. So how many of words do I have that I need to compute? So how do I compute it? Total number of words should be equals to what? It will be like or total number of capacity or total number of bits, right? Total number of bits should be equals to what? Should be equals to total number of words into bit per word. Okay, but they have given me everything in bytes. So shall I convert this into bytes as well? So I can convert this formula into bytes as well. What you can do, you can convert everything into bytes, right? This will be total number of bytes will be equals to total words into byte per word. Just simple conversion I'm doing, right? So unit of word gets cancelled. Byte is equals to bytes. That is what I'm doing. So now what I can do is do I know total number of bytes? Yes, I know, because they have given me the maximum capacity, memory size. This is the total number of bytes I have, right? This is the total number of bytes. Do I know word per byte? Yes. What is word per byte? Yeah, sorry for the interruption. Just my recording got cut. As I was explaining, one word is 2 bytes. One word is 2 bytes, right? So how many bytes per word? How many bytes per word? Okay. How many bytes per word? It is simply 2, right? I have for per word, I have 2 bytes. That's why it will be 2 bytes per word. This is the unit of bytes per word, simply. Okay. So I have 2 bytes per word. So I will replace everything here, right? I will replace everything here. What is the total number of bytes they have given me? I have found it out, right? That is 2 raised to power 32 number of bytes, right? So each word, right? Each word has how many bytes? 1 byte here, 1 byte here. Total 2 bytes. Each word has 2 bytes. So this will be replaced with 2. This will be replaced with 2 raised to power 32. And this I can replace with x for now. Okay. So this will become 2 raised to power 32 equals to x into 2. So x is 2 raised to power 31. What is this? This is the total number of words. Now, I got total number of words. I need to define address. I need to locate each of these words. This is the total number of words. How many bits I will require to locate each of these words? Either take the log of this. So, number of address lines. You either take the log of this particular thing, or from the power of this 2 raised to power 31, right? I can understand I need 31 bits. So this will be 31 bits. I will require 31 bits to define this many number of words, because it is word addressable. So there will be total from 0, it will go to 2 raised to power 31. From 0 it will go to 2 raised to power 31. So the answer will be 31. This is the answer. This is the solution. Okay. Like there is one formula Okay, that you should know. That formula is what? That formula is this. Memory represented in the form of memory is represented in the form of this 2 raised to power n into m. Okay, this is in bytes. M is what? M is the number of data lines in the system bus. N is number of address lines in the system bus. Okay, and like I just derived the formula. Generally, I've just written it here, right? The formula here I've written capacity of a memory. This formula I've written, but I didn't want to solve using this formula, right? I didn't want to solve this formula is written in the next slide as well, but I didn't wanted to just mug you up this formula. I wanted to explain this concept. This formula is important. Okay, I will highlight this, but I could have directly written the formula and solved it. Okay, but that would not have been any fruitful to you. So that's why I didn't do it. This is the formula. Okay, the color is really bad. Let me take some other color. Yeah, this color is important. This whole formula is important actually. Okay, I somehow won't be able to do this. I will just what I will do is I will just square mark this. This formula is right. These formulas are actually pretty important. I can convert this into byte, but I didn't want it to explain, like just write the formula and put the values and got the answer. No, that wouldn't have been fun. I could have done that as well. Okay, you solve it using the formula. Method 2 is simple formula. But one day, what will happen is gate will ask some non-formula based question and you will not be able to solve it. So I'm preparing you for the worst. Okay, I could have simply wrote down the formula and that would have been enough. I would have finished there. But that is not the correct way to solve this question. Okay, it took me 20 minutes or 15 minutes to explain this question, but it's fine. It's good. You invest 15 minutes now and invest 2 minutes in the examination hall because you know all the concepts. Okay, so I hope you understood this concept very well. So answer will be 31 bits here. Okay, so yeah, this is the about the how memory lines are represented. Like you can go through this formula. Just I've derived in the questions itself. So that's it basically for today's lecture. I hope you enjoyed it. If you did enjoy, please go in the comments and tell you enjoyed the lecture number. You enjoyed this lecture, right? This lecture is 2A. Along with this lecture, you tell I enjoyed this lecture. I understood everything clearly. Okay, because you will see other teachers, but they will just directly write the formula and just directly tell the answer. Put the number of m equals to that and then find the x equation, x value, right? But we are not doing it. We're understanding everything conceptually here. I'm explaining you everything, just not mugging you up with the formulas, right? I can teach like that as well, but I don't want to do it. I want to teach you everything conceptually. So in the next lecture, we'll learn a bit more about instructions and a lot more things. Thank you for watching and I will see you in the next lecture. Hey everyone and welcome back to my channel and welcome back to another lecture of COA. So this will be the lecture 2B of COA. So previously we have learned about micro operations, byte and word addressable memories. So today we'll continue along with that. We did few questions, very good questions. If you haven't, please go through, revisit it again if you are not totally cleared by those questions. Today we learn few more concepts that will clear the concept of byte and word addressable more. Okay, and in some place, right, if you are stuck or if you are not able to understand that concept when I'm explaining it, it's okay. You note down that I'm not able to understand this or star mark it down. Later on as we move along the subject, right, you will that doubt, right, will be cleared automatically. Because as everything is interrelated, so sometimes something will come later on. So you learn about that. Okay, the reason that I had taken 1 instead of 0 here, the reason was this. So that is the main thing. Okay, so today we'll study byte and word addressable, and then we'll study about little and big endian byte ordering. So how are bytes arranged, how is data formatted, that also we'll learn. Then we'll understand instructions based on operand. So there are various types of instructions that are based on operands. How many address I will store, those we'll learn, and obviously we'll do few numericals on those. So let's start with this topic. I explained this previously as well, that abbreviation small b is represented for bits and capital B stands for byte and capital W stands for words. Okay, wherever you have seen b, small b, it means they are talking about bits. If it is kb, right, that means how many bits we have. Kilo means 10 raised to power 2 raised to power 10 into 2 cube bits, correct? If it is simple, k small b, this will be only 2 raised to power 10 bits, right? because this is already representing bits. This is bytes, and word is like whatever the conversion you do from word to byte, then you convert it into bits. That you can do. Okay. Additionally, the term double word and quad words are used. A double word contains twice as many bits as a word, so it's basically double of a word. Okay, and the term quad word is the 4 times of word. That's it. That's 4 times W. 4W. This is 4W, and this is 2W. Okay, not 2B, 2W. Okay. So like I explained this previously as well. Let's understand with few examples. So if your processor is a 8-bit processor, then if it is a byte addressable, the data it will store in 8 bits, chunks of 8 bits. In word addressable also it will store in chunks of 8 bits. But if your processor is 16-bit, I explained previously as well, the data in byte addressable, how it will store the data in groups of 8 bits. So here it will store in 8 bits only. 1 byte, then 1 byte, like this. But if your data is word addressable, how it will store the data? It stores in words, right? It stores in words. So one word is equals to how much? It is a 16-bit processor, so it will store 16 bits of data in one word. That means 2 bytes. 16 bits means 8 times 2, that is 2 bytes. So one word will store 2 bytes. So what is the bytes per word? Bytes per word here, it is 2. Okay, we solved the question as well in the previous lecture. Here as well, if it is a 32-bit processor, this will be same. This will not change. Okay, this will store the data as 8 bits, chunks of groups of 8 bits. Each cell will be of 8 bits. Here each cell will be of 32 bits, as it is a 32-bit processor. How many bytes? 4 bytes. So this will be 4 bytes. And same, like you can do the same thing here. 64-bit, it will be 64 bits, right? If it is n-bit processor, this will not change. This will be 8-bit only, and word addressable, it will store data in 8-bit format. It will always be a power of 2. It will always be a power of 2. Remember this, right? Always will be a power of 2. How many bytes will I have? I have derived a formula, right? It is log base 2 n. Okay, you will take the upper bound. This many number of bytes will have. Okay, so like an n-bit means it is the length of the instruction as well. So the length of instruction is defined by this 64-bit processor. So each instruction's length will be 64 bits. So this is also like there is a convention that we generally talk about the length of instruction like this. It is a 32-bit processor. That means each instruction will contain 32 bits of information, each instruction. So length of instruction. So let's take another example, another case study. So now if I have two different types of processors, 16-bit and 32-bit processor, and if both of them are byte addressable, so they will store data like this, right? Both of them are byte addressable. Okay, byte addressable. But my processor is 16-bit and here my processor is 32-bit. So what will be difference in this particular instruction? Move R100. So what does this mean? This means go to location 100, okay, and then move whatever the contents of 100 in the R1. But how many bits I will move? How many bits? This will specify how many bits I will move. This specifies how many bits. So computer always works in word, okay? It does not work in bit or byte. It is defined by this 16-bit or 32-bit. So how many bits I will move? So as it is a 16-bit processor, I will go to her location 100, and from starting 100 I will have 8 bits in this particular 100 location, right? And at 101 again I will have 8 bits. Total I have 16. So I will move total 16 bits from 101 to 102. So contents of 101 and 102 will be copied to R1. But in case of 32-bit processor, what will happen? I am working 32 bits, right? I have 32 bits. So I will go to this location 100 and I will copy 32 bits from this location to the end. So this is 8-bit, 8, 16, another 8, 24, another 8, 32. So total, how many bits I will copy? How many bytes I will copy? I will copy 4 bytes here. So these many things I will copy here. in 32-bit processor, and these many 2 bytes I will copy in 16-bit processor. So this is just to give you analogy and basic understanding what is the difference between a 16-bit and 32-bit processor. Now I am just giving you a hypothetical system. The way it works can be different. Okay, they can, like, it depends on the architecture and all those things. I'm just giving you an example that these type of things happen when there is difference between the bits of the processor. So obviously I will be able to process more data here. Okay, that is my advantage. So let's do one question along this. Okay, consider a 32-bit hypothetical processor which supports 128 megabyte of memory. So my total memory is 128 megabytes. Can I convert this? So what is 1 mega? 1 mega is almost 10 raised to power 6. This means 10 cube whole square. So this almost will be equals to 2 raised to power 10 whole square. So this will be 2 raised to power 20. So this actually is how much? This is 128. 128 is how much? It is 2 raised to power 7 into 2 raised to power 20, right? Mega is 20. This is how many? This is bytes. Remember, this is bytes. This is not bits. This is in bytes. Okay. So this part is done. Then what they're telling, if the system is redesigned to use word addressable memory. Previously it was using byte addressable memory. Okay. So now we are using word addressable memory. So, okay, how many address lines would be needed in the system? So you see, right, if I have this byte addressable memory, I have to, like, for each byte I have to store a location, right? But if it's a word addressable memory, how much how much will it support? It is a 32-bit hypothetical processor. If it's 32-bit, this means one word is 32 bits, or it is equals to 4 bytes. So in a single word, I will have 4 bytes of information. If it was byte addressable, I would have only 1 byte of information. So 1 byte is here, 1 byte is here, 1 byte is here, 1 byte is here. Okay, so this is total 4 bytes. 4 bytes of information. Okay. So I have 4 bytes. So how many of this, like this, right? It will be here again, one word here, and it will go on until what? Until some x value. I don't know. It will start from 0 to some x value. Okay. So it will go on like this. So previously I had a byte addressable memory. Okay. And this is basically the number of data lines, right? 32 bits means how many data lines I will require? How many data lines I will require? I will require total of each word is how much? 4 bytes, right? So I can use that formula, or I can directly write what is the total memory capacity. It is 128 megabits, right? Megabytes. It should be equals to what? Total number of words into what? Into words per byte per word. Byte per word. How much byte per word I have? So I will write here byte per word. So what is 128 megabits? I already have written it. It is 2 raised to power 7 into 2 raised to power 20. Okay, this should be equals to total words. Total words I can define it like a power of 2, where this m is the number of address lines. In the previous lecture only I defined this formula, right? Number of address lines into bytes per word. How many bytes is inside a word? It is 4 bytes. So this is also in bytes, right? Remember, you have to equate the units. Left and right hand side should be have same units. So what will be my m equals to? Like 2 raised to power m will be equals to 2 raised to power 25 here. Okay, so from here I can write 25. So how many address lines I will require? I will require 25 address lines. Okay, because how many different words I will have? Total words will be x will be equals to 2 raised to power 25 minus 1, because I am starting from 0. I am not starting from 1. That's why x will be equals total number of words will be 2 raised to power 25 minus 1. And in this, to define this words, right, location of the words, I need 25 bits. 25 bits total to define all these locations. And what is this byte per word? This byte per word is actually the data, number of data lines. This formula I have defined in the previous lecture as well. This, right? This is the number of data lines, because my processor is 32 bit. So what is 32 bit? 4 bytes, right? Exactly, that is written. So I will require 32 data lines to transfer data, because processor transfers data 32 bits at a time. It will simultaneously transfer 32 bits read or write operation. Okay, that's why I will require exactly 32 lines only. But for address lines, I just need to mention the locations, right? To mention this many numbers, I need 25 bits. Okay, 25 different combinations. So this was the topic about byte and word addressable. Okay, now let's understand how do we store the data inside the computer, inside the memory, because there can be two types. From this we will understand what types there can be. When a data element larger than 1 byte is stored in a memory, its arrangement in the memory can be one of the two conventions. So there is only a problem when we are storing data larger than 2 bytes. So because if it's a 1 byte data, right, if it's a 1 byte data, I know this standard convention that I will always start from the right hand side, right? So 1 2 3 4 5 6 7 and 8. So this is the bit position 0, and this is defined as the LSB, least significant bit. Why least significant bit? Because if this bit is 1, it will only say value 1, and if this bit is 0, it will only say value 0. And this is known as the MSB, most significant bit, because if this value is 1, right, what will be the actual value? If everything else is 0, this is 1, this will be 2 raised to power 8. Okay, 2 raised to power 8. So that's why, not 2 raised to power 8, sorry, 2 raised to power 7. So that's why this is the most significant bit, because this, if this bit is set, right, it provides a very high value. That's why most significant. So that is fine. Bit ordering, when I have a single byte, is not a big of issue. Okay, not a big of issue. But when I have 2 bytes, how will I define? Like, I can store this byte at the left hand side or the right hand side. So here we have an example. We can store using two conventions. We follow two conventions, little endian and big endian. It doesn't have any significance. Both methods achieve the same result. Choice depends on the system design. No specific significance. Basically, how we store the byte, that is defined by us, and like this little endian convention and big endian, it tells us how we will decode contents from memory. Okay, so here if I have a data, 32-bit data, right, this is a 32-bit data. How? Because if you know one thing, this is in hexadecimal, and in hexadecimal what happens is each digit, right, each digit actually talks about 4 bits. So if this is 0, so I will just once and for all I will just explain that thing only, because I know there will be a bit of doubt that if I have if I am operating a hexadecimal number system, then this will be going from 0 to F, right? If you know about 0 to F, so 0 is represented as 0 0 0, 1 is represented as 0 0 1, 2 will be represented as 0 0 1 0, and we'll go on. Okay, I will not write everything here, and 15 will be represented as 1 1 1 1. If you place, right, what will be this equals to? This will be actually in decimal format, this will be equals to 15, and in hexadecimal we denote it with F. Okay, that is our notation, hexadecimal. So each letter, right, represents 4 bits. So that's why I'm converting into bits. So this is a data. So there can be two ways to store this data, right? So this is a single byte, correct? So because this single letter is a 4 bits, so 4 plus 4 is 8 bit, and it is a single byte. So this 0A is a byte, 0B is a byte, 0C is a byte, 0D is a byte. Each of them are bytes. That's why I am storing byte by byte. But which ones to store first? Do I store this OD first and then OC? So how it will be stored in memory? So here, if the memory is something like this, right, let's assume it has to be byte addressable. If it is word addressable, then this problem will not arise. If it is byte addressable, then what will happen is, if I'm processing 32-bit integer, 32-bit data, right, how will CPU write it down? So there will be total 4 locations, right? Here, as it has mentioned, there will be total 4 locations, and each it is byte addressable, right? As it is byte addressable, memory will store it in chunks of byte. It will store it in chunks of byte. If it is storing in chunks of byte, what will happen? Will I store this byte first or this byte first? That is the only difference. Because when I will decode, this will be the least significant byte and this will be the most significant, because this is on the left hand side, right? That this was the original number. So there can be two methods. One is little endian, another one is big endian. Okay. So in little endian, what we do is the least significant byte is stored at the lowest address. Then I move to the next addresses, right? So that is the like convention of little endian. The least significant byte is stored at the smallest memory address. The bytes are stored in reverse order, with the most significant byte at the highest address. It is reverse, right? Because initially what we tend to see is this is at the this is at the rightmost side and this is at the leftmost side. But what is happening? I'm reversing it basically. OD is getting stored first, then OC, then OB, then OA. So that is what little endian does. It just reverses. So the least significant byte, this is a single byte, right? It stores it here, and the most significant byte is stored at the end, at the highest address. And big endian is just the opposite. Big endian stores the most significant byte at the smallest memory address and the least significant byte at the highest memory address. That's the difference. Okay, that's the only thing that we need to understand. With the help of a question, we can understand this concept better. But you can see I have written down few examples. You can go through this example and you can see where am I storing the values. So if I have a word named 4 byte word, right? It is 12 AB 34 CD. How will I store? If it is little endian, right? CD will be stored in location 100. Let's assume that I am storing it starting from location 100. CD will be first stored in location 100. Then 34 will be stored in location 1001. And then AB will be stored in location 1002. And 12 will be stored in location 1003. Okay. So the LSB is stored in the lowest address. It is stored first. And the MSB is stored last. It is stored at the highest address. That is what little endian follows. Big endian, just the opposite. LSB is stored at the last and MSB is stored at the first. You can see the difference. Okay, let's do a basic question, and through this we'll understand this concept. Okay, so if the numerical value of a 2 byte unsigned integer with little endian computer is 255 more than on a big endian computer, which of the following choices represents the unsigned integer on a little endian computer? Okay, so it is telling me on little endian, unsigned meaning it is only positive. It doesn't have any sign associated with it. It is 2 byte data. Okay, and it is telling me that the 2 byte data on little endian computer is 255 more than the big endian representation. So what does it mean basically? So let's take an example. If I had X, Y, W, Z. Okay, each of them are bytes. So this is the actual number. Let's assume this is the actual number. Which of the following choices represent the unsigned integer on a little endian computer? Or this is the unsigned integer on little endian. Okay. So in little, let me assume this is the actual number. This is the actual number. Sorry. Okay. In little endian, how will I store the data? So this will be stored first, then this, right? Sorry. This byte will be stored, then this byte, then this byte, then this byte. So word will be stored like this: Z, W, Y, X. It will just be reversed. In big endian, the word will be stored as it is. This is the little endian, and this is the big endian. Okay, so this will be X, Y, W, Z only. And if I'm subtracting this, right, little endian minus big endian, they're telling me I'm getting 255. Okay, this is in decimal, right? This is in decimal. And remember this, all these, right? All these are in hexadecimal. Okay, all these are in hexadecimal. So I need to form this equation basically. So obviously I cannot take any numbers, everything is unknown. So what I will do is, okay, sorry, it was 2 byte data, not 3 byte data. Sorry, 4 byte data. Okay, I'm sorry. I can only choose X, Y, right? That should be enough. So if I do X, YX minus XY, I'm getting 255 in decimal. Okay. So obviously I'll not be able to like think of anything, any number out of the wind. I'll just take help from the examples. Okay, so if I take let's take this example. Let's take this example first. 6655. Okay, 6655. So it is telling me which of the following choices represent the unsigned integer on little endian computer. So whatever written, all these are the representation in little endian. Okay, so I know little endian minus big endian is 245. So I'll write that down. So this is little endian, right? So it is 0655. This is 0x6665, I think. Yeah, 65. So in big endian, how it will be stored? Just the reverse, right? This is 1 byte. This is 1 byte, right? 1 byte. So this byte is in little endian is the LSB. Okay, so this will be in big endian, it will be at the last, correct? So it will be 0x65. This is 1 byte and this is 1 byte. This will be 66. This is equals to 255 in decimal actually. So I want to convert everything in decimal. Okay, we have to convert everything into decimal. Or what we can do is we can convert everything into binary as well. Whichever, like you can do a decimal to binary. So a prerequisite is I will obviously post the video number systems as well. So in number systems I will talk about the conversions and all those things. I hope you know basic conversion of number systems. So I can convert this into simple binary. So how is 6 represented? It is 110, right? So it will be 0110, then 0110, then 0110, then 0101. Okay, and I am subtracting it with this num value, right? This is 0x. Like I can do the simple subtraction as well. We don't need to do all this. So what will this be? This will be simply 0x101. Okay, 0x101. So what is this in like binary? I can convert this into binary. So what will be this in binary? So this will be 0. Okay, this will be also 0, right? This will be also 0. Yeah, this will be 0000, and or I can directly convert it. This will be in decimal 16, 1 into 16 raised to power 0 plus 1 into 16 raised to power 2. So 16 raised to power 2, 16 square is 254 plus 1 is 255. So LHS is equals to RHS. So option A is satisfying. Option A is correct. This number conversion you have to do. That is the homework for you. I will obviously post a video in part 2. I think number conversion will be there, but or in some other video. I will link that video in the comments below or something. Number conversion you don't know, and in like I think in digital electronics also you have been taught number conversion. So this was for the option A. Okay. Now let's check the option B. So in option B, what I had? In option B, I had this, right? 0001. So I have to check this equation. 0x0001. Again, I will swap the bytes. This is 1 byte, right? This is 1 byte. This is 1 byte. I just swap the bytes. In little endian and big endian, the bytes are just MSB will be at the start for big endian, and for little endian MSB will be at the last. So this will be 0x0100. So equals to, it should be equals to 255 decimal. Is it getting equated like that? Let's convert this into simple decimal. So this, right, in decimal this is simple 16, not even 16, this is simply 1, and in decimal this is 16 whole square. So I'm subtracting 256, right, from this. This is minus 255, which is not possible. Minus 255 is not possible. It is signed integer. I will get unsigned integer, right? It will not have any sign. So option B is wrong. So let's choose option C. Okay. Option C, what I had? Option C, I had 0x43. 0x4243. So it will be 0x4243. Okay. So it is 0x4243, right? Yeah. Big endian minus little endian. 0x. This was a MSQ question. So yeah, obviously you have to check all the options. You cannot simply just check one and that is it. No, you cannot do that. 4342 equals to, it should be equals to 255 in decimal. So again, if I want to subtract this, like I can convert this into simple decimal, then I will do it, because I have forgotten myself the hex subtraction. Okay, so this will be 4 times 16 raised to power 3 plus 2 times 16 raised to power square plus 4 times 16 raised to power 1 plus 3 times 16 raised to power 0, and everything will be same here only. Okay, this will be what? This will be 4 times into 3 times 16 square, 3 times 16 square, and this will be 4 times 16 raised to power 1. This will be 2 times 16 raised to power 0. And now if I subtract this, right, so what I will get this 1 times 16 raised to power 0 plus this will be 0 only, plus this will not be plus, actually this will be minus 1 times 16 whole square, and this is 0 only. Okay, again I'm getting a negative number. Again I'm getting negative. So what I'm getting, again I'm getting minus 255, which is wrong. It should be a positive number, correct? So let me check the last and final option, option D. So in option D, what we have, in option D, number is 0100. So it is 0100. So in little endian it is 0x 0100. So in big endian, what it will be? It will just be like, this is 1 byte, right? This is 1 byte. So this will be 0x 0001. This will be equals to, just hold on, this will be equals to, this should be have been equals to 255 decimal, right? So this is rather simple, right? This is what, this is 1 into 16 square minus 1 into 16 raised to power 0. So this is actually equals to 255 in decimal. Okay, so it is satisfying. My LHS is equals to RHS. So option D also is correct. So these two numbers is possible in the computer, right? If it's unsigned integer, these two values is a possible. There can be many more as well. It depends. So in this particular option, these two values will be possible according to the given question. So little endian and big endian is nothing, just the byte ordering. You don't have to take too much stress. Whatever I'm teaching, that much stress you have to do. Especially I'm talking to those students who are preparing for GATE EC. Don't have to take too much stress. If you are preparing for placement, yes, you can go more in depth. But for GATE EC, COA, this much is more than sufficient. Okay, now let's come to this one, the ISA, instruction set architecture, right? So now we have learned about like how we are storing the data in our memory. Now we learn about few things about instructions, because we haven't talked about instruction length. So now we will discuss about that. What is the length of the instruction? So generally, the instructions can be classified based on the operands. Okay, there can be many other classifications, but we will today study types of instructions based on operands. So what does it mean? So here, instruction can be of this format: opcode, address 1, address 2, address 3. Now what does each of these address means? It means opcode is there. Opcode tells us what? Opcode tells us what operation it needs to perform, right? I have explained this previously as well, right? Opcode will tell us if I need to do addition, subtraction, division, whatever instructions there are, whatever definitions you have, whatever instructions you have made. That is what opcode tells us. But obviously, perform operations on what? Where are the operands? Where are the operands, sir? CPU will ask, where are your operands? And you will say, you will give him this operands. Here, take your operands. This is the address of the first operand. This is the address of the second operand. And I am instructing you, store the result in address tree. After performing the operation, store the result in address tree. So you throw these things. You throw the address to the CPU. You tell him, do all this. Okay. So your CPU then understands, okay, I will take the first operand from address 1. There is a memory. There is a memory, okay. And in memory, I can have many things. So this is address 1. This is address 2. Okay. So this is like any value x and y, any value is here. So this address 1 tells that go to this address and fetch the contents of address 1, that is x. Okay, This is the operand 1 and this is the operand 2, and store the result in some other place in memory in address 3. Okay, so this is a basic structure of a 3 address instruction. There can be variants as well. I am not going into too much depth. I'm just giving you a overview right now. So this is a 3 address instruction, and what does 3 address instruction do? It can support a maximum up to 3 addresses. Why am I telling maximum? So if it is a 3 address instruction, right? If the CPU supports 3 address instruction, it will automatically support 2 address and 1 address and 0 address instruction. We'll like learn that right now only. But if a CPU supports 3 address instruction, it means it automatically supports the lower one as well. Obviously, if you are supporting 3 address, you can support 2 address. It is lower value, right? You can support that. So it automatically supports 2, 1 and 0 address instruction. Okay. Now, will you use it or you will not use it? That is up to you. And how we will use it, I will teach you. Just have a bit of patience. I will teach you how we'll use 2 address instruction on 3 address instruction. I will teach you. Just have a bit of patience. Just listen to me carefully. Okay. Please give full concentration right now, because this topic is very, very important. Okay. This question can be asked in examination. So 3 address instruction means I have 3 addresses and there is a 1 opcode. So these first 2 addresses are generally in the question they will tell you what are these 3 addresses, they will define you. But if they don't define you, then you know the first 2 address is for the operands from which you have to fetch the operands, and then in the third address you have to store the result. Now, what is 2 address instruction? What is 2 address instruction? It supports a maximum of 2 addresses. Just like 3 address, it supports a maximum of 2 addresses. But here, what we do, we use one operand is used both as the source and the destination. So in the question, they will specify what they are talking about, which address is source and which address is destination. They will specify it. Okay. So, but in 2 address instruction, one operand is used as a source and a destination. Okay. So both are source and destination. So let's say address 1 is used both as source and destination. So what I will do, I will take the contents. Okay, I will just copy this thing. I will take the contents from address 1. I will take the contents from address 2. I'm performing some add operation. Then again I will come back here and store the result in address 1 itself. So address 1 is both source, acting as a source and as a destination. So one of the address will act as both source and destination. That is the format of 2 address instruction. Now, which address is source and destination? They will mention in the question. You don't have to worry about that. They will mention in the question. So this, right, it supports a maximum. So in a 2 address instruction, it can also support. Now this is a very, very important point, just as the previous point only. Support 1 address or 0 address instructions. 0 address instructions. Okay. So that is what it can support. Now, what about a single address? Then what will single address then? So single address. Now, important point is it cannot. Also another important point. It cannot support 3. It is not possible. It is not possible for it to support 3 address instruction. Okay. Not possible. Why it is not possible? Because we don't have enough space. We don't have enough length. Instruction length is of only this much, right? We don't have enough space to add another third address. So we cannot do it. Now, in a single address instruction, it supports only a 1 address. And what will be this 1 address? So generally, this is just I'm giving you a hypothetical situation. What we do is it only supports 1 address. So the other operand, right? One operand is taken from the address 1. The other operand is taken from the accumulator. It can be taken from some other place as well, taken from some register, taken from some stack, taken from other place. Okay, it depends on the architecture. But generally, one operand is taken from the address and the other operand is taken from the accumulator. Just architecture, just a hypothetical system. That other operand, right, can be something else as well. You don't have to fix your mind. Okay, so in one address, we implicitly use we know from where to take the other operand, and then again we store this store the result in this particular address, or we can store it somewhere else. Okay, that will be defined in the question. You don't have to worry, that will be defined in the question. Okay, so it only supports one address. So obviously, if it supports one address, right, it cannot support two address or three address. Two and three address it cannot support, but obviously it can support zero address. Okay, just like this can support 1 and 0 address. It can support 0 address. And what is 0 address? That will, like here I've given an example, like add m. If it is add m accumulator, that means what it will do, it will add accumulator and memory and then store the result in memory. That's it. Okay, now what is 0 address instruction? If I don't have any operands, right? If the instruction is 0, like I don't have any operands, then I will use 0 address instructions. What it means, operands are implicitly from the stack, or what it can be like increment as well. If there is, like this is add means pops two values from the stack and then adds and pushes the results. So this is used in stack based architecture. There can be other uses as well, I will explain. So I have this stack, right, and at the top of the stack I have this x and y value. Okay, what I am doing, if I write add in a 0 address instruction mode, what it will do, it will pop two values from the top of the stack, then it will perform x plus y, and then again it will push the value. So stack now will contain x plus y. Okay, the top of the stack will contain x plus y. That is what it will do, right? There can be other use cases, like if I say increment inc ac. Okay, simply if I write inc ac, or if I write inc a, like I have defined my own hypothetical system where this is a instruction. What does it mean? It basically does what? It basically increments the accumulator by 1. Okay, so here did I need any address? No, I did not require any address. So 0 address instructions are also possible. Okay, sometimes this can be also instruction, right? This. Okay, yeah, INCA and other things, like a similar example to this. Okay, I hope you understood the difference. Now this 0 address instruction cannot support anything else, right? It cannot support 3, 2, 1. Not possible, because my opcode, I have only opcode, I don't have any addresses, I have only opcode. So I hope you understood the difference between 3 address, 2 address and 1 address and 0 address instruction. Now we will do questions, and from here your doubts will be cleared more. Let's do this question first. A hypothetical processor supports 2 address instructions only. It has 32-bit instruction and 12-bit addresses. Then minimum and maximum number of 2 address instructions that can be formulated respectively. They're talking minimum and maximum. So a hypothetical processor supports 2 address instructions only. So it supports 2 address instructions. Okay. So if it supports 2 address instructions, that means it can support 1 address and 0 address as well. Okay. But we are not going into that. What are they asking? They are asking then the minimum and maximum number of 2 address instructions it can be formulated. So that is what it is asking. It is telling it has 32-bit instruction and 12-bit address. So each instruction is 32-bit long. So this 32-bit, right, is the CPU instruction length. Okay, so I have total of 32 bits. So let me just mark this down. This is a 2 address instruction, right? So first will be my opcode, then will be my address 1, then will be my address 2. Now as it is a 2 address instruction, they have told me that this whole thing, this total, right, total instruction length is 32 bits. And also they have mentioned that each address is 12-bit long. So this is 12-bit, this is 12-bit. So what is the length that I have left for opcode? 12 plus 12, 24. I have total 8 bits length. So opcode length by adding this will come out to be 8 bit, because total instruction length is 32 bits. I have only 8 bits left. Now what are they asking is how many then minimum and maximum number of to address instructions that can be formed. Now the main thing is this, right? This is only for the addresses. Okay, this is only telling me the location of the operands. What does it tell me? It tells me how many instructions I can have, correct? If I have opcode length of 1, that means it is 1 bit long. It can be either 0 or 1. So at max I can define 2 instructions. It is 2 raised to the power 0. Not sorry, 2 raised to the power 1. It is 2 raised to the power 1 because I have 1 bit, right? Now if I have 2 bits, like this can be either 0 1, this can be 0 1. How many instructions I can have? If the opcode length is 2 bits, I can have 2 raised to the power 2. 4 combinations, right? 0 0 0 1 1 0 1 1. 4 combinations. Now if I have 8 bits, 1 2 3 4 5 6 7 8. So each of them can have 0 1 0 1 0 1 and so on, right? So on. So how many different instructions I can have? Maximum instructions. Maximum instructions is 2 raised to the power number of bits 8. That is 256. Okay. Sorry, 2 raised to the power 8 is, yeah, it is 256 only. Yeah, 256. Okay. So this many number of maximum instructions I can have. Now, so 256 is maximum, so obviously option D is correct. The maximum is 256. But what about minimum? Minimum, you have to at least define 1 instruction. So what we do is you can make all the other, like you have to at least for design and architecture, right? You have to give at least 1 instruction, right? That is the minimum, because you can like make all the other bits redundant. You can just only use 1 bit. That is up to you. That is up to your design. Minimum is up to your design, right? Maximum is 256, 2 raised to the power 8. Minimum, at minimum you have to choose 1 instruction for two address instruction, right? Minimum you have to choose at least 1. If you choose 0, then that means it is not even a architecture. What is it? It is nothing. 0 means null, right? So no, minimum you have to choose 1, and maximum is already been proven here. That is 256. I could have directly told you that you just simply need to write what maximum number is. I could have directly told you the formula. What is the formula? Maximum number of instruction. This formula will be what? It will be equals to 2 raised to the power length of opcode in bit. But I'm explaining, right? I'm explaining you everything. That's why it is taking me so much time to do all these questions. I'm explaining you. So this is the formula. Don't need to remember. Just conceptually understand. If I have different combinations, how many different instructions I can have. Just that much you need to understand. Okay. And let's do this, right? A hypothetical processor supports 32 one address instructions only. So a hypothetical system supports 32 one address instruction. Okay, fine. So if I have like one address instruction is something like this. This is opcode and this is address 1. And I support 32 of this. 32 of these instructions. If address length is 3 bits, then length of the instruction is, address length is 3 bits. So this length, right, they have told me is 3 bits. What will be the length of the instructions of this whole instruction? They are asking me length of this whole instruction. Now I support 32 different opcodes. I support 32 different opcodes. I support 32 different one address instruction. So how many minimum number of bits required to support these many 32 instructions? How many bits I will require? Okay, it's simple, right? 32, I need to support 32 combination. It should be some power of 2 raised to power n. So from here n will be simple 5, right? Simple 5, or what you could have done is simply done the log base 2 of 32 and you would have got the answer n as equals to 5. Okay, so I need 5 bits here. This should be 5 bits. So what should be that like minimum? At least this has to be the length, right? At minimum, this has to be length. I cannot choose a 4-bit opcode length. If I choose 4-bit opcode length, I can only define 16 instructions. I cannot define 32 instructions at minimum. So hence instruction length, right? Length of instruction length will be at least 8 bits. At least it has to be 8 bits. It can be higher than that, but at least it needs to be 8 bits. So 8 will be your answer. This will be your answer. Okay. So let's now move on to next question. So we have a lot of questions. We'll solve mainly questions in this lecture. So let's do this question now. A processor has 40 distinct instructions, 24 general purpose register. So I have 40 distinct instructions. Okay. So if I have 40 distinct instructions, what will be the opcode length? Now I will do directly. Now I will not do slowly. Okay. I have 40 different instructions. So 40 will be equals to 2 raised to power n. So I have to choose n will be equals to log base to upper bound of log base to 40. So at least how many bits I need to define 40 instructions? I will require at least 6 bits, right? At least 6 bits. N will be equals 6 because 6 can define with the help of 6 bits I will be able to define 64 instructions, but it's okay, I'm only using 40 instructions, that is fine. But can I use 5 bits to define 40 instructions? No. With 5 bits at most I can define only 32 instructions. I cannot define 40 instructions, so I'm coming short of 8 instructions, so I will not use 5 bits, I will use 6 bits. And I have 24 general purpose register. So I have registers from R0 to R23. Total of this 24 general purpose register. A 32-bit instruction word has an opcode, 2 register operand and an immediate operand. Okay, so it's a 3 address instruction like thing, 2 register operand and an immediate operand. It's just a hypothetical system. Okay, it's just a hypothetical system where, so sometimes they will define you how the instruction is defined. So first I have a opcode, then I have two address 1 and address 2. Then I have what? Then I have an immediate operand. It can be anything. Immediate operand meaning that it is exact, like if I have written here 2, so this 2 will be not address, this is a operand, directly operand, right? This is not address. Okay, so it's just a hypothetical system. They have defined the architecture like this. It doesn't matter for me. I will write down, okay, it is an immediate operand. Okay, so what are they asking? The number of bits available for the immediate operand field will be how many bits? What is the length of this operand, immediate operand field, right? Okay, what is the length? So if I have 24 general purpose registers, right, how many bits will I need to define these registers? How many bits will I need? I have 24. How many bits I will need? So 24 will be equals to 2 raised to power some value n. Correct? Not m, this time m. Because I need to, like, there will be 24 different addresses for 24 registers. I have 24 addresses for 24 registers. So my m will be equals to what? Again, I will apply the same formula, that is upper bound of log base to 24. So how many bits I will require? I will require 5 bits. To define 24 different addresses, I will require 5 bits. This will be again 5. So each address, like opcode length, I have already found out it is 6. Each address is 5. And they have told me that the total instruction length, it is a 32-bit instruction word. So total is 32 and opcode length is 6 and my address length is 5. I have 2 address fields, 5 plus 5. Then I need to find out the length of this immediate operand x. So this x will be equals to what? It will be 16 minus 32, that is 16. So my immediate operand field length will be simply 16. Okay, it will simply be 16. So 16 will be your answer. So that's how simple this question is. So let's now move on to next question. These type of questions can come and you should be able to solve these type of questions. So these are the easy questions. There are a level that is up from this question that we will study just in a bit, don't worry. But these are the type of questions that you need to learn. Now consider a processor with 64 registers and an instruction set of size 12. So I have 64 registers. So how many bits I will require to define the addresses of these 64 registers? Again, now I will, as I read along the question, I will directly write down the length of the address, because I know what type of questions they are asking me. So it will be 2 raised to power m. So m will be again log 2 of 64, that is 6, right? I will require 6 bytes. It's not 6 bytes, 6 bits. The instruction size is 12. They have not mentioned it is as bits, but it is 12, right? So length of instruction, each instruction is 12. Each instruction has 5 distinct fields, namely the instruction set size is 12. So this is not the whole instruction, like this is not the instruction size of the whole CPU. This is just the instruction set size. In instruction set size meaning I have 12. Sorry, this I have interpreted it wrong. This is the number of instructions that I support. Number of instructions. I write this here. This means basically number of instructions I support. This is equals to simply 12. So number of instructions that I support is 12. Okay. So how many bits will I require to support this many number of instructions? Again, I will use the same thing, that is 12 is equals to 2 raised to power n. So I will require n equals to simply 4, right? Upper bound of log base 12 is 4. So slowly I will have like they have defined how each instruction is present here. I have 5 distinct fields. First is opcode. First I have opcode. This is my opcode. Next I have 2 source register identifier and a destination register identifier. So I have 3. This is a 3 address instruction, right? Address 1, address 2, address 3. Then next, what do I have? A 12-bit immediate value. So it is required. It is their architecture. They can do anything with their architecture. So I have a 12-bit immediate value that is 12 bits long. Okay, so each address, how much long is each address? I have already calculated it. It is 6 bits long, right? So here it will be 6 bit and it will simply be copied everywhere. 3 addresses I have, so each address has to be defined by 6 bit because I have to define 6 locations. And what is the length of the opcode? Opcode length I have already calculated it. It is 4, right? It has to be 4. Minimum length is 4. Each instruction must be stored in memory in byte aligned fashion. So we are storing each instruction in byte aligned fashion. So what do I mean by byte aligned fashion? So now remember, right? Byte and word addressable. So instructions in the memory are stored in byte aligned fashion. So this will be 1 bit. This will be not 1 bit, sorry, 1 byte. And if this is 100, right? This will be 101. This will be 102, like this. Okay, this is 1 byte. If it was word addressable, then it totally depends on the size of the instruction of the CPU. They will mention it. Now, if a program has 100 instructions, the amount of memory in bytes consumed by the program tasks. The program has 100 instructions. So how many total bits it will have? Total bits of the program. This will be equals to 100 as it has 100 instructions. And what is the length of each instruction? The length of each instruction is 4 plus 6 plus 6 plus 6 plus 12. So this is 18 plus 4, 22 plus 12, that is 34. So each instruction is 34 bits long. Okay. So yeah, 18 plus 2, 12, 34. So each instruction is 34 bits long. Okay. Each instruction is 34 bits long. So 34. So what is this basically? This is the number of instruction and this is the length of each instruction in bits. Okay, but what I actually require in bytes, because each instruction, like they are storing, it is a byte addressable memory, they are storing it in total bytes. So I need to find out the total number of bytes, how many bytes is it consuming. I will just simply add with it, right? Because with each increment I'm adding 1 byte. So this comes out to be 34100. So this is the total bits. But if I want to convert it into bytes, what will be total bytes? I just need to divide it by 3400 divided by 8, that is 2 raised to power 3, right? So here I have, this is actually this is 417 into 2 into 24 into 25. Yeah, this will be 17 into 25. So what is 17 into 25? I will just quickly calculate that. What will be 17 into 25? So it will be 425, and you will say total I will require 425 bytes. So it will take 425 bytes, right, in the storage, and your answer will be wrong. This will not be your answer. Why your answer will be wrong? Because you didn't take into factor what I explained previously. What was the thing? I explained previously that you are storing it in bytes, right? So it's not like that I can store 34 bits like this. How will I store 34 bits? What you're telling me that in each instruction contains 34 bits, right? How you will store it? So you are telling me that first, how many bytes is this? This is 4 bytes plus 2 bits, right? So what you're telling me that in the first 4 locations you are storing the instruction, okay, of 4 bytes. Then in the next location, what you are doing, although it is 1 byte, what you will do, you will store the first 2 instructions, like the last 2 bits of the previous instruction, and after this 2 bits, right, you will start from here and you will write the next instruction, the MSB of the next instruction. Can we do it? No, we cannot break it down. We cannot break it down. What is the better alternative? The better alternative is, okay, it's okay, you keep this space as it is, you leave this space, okay? It is a byte addressable memory, you leave this space. We have to leave this space, we cannot use this. So what I will do, I will have a memory, and this memory actually has a 34 bits. Each instruction has 34 bits. So I will store this first bit here, how many bits I have left. So after this, right, how many bits I will have left? If I subtract 8, I will have 26. Again, I will store the other byte here. How many bits I will have left? It will be 18. Again, I will store the other byte. How many bits I will have left? It will be 10. Again, I will store the last bit. How many bits I will have here? This is byte. How many bits I will have left? 2. So I will store the 2 bits here only. Okay. Store the first 2 bits here, and I will keep this empty. It's not like I can start the next instruction from here. CPU won't be able to understand. The next instruction will be started from here. Okay. This is the starting address of next instruction. It is not word addressable, it is byte addressable. We cannot store data like this, like fragmented. We cannot do it. It will cause error. So each instruction, right? Each instruction actually takes 5 bytes. I will have to assign, minimum I have to assign 5 bytes. I cannot assign 4 bytes. I cannot assign like this, a fraction number. If I convert this into bytes, what will be this? This will be 34 by 8. What is 34 by 8? It is 4.25. Not possible. Okay, not possible. It should be a integer. It should always be integer. So I will take the upper bound of this, that is 5. I will choose 5. Okay, I have to assign 5 bytes. It's okay, we can waste space, but our CPU needs to understand the instruction. That is the most important. This is a messy way to add the next instruction in the same byte itself, right? We will not do. So we have to assign 5 bytes, not 4.25. That is wrong. So now I will use the same formula again. What I will use? Total bytes, right? Total bytes will be number of instructions into what? Into bytes per instruction. So how many number of instructions I have? They have given in the question 100. And what is the bytes per instruction? 5. I need to minimum assign 5 bytes for a single instruction. So it will be total 500 bytes. So it will consume, the program will consume total of 500 bytes in the memory. So answer will be 500. This will be the answer of this particular question. So this is a very, very good question. Don't get fooled by that particular thing. So what I'll do, I will give this question as the homework, and in the next lecture I will solve this question and this as well, this question as well. Few questions you write it out by yourself, and in the next lecture we will solve all these questions. Okay, this is one question and this is also another question, because we will study just a next topic, and in the next lecture we will solve all these questions. So the next topic is about variable length instruction set. Just hold on a second, I will drink a bit of water. Now instruction length can be classified in two ways. One is fixed length instruction, another one is variable length instruction. So whatever we will study this fixed length instruction. We will study this. We will study this. Okay. So what is the difference in this? What is the difference? So in fixed length instruction, right? If they have mentioned it is a 16-bit processor, so length of each instruction will be fixed. Length of each instructions will be fixed. Okay, just hold on. I will do one thing. Yeah, this is fine. Yeah, length of each instruction is fixed. Let me just check. Yeah, everything is recorded. But what will be difference is that the opcode length can vary. Opcode length can vary, and how it will vary I will explain that. Okay, with example. In variable length instruction, the instruction has flexibility. It can change length of instruction can vary. Okay, length of instruction can vary, it can change. So it depends from from architecture. So we will not discuss, this is out of syllabus. Okay, we will not discuss about this. Okay, we will only discuss about the fixed length instruction. And in fixed length instruction, the opcode length can vary. How it will vary, I will talk about that. So then inside fixed length instruction there can be two classifications. This is inside fixed length instruction, there can be two classifications. This is within fixed length instruction, right? So one is either your opcode can vary or it cannot vary. So that, like I have told, it can vary, can be variable, it can be fixed as well. Okay, whatever we have studied is fixed. Right now whatever we have studied up until now is fixed opcode. Okay, because opcode was fixed. Now I will show you how opcode can vary. So the opcode portion of the instruction has a fixed number of bits. So like instruction, right, it is comprising of many things: opcode, address 1, address 2, immediate operand bits, all those things. So opcode portion is fixed for a fixed length opcode, and opcode portion will be variable for a variable length opcode. So these are the examples of variable fixed length opcode and variable length opcode. What happens is, for a fixed length opcode, right, it is very simple to decode. If I have written 000, okay, then I exactly know what does 000 stands to, like what operation I need to perform. If it is fixed opcode, but if it is variable opcode, right, first I have to understand what is the length of my opcode. Is it 1 bit? Is it 2 bit? Or is it 3 bit? Then I will understand that, okay, if it is 1 bit, then first bit is 0, then for that particular bit, like for that 1 bit of opcode, what is the instruction? So decoding becomes very, very difficult. That's why it is written fixed length instruction, it is easy to decode, and variable length instruction, it is complex to decode. Okay, it may waste memory, just as we saw, right? I had 34 bit, okay, of instruction length, but I cannot simply store it in 34 bits. I have to store it in byte addressable. So there I was wasting 6 bit. 6 bit was simply getting wasted, okay, for using 5 bytes. So that's why memory wastage here. There is no memory wastage. Wherever we require less memory wastage, we will use this type of things. Okay, this is out of syllabus, this is inside syllabus. So we'll discuss now with example, with a question. I will discuss what do I mean by fixed and variable length opcode. Okay, so we'll do 2 questions and there we'll understand. A hypothetical processor supports 2 address instructions and 1 address instruction. If it supports 2 address, automatically it supports 0 and like 2, 1 and 0. But they have told me that it supports both 2 address and 1 address instructions. So how it will support, we'll see. We'll see that. It has 32-bit instruction and 12-bit addresses. So the instruction length. So first of all, let me draw the 2 address instruction. So this will be opcode. This will be address 1. This will be address 2. Okay, so in opcode, like it is telling me that it is supporting this 2 address instruction, and the instruction bit is 232 bit. So it is fixed. This is fixed, right? This will not change, because whatever we'll study fixed instruction only. Opcode can be variable. How it will be variable, I'll show you. So it is 32 bit. And it supports 12, each address is of 12 bits. So this is 12 and this is 12. So if it is a 1 bit address, right? 1 address instruction, it will be opcode, then it will be address 1. So this is like now this will be 32 bits. Okay. So here what I observe, this is opcode 1, this is opcode 2, and this is opcode 1. The lengths of these opcodes, right, will be different. Here the length of the opcode is how much? It will be 32 minus 24, that is 8 bits. Here what is the length? This is 12 bits, right? This is 12 bits. So this will be 32 minus 12, that is 20 bits. So opcode length is variable. How we'll understand that whether it is a 1 address instruction or 2 address instruction, that we'll see. Now what are they telling? If there are 254 2 address instructions, so there are a total of 254 2 address instructions. So there are a total of 254 2 address instructions. So this is the 2 address instruction, right? How many maximum number of 2 address instruction I can have? Maximum number of 2 address instructions. It will be 2 raised to power opcode bits of opcode length 1, right? This 2 raised to power 8 bit. For 2 address instruction I have 8 bits. 2 raised to power 8 is 256. So they're telling me I'm only using 254 2 address instructions. I'm not using all 256. So I have left 2 empty. So what is the use case of that 2 empty? That we'll understand. So unused 2 address instructions. How many unused 2 address instructions I have? It will be this subtracted by the used 2 address instruction. I am only using 254. Okay, so it will be 254. So this will be 2. Okay, this is my unused 2 address instruction. So I have 2 left. Now what are they asking? They are asking then the minimum and maximum number of 1 address instruction that can be formulated respectively are. What are the minimum and maximum number of 1 address instructions? So to understand this thing, please concentrate with me right now. Let's take example. Please concentrate with me right now, and let's take a smaller example. This is a bigger example. I will take a smaller example. I have 6-bit instructions. Okay, the length of the instruction is 6-bit. So I have 6-bit instructions, and I have 2-bit addresses, and 3 2-address instructions are supported. So if I have this small example, this is my opcode, this is my address 1, this is my address 2. Okay, this is a 2-address instruction. Now they're telling me the total length of this is 6 bits, and each address length is 2 bits. Each address length is 2 bits. This is 2 bit, this is 2 bits. Okay, so what will be the opcode length for 2-address instruction? It will be 2 bits. And they're telling me I'm only using 3 2-address instructions. Instructions. So how many different instructions I can maximum support? Maximum 2-address instructions supported. It is 2 raised to power, the length of the opcode for 2-address instruction, it is 2, right? 2 raised to power 2, it will be 4. I can support 4 different combinations. Okay, add, divide, subtract, multiplication, because my opcode length is 2 bits, right? It can be 0 1 0 1. So now what about if I'm using like 1-bit instruction? If I'm using 1-bit instruction, how will my opcode? So opcode will be like this, right? So address length is 2 bits, and this overall instruction length is 6 bits, right? So this length will be simply 4 bit. So for single address, 1-address instruction, you are getting opcode length to be 4 bits. Now you will say maximum number of supported one address instruction will be equals to 2 raised to power 4, and you will be absolutely wrong, because yes, it is correct, but if it only supported 1-address instruction, because we're already supporting 2-address instruction, I cannot simply write this. Okay, I cannot simply write this. So what will I write? What will I do here? So I have already used, like they are telling me, I have already used 3 2-address instructions. So out of 4, I have used 3. So 1 is left. Okay. So let me take example. So this many combinations are there, right? 0 0 0 1 1 0 1 1. 4 combinations. So let me take these 3 and assign. Okay, these 3 are assigned. So this is left, right? So this will help me to identify that this is a 1-address instruction, because all these are used. So this will help me to identify that this is a 1-address instruction. Okay, so let me take an example. The example is this, that 1 1 is already gone, right? 1 1 is already gone. So how will be the opcode be? So if I've written like this, that it is like for 2-address, let's take a 2-address instruction, right? Let me take a 2-address instruction, 0 0 1 0 1 1. Okay, this is 6-bit. This is the instruction. This is the instruction. Okay, now there can be 2 cases. I have to check whether this is a 1-address instruction or it is a 2-address instruction. Okay, so how will I check it? So first I will check the first 2 bits. Okay, I'll check the first 2 bits, because I know for 2-address instruction I just need to check the first 2 bits. So first I will check the first 2 bits. I observe 0 0. 0 0 actually has a definition. 0 0 has been assigned, so it will be a 2-address instruction. Okay, it will be 2 address instruction. Now if I will check the first 2 bits. According to the first 2 bits, I see it is already been assigned as a 2 address instruction. So I will go with 2 address. So first I will check for the 2 address instruction. Okay, first I will check for 2 address instruction. So first check for the lowest opcode length. What is the lowest opcode length? Lowest opcode length in our case, right? 2 address instruction has only 2 bits. So I will check the first 2 bits. 0 0 has already been assigned. Let me take another example. Let me take the same example. Okay, but this time this is here, right? Okay. This time I will choose 1 1. So I check the first 2 bits. I see it is 1 1. And 1 1 I have already defined that it is left, right? It is not assigned, it is left as it is. So 1 1 I can assign for 1 address instruction. So this actually, by seeing this 1 1, I identify, my CPU understand, okay, this is a 1 address instruction. So I will not go here, I will go here. By checking this 1 1, this has already been unassigned, this is not unused. This opcode for 2 address instruction is actually unused. Okay, so 1 1 is actually unused. So now this becomes fixed actually. For 1 address instruction, this becomes fixed. If I make it 0 0, then again I will go back to 2 address instruction. So 1 1 is fixed. Okay, and this is my opcode for 1 address instruction, right? And this is my address 1. So I have, how much space do I have left? So this is fixed, right? This thing is fixed actually. From the previous 2 address instruction, this is fixed. So how many space I have? 2 bits. So total 2 bits I have, right? 2 bits I have left. I have 2 bits left. So how many different combinations I can do? Because already this has been fixed. My CPU identifies that it is a 1 address instruction by just the first 2 bits. Okay, and this is fixed already. This is already fixed. So I have 2 bits left. So how many different 1 address instruction I can have? I can have 2 raised to power 2 into 1. 1 into 2 raised to power 2. How does this 1 come? I will explain. Don't worry, later on. This is 2 raised to power 2 because I can have total 4 combinations. I will write the combinations in front of you. I will write the combinations. So this, right? If I write here, first one is 1 1 0 0, 1 1 0 1, 1 1 1 0, and 1 1 1 1. This is the maximum number of 1 address instruction that I can have. Okay, maximum number of 1 address instruction. Now let me take another situation. What is the another situation? If I change this question, right? If I change this question now, okay, I will copy and paste this question again. Now what I do, I change this statement. This I change to 2. If I change to 2, what will be changed? Pause the video, try it by yourself and tell me in the comments what will be changed if I change this to 2. Okay, just tell me in the comments below. Everything will be same. This will be same. Okay, this thing will be same. This thing won't change. But one important thing will be changed. What will be changed? This, right? This thing will be changed. Now they're telling me that I am assigning two address instructions. So I'm not assigning 3. I'm only assigning 2. So if I'm assigning 2, so let just hypothetical. I'm just assigning any 2. You can assign any 2. It will not change your answer. So I have assigned these 2 and this 2, right? I have left. So now how many combinations I have for 1 address instruction? How many combinations I have? If I check, right, now for 1 address instructions, this will be simply, these 2 are fixed, right? These bits are fixed. So it, like, the combinations can be, I will just copy and paste this thing. Okay, this thing will copy. This also again I will copy. It can be 1 0 1 0 1 0 1 0. So this, right, this is fixed. Okay, I am only varying this, correct? So now how many one address instructions I can support? I can support a total of 8, correct? 8. And how it comes? How many ways I can define that this is a one address instruction? 1011. So 2 ways, right? So it becomes 2 multiplied by the number of bits that I have left for one address instruction. 2 bits I have been left, so it will be 2 raised to power 2. So this 2 comes by the unused opcodes from the previous higher address instruction, from the previous instruction. Okay, and this comes number of bits available for current address instruction. Okay, so this is a formula, like many educators, they just mug you of this formula, but you have to understand how many free or unused opcodes I have from the previous instruction. That many combinations I can have in this here, multiplied by the 2 raised to power number of bits that is available for my current instruction opcode. Okay, so I hope you have understood. Like, I have a table. If this is the 2 address instruction, right? So if I have 2 address instruction, and okay, yeah, this is actually the number of 2 address instruction used. Okay, assigned. So these are the used 2 address instruction assigned. These are the assigned 2 address instruction. If I have assigned 3 2 address instruction, and then how many unused opcode I have for 2 address instruction? 1, right? Because 2 raised to power 2 is 4, so I can at max assign 4, but I have assigned 3. So how many unused opcode I have? 1. So how many one address instruction I can support? Maximum will be 1, the number of unused opcodes multiplied by the 2 raised to power the number of bits that I have available, that is 2 bits, right? I have 2 bits available, so it is 2 raised to power 2. So what is the total number of instructions? Total number of instructions here is, I am assigning 3 2 address instruction and 4 one address instruction. Total number will be 7. Same as 2, right? If I am assigning only 2 address instruction, I have 2 unused opcodes. How many maximum I can support one address instruction? It will be 2 times 2 raised to power 2. This will be fixed. This thing will be fixed, right? So now I can support, this is 8 and this is 2. So I can support 10 instructions total. The architecture, CPU architecture can support 10 instructions. If I have assigned only 1 2 address instruction and I have 3 unused opcodes, so it will be 3 times 2 raised to power 2, that is 12. And if I am not assigning any 2 address instruction, basically it is a 1 address instruction only, so it will be 4 times 2 square, that is 16, which we get by our own standard formula, that is 2 raised to power 4. So this is simply a 1 address instruction architecture CPU. Okay, this is not a variable length opcode, this is a fixed length opcode. This thing is a fixed length opcode. Okay, so there is another way. If I am assigning all 4, if I have assigned all 4, okay, of 2 address instructions, so how many unused opcode I have? 0. So this will become 0 times 2 raised to power 2, which is 0 only. So here, how many total number of instructions I will have? Total 4. And what is this actually? This is actually 2 raised to power 2. What is 2? 2 is the number of bits of the opcode, right? How many opcode bits I have? 2. Remember, 2 address instruction, I have 2 opcode bits. So it will be 2 raised to power 2. So this will be Yeah, this will be 2 so total, this is also a fixed length instruction, right? If I'm using all the possible maximum number of instructions in a particular address, so it will become a fixed length instruction, and this, all these are variable length opcode, and these two are the fixed lengths. Okay, I can extend this further. Okay, okay, so I hope you understood, like we have to have a trade-off, right? If you want your CPU to support this many number of 2 address instructions and this many number of 1 address instruction, you have to decide accordingly. So accordingly you will choose the unused and used opcode. I hope you got the understanding, and if you didn't, please rewind, rewatch, because you need to watch this very, very carefully and repeat again. So now if I tell you, this is the same question only, I think this is the same question only, right? This is the same question. Now if I tell you to solve the same question, right? If I tell you to solve the same question, will you be able to solve it? Okay, so this question I'm giving you as homework, and in the next lecture I will solve this question. I will give you homework, more questions. This also, take the screenshot, pause the video and try to solve all these questions, and in the next lecture we'll solve all these questions, and also we'll learn about new concept, that is instruction cycle. Pause the video, try it out by yourself, and in the next lecture we'll solve all these questions. Okay, this is one question, and I think this is the last, this is the end, I think. Yeah, this is the end. So we'll solve all these questions, and in the next lecture we'll start with new topic, that is instruction cycle. Thank you for watching, and I will see you in the next lecture. Until then, happy learning. Hey everyone, and welcome back to my channel. So today we'll continue with the next lecture of our COA. So we'll continue with lecture 2C. So in the previous lecture we learned about different types of instructions based on their address. We learned about fixed length instructions and variable opcodes and fixed opcodes. So I gave you, like I taught you the how in variable opcode our CPU actually understands whether this is a 2 address instruction or a 1 address instruction, or vice versa. Okay, so today's lecture will solve the remaining questions that I gave you as homework. Okay, all those questions will solve, and then we'll start with a new topic, that is instruction cycle. So let's do all these questions. This was the question that I gave you homework in the previous lecture. A machine has 32-bit architecture. That means it is fixed length instruction of 32 bits. Instruction length is 32 bits with one word one word long instructions. So one word is 32 bits, which is 4 bytes. It has 64 registers. I will have 64 registers. Then how many address lines will I require to define this registers, to define the location of these registers? 64 equals to 2 raised to power n. So your n will be simply 8 bits, right? I will require 8 bits to define different. So this is not 8, sorry, this will be 6 bits. I will require 6 bits to define 64 registers. Okay, so now next, what are they telling? Each of which is 32 bits long. So obviously it's a 32-bit, it follows a 32-bit architecture. Each registers are 32 bits long, that is each registers, right, are 4 bytes. Okay, so this, let's assume some starting address as 100. This will be 101, and it will go on till how many? 163. Okay, this many registers I have, total 64 registers, correct? 4 bytes in the memory. It needs to support 45 instructions which have an immediate operand in addition to 2 register operands. So I am using, this is for the fixed opcode length. So I need 45 instructions. I need to support 45 instructions. If I need to support 45 instructions, what should be the opcode length? The opcode length will be equals to 2 raised to power m, should be equals to 45, correct? So m will be equals to what? Upper bound of log base 245, it will be 6 again. So I will be requiring 6 bits to define 45 different instructions. Okay, so also I need to support like two address instruction and a immediate value. So this is my opcode, this is my address 1, this is my address 2, this is my immediate value. What is the size of these individual things? So opcode length is 6 bit, correct? Address are the address of the registers. So how many registers I have? I have 64, right? So they will require 6 bits again. Each address will require 6 bits. So this is 6 bits. This is also 6 bits. So what will be my immediate value length? It's same, right? Overall instruction length is what? 32 bits. So what is used up by these three components? It is 6 plus 6 plus 6, that is 18 bits. So the bits, number of bits that I will have for immediate value will be for 14 bits. Okay, this many bits I will have. Now what are they asking actually in the question? They are asking, assuming that the immediate operand is an unsigned integer. Unsigned integer meaning it doesn't have any sign, it can be only positive. Okay, the maximum value of the immediate operand can be. So the total length of the immediate operand is 14 bits. So what will be the maximum value of this 14 bits? So how many combinations I can have? I can have from 0 to 2 raised to power 14 minus 1, because obviously I have to take into account 0 as well. That's why the answer maximum value will not be 2 raised to power 14, it will be 2 raised to power 14 minus 1, because this minus 1 is due to this 0. This 0 has been accounted. So this is one combination. So the maximum value of the immediate operand can take 2 raised to power 14 minus 1. That is the maximum value of the immediate operand, right? Why it is the maximum value? You just write down. You have 14 bits, right? Like, let's take small example. I have 4 bits. What is the maximum value? If it's an unsigned integer, what is the maximum value it can take? If all the bits are 1. What happens when all the bits are 1? You get 15. Okay. What is this? This is 2 raised to power 4 minus 1. That's it. Just always take small number of bits. Check whether this example is working for this or not. So if I have 4 bits, the maximum number will be 15. If I have 14 bits, what will be the maximum number? 2 raised to power 14 minus 1. So what is 2 raised to power 14 minus 1? So what is 2 raised to power 10? Into 2 raised to power 4 basically. 2 raised to power 10 is 1024 into 16. Okay, so this is like a bit difficult. So I will use a calculator only. So 16 into 1024, it will be 16384, and I have to subtract it by 1. So maximum will be 16384 minus 1. So it will be 16383. Okay, so your answer will be 16383. This will be your answer basically. So that's basically it about this question. Let's do this question. So this has this had other 2 parts as well that we'll solve in today's lecture only after understanding instruction cycle. So I have considered the following segment: R1, R2, R3 are general purpose registers. These instructions are there, right? Move, add, all these things. This basic mnemonics you can understand. Move means moving the values. Look, it has also mentioned the operation. What is actually happening? So assume that the content of memory location 3000 is 10. So in memory location 3000 I have 10. Okay, memory location 3000 I have 10. Somewhere in location 3000 I have the value 10. In memory location the content of register R3 is 2000. So register R3 has R3 has 2000 value, and the content of each of the memory locations from 2000 to 2010 is 100. So let's say from here, right, I am somewhere here 2000 to 2010. All the contents are always 100. Okay, and what else they're telling me? The program is loaded from memory location 1000. So program is loaded from memory location 1000. That means my PC value, current PC value is what? Program counter value should be 1000, right? PC stores the address of the current instruction. I mean the next instruction that it needs to be fetched. So before starting of the program, next instruction will be fetched from the 1000 address. All the numbers are in decimal. Assume that the memory is word addressable. The number of memory references for accessing the data in executing the program completely. So how many times I am actually using memory references? How many times I am accessing the memory? Here move R1 3000. So what am I doing here? I'm going to location 3000 and then whatever the contents there are, I'm moving it to R1. So am I accessing a memory? Yes, I am accessing memory. So this will be 1 times. Here move R2 to R3. What it is doing? It is going into address R3 and then copying it back to R2. So am I accessing a memory? Yes, I'm accessing a memory. So this will be 1. This will be once. Okay, once here I'm accessing the memory. Okay, then here how many times I'm accessing the memory here? Then again this instruction, right? This small instruction, what it is telling, move R3 R2. That means whatever the contents of R2 I have, move it to R3. Again I'm accessing the memory. Okay, in these 3 cases. So what is happening? If I see the code, right? Actually there is a loop here. So it's not like throughout this whole program I will only access the memory thrice. As there is a loop, what it will do is it can loop back to here. So this loop, right? Don't worry, I do get it that you are not able to understand this loop here. It will go here. In recent question in GATE 2000, like from now onwards, they will explain all this. It's okay. But I am explaining you this because previously 8085 was in syllabus. Now 8085 is not in syllabus. So loop and all those things will be explained. What does it actually do? So here, right, loop means it will check if I am getting a 0 value. Okay, if I am getting a 0 value, then branch not 0. If it is not 0, right, I will branch to this instruction. If it is 0, I will not branch. If it is not 0, I will branch to this instruction. If it is not 0, I will branch to this instruction. If it is 0, I will not branch. If it is 0, I will not branch. Branch means I will not jump, basically. I will not jump. Okay. So how do I check it? So I have to check, right, whether the contents branch 0 means, okay, yeah, branch or not 0. If this result, whatever this result is, if this is 0, then only. So I'm decrementing R1, right? After decrementing, if I'm getting a 0, I will not branch. If I'm getting a not 0, I will branch. I will branch to this loop. Don't worry, they will mention all these instructions now. Okay, they will mention. Previously, this was a 2007 question. There we had a subject known as 8085. There you already knew all these programs. You have to remember the codes. Okay, now you don't have to. So what it will do is here. Let me now run the program. So what I'm doing, I'm moving the value address location of 3000 to R1. So 3000 has 10. I'm moving it to R1. So R1, I will write here, R1 will have value 10 because 3000 location, like I will go R1 equals to M 3000 and M 3000 is simply 10. Okay, fine. What about next? Next is R2 is being stored to MR3. Okay, R2 R3. So what this means is R2 is storing the memory location of R3. R3 is what? R3 contents of R3 is 2000. So I'm going to this 2000 location, okay, and then getting the contents. Don't worry if you are not able to understand this. We'll learn indirect addressing later on. This is actually addressing mode that will be taught to you in the next lecture. So don't worry if you're not able to understand. We'll understand this later on. For now, just understand this. This R3 has 2000 value, and what this instruction means is that R2 R3 means I'll go to the location pointed by R3, pointed by the contents of R3, that is 2000, and then take that value. What is being contained by 2000? It is 100. So R2 will be simply equals to 100. Okay. Next, I have add R2 R1. Add R2 R1. So I will add R2 R1 and store in R2. So R2 will be simply R2 plus R1. So it will be 100 plus 10. So it will be 110. Next, if I go next, what is the next step? These are all micro operations. Next is move R3 R2. So whatever the contents of R2, I am moving it in R3. So I will move in R3. So this will be R3 equals to R3 is equals to what? R3 is equals to R2, right? Whatever R2 has, R3 is equals to that. Okay. So this R3 will be equals to R2, simply 110. And then what I am doing, I am just incrementing R3 and decrementing R1. So incrementing R3. So R3 is R3 plus 1, that is 111, and I am decrementing R1. R1 is what? R1 is R1 minus 1, which is 9. Now what I am doing, I am just checking if the final result, right, what I did just before this instruction, is it 0 or not. If it is not 0, I will loop, again start over. If it is 0, I will not loop, right? I will halt my process. Okay, that is what this BNZ means. BNZ means branch not 0. Branch if not 0. Branch if not 0. Don't worry, they will explain. They will explain this, right? In nowadays they will explain if they give this type of portion. So here one thing you have to understand is that your R3 is decrementing. So how many times will this loop occur? It will check until R1 goes to 0, then this loop will stop. Every time I am doing some processing, what is happening? I am not doing anything, right? I am just going. So I am starting from here again. So this is one time operation. This is one time operation. So in the first line, right, I am accessing the memory only once, and this is a one time operation. And in the loop, how many times I am accessing the memory? In loop, I am accessing memory twice. So if let's say the loop runs for x times, loop is x times, it is running for x times. I don't know, I will calculate that. It is running for x times. Now can you tell me in this overall program how many times will I access the memory? This, right, this first line is only one time. This is only, I'm accessing here only once. After this, whatever is happening, I'm repeating. That is inside loop. So I will access, this one is fixed, this is for the first line, and the number of times which the loop is happening, I am accessing the memory for each time twice. So it will be 1 plus 2x, right? 2x means 2 is the number of memory access times the number of times the loop is actually working. Okay, so this will be equals to total number of memory access, right? This will be the result basically. This will be the result. So for this I need to find out x. How do I find it out? So it's very simple, right? This is happening only once and all these manipulations are happening, but I don't care about this. At the end I'm just decrementing R1 each time by 1, okay, at each event. So when the loop ran once, my R1 from 10 it reduced to 9. Then again from 9, when the next time the loop will run, it will reduce to 8. Then again it will reduce to 7, and it will go on until what? 0. It will go on until 0. So at 0, then next my B and Z will check branch if not 0. Is it not 0? No. R1 this time is 0 actually. So I will not branch, I will halt HLT. This last instruction, right? But how do you identify the number of, like how many number of times this loop is happening? So whenever you are in some problem, right, you choose lower number of values. So let's assume my R1 starts from 2. Assume initially my R1 starts from 2. If my R1 starts from 2, so first time I will run the loop and 2 will be reduced to 1. Next time the loop will run and 1 will be reduced to 0. And at this particular point, right, after this particular point, what will happen? It will check if it is 0 or not 0. It is not, it is 0. So obviously I will not branch, I will halt. So how many times did the loop run? So once the loop ran when it reduced from 2 to 1. This is one time. And then again the loop ran when it reduced from 1 to 0. As soon as it goes to 0, I stop my loop. So for when R1 equals to 2, I am running the loop 2 times. So when R1 will be equals to 10, how many times will I run the loop? 10 times. So X will be, from this analogy, I get my value of X as 10. So I will replace that value. So number of memory access will be 2x plus 1 and x is 10. So it will be 2 times 10 plus 1, that is 21. 21 times I will access the memory in this particular program. That is option D. Option D will be correct. Now there is other parts which we will solve in today's lecture only. Okay, just understand this thing, that CPU actually, like this fundamental thing you understand, CPU can go to memory for only 2 reasons. Okay, CPU goes to memory for 2 reasons. One is instruction fetch. Okay, that we will study today only, instruction fetch. And the other is operand fetch. Operand fetch you already know, right? The contents of that particular memory, I am fetching it. I am storing it somewhere in my own register. And what is instruction fetch? It like PC tells go to this value, right? This will have the instruction. So it can either take the instruction information from the memory, or it can take the operand. So CPU has only 2 reasons to go to the memory. Okay, and it can only fetch from the memory, right? And it can obviously write from the memory. It can do all those things. Okay, I hope you understood this important point. Now let's do this next question. So here, consider the following instruction sequence where registers R1, R2, R3 are general purpose memory. Okay, denotes the content at memory location X is, okay, content at memory location X is, okay, what will be the content at memory location X? So after performing all this operation, what will be the content of memory location X? So this, right, this is actually not exactly that instruction set question, but these are also like easy questions only, which you will be able to solve, okay, by knowing few basic things. So if I see this, right, what will be here? So if I have to run this program again and again, this is gate 2021, and they here, if you observe, they will explain everything, right? They will explain what each instruction does. It's the same question, almost ditto same question only, okay, but here they have explained. Okay, so move R1 to 5000. Again, I am accessing the memory only once. Move R1 to 5000. So R1, like in memory, like I have to first write these things down, that memory location 5000 has value 10. Memory location 5000 has value 10. Okay, then my memory location 5000 has value 10. Then what are they telling? The content of the register R3 is 3000. So R3 has value 3000. Okay, and what else? The content of each of memory location 3000 or 3010 is 50. So like this is just the same question only, so I'll do it a bit fast. 3000 to 3010 is basically 50. So each of them has 50, everything has 50. The instruction sequence starts from memory location 1000. Okay, all the numbers are in decimal format. Assume that the memory is byte addressable. After execution of the program, the content of the memory location 3010 will be. So I am starting my PC initial value, right, is starting from 1000. So let me just go through what is happening in the program. First I am storing something from the memory to R1. Then I am storing the going to the memory of this particular location, storing it to R2. Then I am adding two things. I'm storing it in R1, R2. Then again what I am doing, I am storing this value in R3, memory location of R3. Then I'm incrementing. So once I do first few iterations, then I will understand, because I am observing there is a branch instruction, so there will be a loop basically. Okay, there will be a branch. Okay, so let me break it down basically. So what is happening here is that first I am moving the contents of 5000 to R1. So R1 will have memory value of M 5000. So what is it? It is 10 basically. It is 10. Okay, then R1 has memory location 5000 to 10. Then next what is happening? Memory location, like I'm moving the memory location pointed by R3 to R2. So R2 is MR3, and what is R3 equals to? R3 contents of R3 is 3000. So it will be M3000, and 3000 has value 50. It has value 50. Okay, so my R2 will be equals to 50 basically. Fine. Next what is happening is that move, like I'm adding R1 and R2, right, and storing it in R2 itself. So then I'm doing R2 equals to R1 plus R2. So this is 10 plus 50, and I'm storing it in R2, so it is 60. So R2 becomes now 60. Next I'm doing move R3 R2. So I'm moving R2 contents of R2 in memory location pointed by R3. So memory location pointed by R3, that is 5000 or 3000, sorry, will be equals to R2 now. So it is basically memory location of 3000 will be equals to R2, that is 60. So this, right, this 3000 value changes to 60. Okay, fine. This is 60 now. Next what is happening? Then what I'm doing, I'm incrementing R3 and decrementing R1. So R3 becomes R3 plus 1. So it is R3 is how much? R3 is simply, if you see, R3 is 3000. So R3 is 3000. R3 will become 3001. And R1 I am decrementing, right? R1 I am decrementing. What is R1? R1 is 10. So we'll decrement R1 by 1. R1 minus 1, so it will be 9. Next I am checking branch if not 0. Branch if not 0 to the given absolute address. I will branch to this address if the result, right, whatever we computed, is not 0. Is it 0? No, it is not. It is not 0, right? It is not 0. It is 9. So again I will branch to absolute address 1004. 1004. Branch if not 0 to the given absolute address. Assume that the content of the memory location 5000 is 10. Okay, and content of the register is R3. The content of each memory location from 3000 to 3010 is this. The instruction sequence starts from, okay, memory location 1000. Okay, one thing I forgot to mention, this, right, this memory, how is it addressable? Have they mentioned anything? Consider sequence content. Assume that the memory is byte addressable. This is a very, very important word. It is byte addressable. If it is byte addressable, then my instruction size rates will be something like this, right? This will be 1 byte, 100, this is 1000, then this is 1 byte, then this is 1001. So what is happening here is that if you observe this instruction, right, it takes up some space. What is the space? 4 bytes. They're given. So from 1001 to 1002 to 1003, I will have 4 bytes, and that will be occupied by the first instruction. Okay, and from 1004, I am starting the next this instruction, right? This instruction is starting from 1004. This is 1000. Okay, this is getting started from 1000. So actually what is happening, this instruction is telling me branch to this particular absolute value if it is not 0. So I will branch to here. I will branch to here, right? I will branch here. So from here I will branch to here. Okay, this is the 1004 address, right? This instruction. So again I will repeat all this. Then again I will check for content of R1. Again same question, just like the previous question, right? Just they have given me the absolute address and I have to calculate the address, right? This address. So as this instruction is 4 bytes, so this will be stored like this in 4 bytes. Then from here I will again restart. So it is just like a loop structure. So how many times will the loop occur? Actually 10 times, right? The loop will occur 10 times, and they are asking me what will be the content of the memory location 3010. So every time this loop will run, right? Every time this loop will run, R2 is this, R1, R2 is this, then memory location of R3 is this. Every time the loop is run, all this is happening, that is fine. I'm going to this memory location and making it equals to R2. Currently R2 is 60. So in next iteration what will happen? Let's do it for one more iteration so that we will understand this. Okay, let's do it for one more iteration. So in next iteration what is happening? Again from here loop will start, right? From here the loop starts. This is just one time operation, right? Just like the previous question. So I will store value of R2 pointed by the memory location R3. R3 is currently what? 3001. 3001. So what is being stored in 3001? It is 50, right? Because I just updated 3000. In 3001 it is still 50. So again I will do the same thing. R2 will be equals to memory location pointed by R3, that is M3001, that is 50. This will not change. So R2 again is 50 only. R2 is 50 only. So then what I will do? I will add R1 and R2. So R1 this time is what? R1 actually is 9. So R1 R2 will change to R1 R2, and it is 50 plus 9, that is 59. Then what we do? Then I go to this memory location. Then I go to this memory location pointed by R3. R3 memory location pointed by R3 is 3001, and I will update it with R2. So M R3, I will update it with R2. So MR3 is MR3, that means M3001. I will go and update it with R2, that is 59. It has been reduced now to 59. Next what I do? Next I increment R3 and decrement R1. So R3 will become now 3000 plus 3001 plus 1, that is 3002, and R1 will be decremented by 1. R1 minus 1, that is 9 minus 1, that is 8. So can I observe a pattern here? Can I observe a pattern? Yes, right, I can observe a pattern. Previously it was 59, now it is previously this memory content on R3, right? This 3000, like 3000 address had 60, 3001 had 59. So what will have 3010? It will decrement by 1. You can do the iterations. It will simply decrement by 1. So your result, right, your answer will simply be 50. Okay, your answer simply will be 50. Why? Because each time my loop is running, each time my loop is running, memory location 3000 plus I is becoming 60 minus I. This is happening. My loop is running 10 times. 10 times. So if loop runs 10 times, so memory location 3010 will become 60 minus 10, that is I is equals to 10, hence it will be 50. So they have asked what will be the value at memory location 3010, that is 50. So 50 will be your answer. Okay, now I know this is not with respect to those address questions, right, like those finding the opcode length and all those things. This is not with respect to that, but this was a different type of question, bit and byte addressable memory. So this also you should understand. Okay, just I just wanted to give you a brief idea about all this. Now we'll come to the variable opcode length. Okay, the variable opcode length. So I gave you homework this question, right? Give you homework this question. So now can we solve this directly now? Yes, we can. Yes, we can solve this directly. So I was done up until this part. Okay, I was done up until this part. And I knew how many unused opcodes I had. How many unused opcodes I had? I had total two unused opcodes I had, right? Two unused opcodes. So if I have two unused opcodes, like I'm not reading the question because we have already read the question previous lecture. So if we have two unused opcodes, that means in the next sequence I can have two different combinations, right? This two will be fixed into 2 raised to power number of bits that I have left. So out of this 20 bits, right, 8 bits are fixed for two address instruction. So out of this 20 bits, 8 are fixed. 8 bits are fixed. How many I have left? 12 bits. So I have 12 bits fixed. So this will be 2 raised to power 12 simply. Okay. So now like you can simply solve it. Right? You can simply find out the result. Okay. So what will be it? 2 into 2 raised to power 12. That is it is 2 raised to power 10 into 8. So it will be 8000 something, 8192. So the maximum number of one address instruction that I can support is 8192. And what is the minimum? Minimum will be 1. At least you have to support 1. Okay, for it to be called a one address instruction architecture, you have to at least support 1. So option A will be correct. Option C will not be correct. Okay, minimum at least you have to support at least 1. Okay, you cannot ignore that. So that's how we solve. Let's do another question like similar to this. The concept will be more cleared by this, right? Consider a system with 32-bit instruction and 12-bit addresses. So my instruction length is 32-bit, okay, and address is 12-bit. If the system supports 254 2-address instruction, once I read this, I will directly go to the formation of the instruction, right? So first I will have a opcode, then I will have two address 1, address 2, opcode 1, address 1, address 2. Okay, so total length they have given me how much? It is 32 bits. Now this is 12-bit address. So this is 12-bit address. What does it mean? So each address is 12 bit. So this is 12 bit, this is 12 bit. So what will be my opcode length here? Opcode length will be 8 bit. So how many maximum 2 address instruction I can support? 2 raised to power 8, that is 256. But actually how many I am supporting? 254. So how many are left unused opcodes? Is 2, correct? This 2 will go into the next state. Okay, now it is telling me that I am supporting 4001 address instruction. Again I will draw the instruction. This will be my opcode. Okay, opcode will be big this time. and this will be my address 1. And again, this overall is 32 bits and address 1 is of 12 bits. Okay, so opcode, what is the opcode length? Opcode length is 20 bits. Opcode length is 20 bits. So opcode length is 20 bits, right? So now what I can say is, out of this 20 bits, how many I can actually use? Because this 8 are fixed, right? 8 are used for the to address instruction. So 8 will be fixed. 8 bits are fixed, and out of this 8 bits, I have 2 unused opcodes, right? So here, this 2 will come here, and why this 2 comes here, that also I have explained in the previous lecture. I will not explain here. I will have explained this very well in the previous lecture. Okay, 2 times the remaining bits. How many remaining bits I have? 12, right? 12 bits I have remaining. Out of 20 bits, I can use 12 bits as it is. So it will be 2 raised to power 12. So what is this equals to? It is 8192. Okay, I have 8192 total maximum that I can use for one address instruction. What are they asking? They are asking what is the maximum number of 0 address instruction that can be defined, like the max. Okay, so sorry, this question is phrased a bit wrong. The maximum number of 0 address instruction that can be defined is like given as 2 raised to power n. Then what is the value of n? So I have to identify the maximum number of 0 address instruction, because maximum 1 address instruction I can use 8192, but I am only using 4000 of this. 4000. I am only using 4000. So if I am only using 4000, I have unused 4192 states. Okay, I am not using those. So I can use it in the next state. So I will exactly do that. So now what I will do is I will draw for 0 address instruction. So this whole thing will be my opcode, right? Whole thing will be my opcode. Now if this whole thing is my opcode, this whole thing is 32 bits only. Out of this 32 bits, this is one instruction, right? Out of this 32 bits, actually this 20 bits are fixed, right? 20 bits are fixed from the previous 2 address and 1 address instructions. They are fixed. They have been fixed. So this 20 bits have been already occupied by the previous instructions. Okay, I have 12 bits left, and out of this 20 bits as well, I have few unused opcodes, right? 4192 unused opcodes. So I will apply the same formula, that is 4192 into 2 raised to power 12. Okay, so what is 4192? 4192 is actually can I write it down in terms of 2 power? Can I write it down? Actually, I don't think I can, or I cannot. I don't think so. I don't think so. A bit of mistake has been done on my behalf. So actually, bit of mistake. So it should have been actually bit of mistake on my behalf. So 2 raised to power 12. It is 4096. Okay, bit of mistake on my behalf. So what we can do, right? This, right? This will not be exactly equals to 4000. This will be 4096. Mistake on my behalf. Why? I am explaining just in a second. I am explaining. Okay. So it is 4096, and if it is 4096, right? How many unused I will have? I'll have 4096 unused, right? So here this will be 4096 into 2 raised to power 12. What is 4096? 4096, right? 4096 in itself is 2 raised to power 12, right? 4096 in itself is 2 raised to power 12. So this will be again 2 raised to power 12. Overall, it will be 2 raised to power 24. Okay, so why am I I made it 4096 just to write it down in terms of power, 2 raised to power term, else the question will be wrong, right? Question will simply be wrong. Okay, so this will become 24. So I have to compare. This is equals to what? This is the maximum zero address instructions that I can support. Okay, this is the maximum zero address instruction that I can support, which they have given me in the form as 2 raised to power n. So n, from here I get 24. So 24 will be your answer. Okay, this is a very, very elegant question, and I am expecting a question for GATE to ask on this same type of format. Let's do the next question. Next question is, a processor has 64 registers and uses 16 bits of 16-bit format. So 16-bit instruction format. So instruction length they have given me as 16. Okay, and it has 64 registers. So how many address lines or address bits I will require? Again, 64 equals to 2 raised to power m. So m will be simply equals to 6. It has two types of instructions, I type and R type. Okay, I type instructions contains an opcode, a register name, and a 4-bit immediate value. So I type, it contains a opcode, a register name. Register name means address, basically address, and an immediate 4-bit value. This is 4-bit immediate value, IV. Okay, and what about R type? Each R type instruction contains an operand and 2 register names. So it is basically 2 address instruction. This is my R type. This contains address 1, address 2. Okay, so what is the length of this? The length, right? Overall length should be 16 bits only. This length should be 16 bits. They have defined me. It is like whatever we study for fixed instruction, fixed length instruction only. Opcode length can vary. Okay, what are they asking actually? If there are 8 distinct I type opcodes, then the maximum number of distinct R type opcodes. So I know there are 8 distinct I type opcodes. How many opcodes there will be for R type? How do I do? It's the same procedure, right? Same procedure, just what we will be learning. So what is the length of opcode in I type? So address 1 is of 6 bits, right? So 4-bit is immediate value. It is a 6. So opcode length will be 6 only, because overall instruction length is 16. So 6 plus 4 is 10. 16 minus 10 is 6. So opcode length will be 6 bits. Okay. So if opcode length is 6 bits, that means how many different I type instructions I can have? 2 raised to power 6, which is equals to 64. But actually how many am I using? I am using only 8 opcodes, 8 I type instructions. But what is the problem here? Have I checked the opcode length of this? What will be the opcode length of this? Opcode length for this, right? If I have 2 address instruction, this will be 6. And this will be 6. So opcode length for this will be 4. So from where should I have started? I should have started from here. Why? Because in the previous lecture I explained, right? I have written down a point. Where have I written down that point? Somewhere I have written down that point, right? Yeah, here, right? I've written first check for the lowest opcode length. Always we have to start with the lowest opcode length. Okay, first we'll fix the lowest opcode length. Few bits will be fixed from that. Then we'll go to the opcode length which has more number of bits, so that I can fix the lowest opcode length. Those bits will be fixed. I can vary the other bits, right? So first I will start with lowest opcode length. So I will start with this. Now they are asking, I don't know how many R type instructions I have. So I will assume I have X R type instructions. Okay. If I have X R type instructions, how many maximum instructions I can have opcode R type instructions? That is 2 raised to power 4. Correct. So, but I am using only X R type instructions. If I am using only X R type instructions, how many unused I have? Unused R type instructions. Unused is 16 minus X. Now I will go to I type instruction. Okay. Now I will go to I type. I type is what? In I type, I have total 6 bits. Out of the 6 bits, actually 4 bits are fixed. Okay, 4 bits are fixed for R type. So these 4 bits are fixed for R type. What is left now? The thing that is left is simply this much, right? 2 bits I have left. So I can, like, this can vary 2 raised to power 2, and in the from the previous stage I had 16 minus x unused opcode, so that also I can use, right? Multiply, that will be multiplied here, 16 minus x multiplied by 2 raised to power 2. This they have given me, this is the maximum number of I type instructions. This they have given me as what? This they have given me that this is equals to I type instructions is 8. I can support 8 I type instructions. This is equals to 8. So from here I will be able to easily find out my value of x. So what will be x from here? So this will be 2, x will be simply 14. So this will be answer. So this is a good question, although here I am not talking about address instructions, but this is also possible, right? If I have some register, it is a one address instruction with some immediate value. Okay, so I hope you understood the point. Please go through it again. Always, the what important point I have also told previously as well. Always in these type of questions, always start from the opcode which has lowest length. Okay, always start from that opcode which has the lowest number of bits. Okay, so we have to start according to that. So why what is the reason is I fix those bits when I move to larger opcodes. Okay, that's why, that is a simple reason basically. So yeah, we have, I think, another last question. So we had huge number of questions actually. So just hold on a second, I will check if everything is recording or not. Yeah, everything is recording fine. So this is the last question. A processor has 16 integer registers, right? R0 to R15 and 64 floating point registers, F0 to F63. So in total, how many registers I have? For this, how many bits I will require to define this? Integer registers, how many address lines I will require to locate integer registers? I have 16, so I will require 4 bits. And floating point registers, how many address lines I will require? I have 64, so I will require 6 bits. Okay, they are separate. Why I will explain. Once you read the question, right, you will understand why they are different. That's why I am representing them separately. I am locating them separately. There are 4 categories of instruction: type 1, type 2, type 3, type 4. Type 1 category consists of 4 instructions, each with 3 integer register operands. So type 1 has 3 integer register operands. So first I will write down the type 1 type instruction. I have a opcode here, then 3 integer registers. So it is, I can name it according to my convention, that is Ri, or they have named some convention, right? They have given R. Okay, they have given R, so it doesn't matter. They have given R, R1, R2 and R3, and have they mentioned the instruction length? Okay, have they mentioned the instruction length? And it uses a 2 byte. Like once you read a question, right, in CS, sometimes what happens is the question is so big that you miss some important point. I missed an important point, that they have mentioned the instruction length. It is a 2 byte instruction format. 2 byte means what? 16 bits, correct? So this whole length will be 16. So each register has 4 bits, right? 4 bits. So this will be 4. This will be 4 bit, 4 bit, 4 bit. So overall opcode will be what? Opcode will be 4 bit. Okay, because this whole length is 16, so 16 minus 12 is 4. So opcode length will do 4, right? So I have to check the opcode length everywhere for all the 4 types. So let's read the next type. What is the next type? Can copy and paste this actually, then I will choose the next type. But instruction size length will be fixed, right? That is 16. Next type, type 2 is what? Type 2 consists of 8 instructions. So type 1 consists of 4 instructions. So I1 is equals to 4. Okay, that is my like type 1 instruction is 4. I2 is how many type 2 instructions I have? 8. 8. And what are they telling me? They're telling me that each with 2 floating point register operands. Type 2 has only 2 floating point register operands. So this, right, this will not have third register. It will be 2 register operands, that is F1 and F2. So this is 6 bits and 6 bits, because to represent a floating point register I need 6 bits, because I have total 64 floating point registers. So now what will be the opcode length? Opcode length here, right, will be lowered. It will be only 2 plus 2, 12. It will be only 4. Okay, it is not lowered, it is same only. It will not be lowered, it will be same. So because overall opcode, overall instruction length is 2 bytes, that is 16 bits. What about type 3? This is type 2, right? Type 3, I will just draw the type 3 one. Type 3 is what? Type 3 category consists of 14 instructions. So type 3 has 14 instructions. I3 equals to 14. And each with, okay, this is done. Type 3 has 14 and each with 1 integer register operand and 1 floating point register operand, 1R plus 1F. So it will have F and R. R1. Okay, so this R1 will be of 4 bits, this F1 will be of 6 bits. So this will be larger opcode length. This will be like, this has become 10 now and I have 16 instruction length, so this will be 6 bits. Okay, next is type 4. Okay, why is it not pasting for some reason? Yeah, type 4. Now type 4, in type 4 they're telling me type 4 consists of n instructions. So it is unknown to me. So type 4 consists of n instructions. I4 is n simply. And how is the formation? It each with a floating point register operand 1F. So it has only a single floating point operand 1F. So it doesn't have even a integer operand. So what will be the opcode length now? It will be simply 10 bits, right? Because overall instruction length is 16 bits. So this has 6 bits. So the remaining 10 bits will go to opcode. So now which one has the lowest opcode length? I will start with that, because here my opcode length is varying, right? I can observe, like from the question itself I can understand this is a question of variable opcode length. That's it. I can take the hint. Okay, and now I will just look for the opcode which has lowest length. Which has the lowest length? Which opcode? I can observe this one, right? This one has the lowest length. Type 2. Type 1. So type 1 and type 2, both of them has the lowest length. Now it doesn't matter if you choose this one first or this one first. It won't matter. We'll see. You can I will choose type 1 as the lowest, and you can do as a homework type 2 as the lowest. You will get back to the same result. So type 1 has lowest opcode length. Type 1 has lowest opcode length. So if type 1 has lowest opcode length, I will start with that. So I'll copy this. So what do I observe is I have 4 bits for the opcode. Maximum how many states I can have? 2 raised to power 4, that is 16. But how many actually I am using? Only 4. I am using only 4 instructions. So 4 I am only using. So how many unused I have? 12. I have 12 unused. Next I will move on to the next instruction, that is type 2. The next lowest. I'll move on to the next lowest. I'll move in the non-decreasing fashion. T1 has the lowest opcode and I will move in the non-decreasing fashion. Okay, so then I will go to type 2. So you can reduce this size further actually for my convenience because I have to add many things. So then I will move to type 2. So type 2 is where? Here, right? Type 2 is here. So I will copy this. Okay, it got moved, right? That doesn't work like that. Okay. Type 2 is here. Okay, I will move this I to here. So how many I'll use? So here, right? Out of this 4 bits, all 4 bits has been fixed already by the previous state. So all 4 bits have been fixed. Okay, I will reduce the size actually. 4 bits fixed by type 1. So how many different instructions I can have unused of the previous state? That is 12. Okay, this will not come here, this will come. It will be 12 times 2 raised to power the number of free bits that I have in this current type. How many free bits I have? 0. So it will be 0. So I can use, I can have 12 type 2 instructions because I had in the previous type I only used 4. So I have 12 left. So I can use those 12 here in this type 2. But how many actually I am using? Only 8. So I am only using 8. So overall how many unused opcodes I have for the type 2? It is 4. So unused is 4. Again I will move on to the next state now. So then what is the next least opcode length? 6 bits. Type 3, right? I will move on to the type 3. Okay. So apologies if the font is smaller, but we have to just do with it. Okay. So this one, right? How many of bits I will fix from the previous state? Here 4 bits were fixed, right? So I will obviously fix 4 bits here because 4 bits are fixed from the previous type. The previous type opcode length was 4 bits. So here I will fix 4 bits. Okay, so this will be 2 bits. 2 bits will be free. Okay, 4 bits are fixed from the previous. Okay, so now what I can write here is this I will take, right? This unused I will take. So unused from the previous state I had 4, and currently how many free bits I have? 2 free bits. 2 raised to power 2. So overall I can have 4 into 4, that is 16. 16 maximum instructions I can have in type 3. But actually how many am I using? Only 14 I am using. Only 14 I am using. So this will be used is 14. So unused becomes 2. Okay. So unused is 2. So I'll go to type 4 and I will say how many maximum I can use. Okay, so I'll copy this type 4, reduce the size. Okay, and I will come to type 4 because next highest length instruction is type 4. So I'll come here and I will see that how many bits are fixed here. How many bits are fixed from the previous type, right? Total of 6 bits are taken from all the previous type 1, type 2, type 3. 6 bits are already fixed. So out of this 10 bits, 6 bits are already fixed. 6 bits fixed. How many I have left? Only 4 bits. Okay, so how many opcodes I can have? This is 10-bit opcode length, right? If this is 10-bit opcode length, I have 4 bits free, so it will be 2 raised to power 4 into the unused of the previous state. How many unused I had? 2. So 2. So this will become 32. So this is the last state actually. So maximum I can use 32, and I will obviously be using 32 only because they have told me but type 4 category consists of n instructions, each with floating point register value. The maximum value of n. What can be the maximum value? This, right? The maximum possible value of n is 32. I can obviously choose lower number of instructions, but the maximum possible value of n will be 32. So this will be answer. This is a very, very elegant question. Okay, this is a very, very elegant and good question, right? 32 will be your answer simply. Okay, we had another question. I'm sorry, I apologize for messing up. We have another question as well. These questions are very, very good. Please revise it again. 32. Okay, so now we'll come here. We'll come to 28 question. Using an expanding opcode encoding for instruction, is it possible to encode all the following in an instruction format shown in the below figure? 14, I need 14 double address instruction, 27 single address instruction, and no address instruction as 16. Okay, so they have given me the lengths of address as 6 and 6 bits. So is it possible? They are asking, is it possible to like have this instruction set architecture? Instruction set architecture means how many different instructions it contains. So this is the ISA, instruction set architecture basically. So let's check. Let's see the opcode lengths. Then I can decide. So this, they have already given me 2 address instruction opcode, like 2 address instruction format. That is this opcode length will be 4 in this case. So overall instruction length from this I can decode. What will be the overall instruction length? 6 plus 6 is 12 plus 4 is 16. So overall instruction length is 16 bits. So what I can do? I can simply do this, right? Okay, so I have overall 16 instruction bit length. So 2 address instruction I have. Look, I need 2 address instruction, then single address and no address. So I will start from 2 address. Obviously that will have the lowest opcode length. So if I start from 2 address instruction, right? 2 address. Okay, 2 address instruction will be, first I will have opcode, then I will have address 1 and address 2. They have already specified the lengths. This is 6 bit, and this is 4 bit. Okay, so how many maximum possible opcodes I can have? 2 raised to power 4, correct? But actually how many am I using? So I am using only 14. They have told me I am using 14 double address instruction, right? So I'm only using 14 double address instruction. So used is 14. So unused, how many unused I have? It is 2. So again I will go back to the next set of instruction, that is 1 address instruction. So in 1 address instruction everything will be same, just few things will be different. What will be different? I will have only a single address. So this will be deleted. This will be deleted. So now opcode length, instruction length is constant, right? Whatever we're studying for constant instruction length. So it should be 16 bits. So I have taken 6 bits. So what will be the opcode length? It will be 10 bits. Out of this 10 bits, the previous 4 bits have been fixed, because previously I was using 2 address instruction set. For this 4 bits has been fixed. So out of this 10 bits, the 4 bits have been fixed. 4 bits fixed. And I am left with this. How many bits I am left with? 6 bits. Because the total opcode length is 10 bits. So I have 6 bit. So how many opcodes I can have? How many instructions I can have? 2 raised to power 6 into the previous unused. Previous unused was 2. So it will be 2 times 2 raised to power 6. So overall it is 30. This is how many? This is like 2 raised to power 7, right? 2 raised to power 7 is 128 into 2. So, sorry, 2 raised to power 7 is 128 itself. Yeah. But how many actually I am using? I am only using 127. Only using 127 single address instruction. So out of this I am using 127. So how many unused I have? Unused is 1. Only 1. I have to leave at least 1 for the next 0 address instruction. So in 0 address instruction, what will happen is that I will not have any address, right? It will be totally opcode. So this is not 1 address, sorry. This is 1. This is not 2 address. This is 1 address instruction. And this will be 0 address instruction. In 0 address instruction, basically I will not have any address, right? Everything will be opcode basically. In this case, number of bits fixed will be changed also. So this whole thing will be opcode. Opcode will be of 16 bits. The whole instruction, right? So out of this, how many are fixed? 10 are fixed, right? 10 bits are fixed. Why are 10 bits fixed? They have mentioned here, right? They have mentioned this 10 bits are fixed. So this will be 16 bit, 6 bit. So here 10 bits are fixed. I have only free bits left, 6. Okay, I have only 6 bits left free. So this will be how many states I can have? Maximum possible. I can have 2 raised to power 6 actually, but this will not be 2 raised to power 6 times the number of unused, that is 1. So it will be 64. Okay. So I can have maximum of 64 0 address instructions, and they are telling me that I am using 60 no address instruction. So yeah, 64 is higher than this. So at max I can use 64 no address instruction, but I am only using 60. I'm only using 64 is unused. I don't care. I don't care about those. So I'm using 60. I will write here. At max I can have what do you call? At max I can have 64 0 address instruction, but I am only using 60 0 address instructions. So it is totally fine. Hence, it is possible to have a ISA, instruction set architecture, like given in the question. Okay, it is possible. So it is possible. What is the question asking? Is it possible? Just your answer. Is it possible if an instruction set architecture is given? Like, is it possible? Yes. My answer is yes. And I have justified as well. I have proven as well. Okay. So yeah, that's it basically for like the previous homework questions. Now we'll start with today's topic, that is instruction cycle and interrupt cycle. Let's start with instruction cycle. So what is instruction cycle? The instruction cycle represents the complete set of steps a CPU follows to execute a single instruction. So up until now we have learned about like instruction, right? A instruction can have 2 address operands, can have 1 operand, can have 0 address, can have anything. So those instructions, exactly what is happening in exactly a cycle. How is the CPU actually completing a set of steps that we'll understand in today's lecture. Even if few things were previously unknown to you, few things were cloudy, right? You couldn't understand. Now I think those will be cleared in today's lecture. Okay, steps in an instruction cycle. So like basically what happens, we fetch an instruction from the memory, right? Because first of all I have to understand what I have to do. What do I need to do? If we need to cook, let's say chicken kofta. If you have to cook chicken kofta, right? First you have to understand how to cook chicken kofta. You will go and read the recipe book. In the recipe book at the starting they will tell you what do you need to cook chicken kofta. Chicken you need, salt you need, sugar you need, on other things I don't know cooking, so I don't know. Okay, but these things you will need to cook chicken kofta. So instruction also will specify those, right? Which operands I need to need. So it will tell me to go to location 3000 and take this operand. It will tell me to go to location 5000 and take this operand. Okay, so I have to fetch the instruction from the memory. As I go to the recipe book and I see the instructions, same CPU goes to the memory and fetches the instructions. It cannot do anything on its own, right? It's a very dumb machine. We instruct it to do whatever. Your manager instructs you to accomplish a task. Does your manager do the task? No, you do the task. But your manager tells you to do, then only you do, right? Else you don't know. You are very alsi. Okay, so obviously I am the person. I am instructing CPU to do something. So CPU goes to the memory and reads the instruction. So it fetches the instruction from the memory and then writes back some results. It can write back a result or it cannot write back a result. It depends on the instruction. Okay, but generally we talk it is writing back something to the result. It fetches some instruction from the memory from me and then writes back and gives some result to me, gives some output to me. Okay, so that is what instruction that is what a instruction cycle looks like. So instruction cycle have few steps. So first step is instruction fetch. In this particular case, what happens is the CPU retrieves the instruction from memory using the program counter. Okay, before starting this, I wanted to explain one more thing, is that I told you one thing, right? I have a compiler which converts high level instructions to low level instructions. So what does compiler do? Compiler converts the program from HLL to low level language, right? Low level language. Now this low level language is actually stored in the RAM. And my CPU goes and access this RAM. So memory, by memory I mean RAM. CPU goes to the memory, that is RAM, and these instructions are written in low level so that my CPU can understand. That is why compiler is there. Compiler is converting your Python code into machine level language. Then your CPU is going to that language. CPU is going to that instruction that is stored in the RAM, and from there it is doing all this, fetching the instruction. Then it is accomplishing whatever task is required. So your CPU does not directly go to the high level language Python. It doesn't go to the Python. It goes to the RAM. Why RAM? Because compiler converts high level language Python, C++ to low level language machine level 1010, and that is stored in RAM. It stores in RAM. So that's why CPU goes to RAM. So that is one instruction. That is one thing that I wanted to mention. So in instruction fetch, CPU does exactly that. It goes into the RAM and fetches the instruction, and it stores in its own register known as instruction register. As I mentioned in the starting lecture, that CPU doesn't trust everyone. Okay, it goes into the RAM and it takes the instruction, but it directly doesn't follow that. It first stores in the instruction register, and from that we start our process. Why is it like that? Why it goes to instruction register? That we will understand later in next few lectures. Trust me, we will understand that. We'll exactly understand that, and that day you will love it. Okay, but for now just understand this, that your CPU goes to the RAM and it tells me, give me what instruction you need me to follow. It gives it, but CPU doesn't follow it instantly. It then stores it in the instruction register for further processing. So this is what happens exactly in instruction fetch. Okay, inside a cycle, inside a instruction cycle, instruction fetch is just fetching the instruction and storing it in the instruction register. And at conclusion of the fetch cycle, after the instruction has been fetched, what does the CPU do? CPU tells the program counter to increment its own value, because I have fetched the instruction. So program counter always points the next instruction. So as soon as I have fetched the instruction, let's assume a case where I am at a memory of location 100, right? This is the memory, and this is location 100, and this is location 101. So it has some instruction X. So my CPU will go and fetch this instruction. As soon as I have fetched this instruction, my program counter PC will now point to 101. It will point to the next instruction. It is sequential, right? It will point to the next instruction. If I have some branching or something, then I will change the PC value inside the instruction. That will be there. That also we'll learn today. That is interrupt cycle. Okay. So at conclusion, the PC is incremented by 1, and it now points to the starting address of the next instruction, that is 101 in our case. So it is very important to understand exactly what is happening in the phase cycle. Two things are happening. First thing is this. The CPU retrieves the instruction and stores it in the IR, instruction register, using the program counter. So how does CPU know that where I need to go? Program counter has that value. Program counter initially had 100, so CPU will tell I need to go to the memory location where program counter is pointing. Program counter is pointing to 100, so I'll go to that location 100, and I will store this instruction, contents of 100, inside a register known as instruction register inside the CPU. That will be stored. Then this is the first task. Second task is the PC in the same place after it is fetched, right? What we do, we simply increment our PC by 1. That is the task of the instruction fetch. So this is one of the parts. Next, we do instruction decode. Okay, in instruction decode there are many things. Instruction decode is the control unit decodes the instructions stored in the IR to identify the operation, opcode and operands. So we need a decoder, right? Just like previously we had 3 address instruction, 2 address instruction, we had variable opcode length. Someone needs to understand what does it mean basically. What does this instruction mean? Does it mean it is a 2 address instruction or a 1 address instruction? So CPU is the head, right? It is the control unit. It is the manager. It is the manager basically, and it decodes whatever is stored in the instruction register. It decodes. It's basically like a translator. It translates from, if you don't understand Hindi, it translates Hindi to English, whatever the CPU will understand. Okay, and it then sends some signals. Don't worry, control unit is a separate topic itself. We'll study this in the next few lectures. So for now, you just understand that in this phase, instruction decode, control unit is decoding whatever is written in the IR, stored in the instruction register. It understands like what are the operands, what is the opcode, what does it actually do. Okay, that is what control unit does. We will study this later on. Next, after this, we have few effective address calculation. What is effective address calculation? This is also known as addressing modes. Okay, this we'll learn in the next lecture itself. What is addressing modes? Sometimes what will happen, if I have written move R1, R2. Now this can be perceived as many ways. This can be perceived as store the value of R2 inside R1. This is one way of perceiving it. Another way of perceiving it will be store the value of the location pointed by R2 to R1. Oh, okay. So CPU has to do this calculation. Whether I need to go to the memory location or directly store the value of R2. There can be many things, right? This we'll learn in the next lecture. Don't worry about this. So this is the effective address calculation. We have to calculate the address. Exactly address of the operands. Sometimes there will be some time taken to calculate the address of the operands. Operands, I may not be able to get the address operands directly. I may have to go to some memory location. From there, I will be able to get my operand. So this is what happens in the third phase. Then operand fetch. After I know that my operands are located exactly at this location, then I fetch the operand from the registers, memory, or wherever they are present. Then after I get the operands, then I finally do the execution. So here which comes into action? Here my ALU comes into action. Finally ALU has got its input, ALU has got its operand, it has got its input. Now ALU will start performing any arithmetic or logical computations like addition, subtraction, anything, or data transfer. Okay. At the end, obviously the value is stored in the accumulator. Okay, and after, if the instruction states that we have to write back the result, we write it back to some register or memory wherever the user wants. Okay, we write it back. Okay, so let's take an example. From there we'll understand this better. So here we have this example, right? Instruction set architecture, instruction cycle with example. For instruction add R1 and R2. So what it does is we fetch, first of all we fetch this instruction. So this instruction is located, let's say, in location 100. So PC will point to 100 and it will fetch the instruction and it will store it in the IR. So here IR, I will go to memory pointed by PC and store it in IR. The contents of memory pointed by PC, I will store it in IR. Okay. Then what I will do? Then I will identify the operation. So control unit will now decode. What do I need to do? Do I need to do addition, move, whatever I need to do? It is telling add. So I have, what control unit will understand? Okay, I need to add two values that are stored in R1 and R2. That is what control unit will decode. Okay. So here control unit comes into action. After that, effective address calculation. Determine the addresses of R1 and R2 if memory based. So if it is a memory based architecture, right? So let's say R1 has 1000 address stored and R2 has 2000 address stored. So if it is a memory based architecture, if it is indirect addressing mode, that we'll learn in the next lecture, don't worry about it right now. What it will do is that my CPU will understand, okay, I need to go to location 1000 for operand 1 and I need to go to location 2000 for operand 2 to get the two operands, to get the value in the memory R1 and R2 to perform the addition operation. Now it will fetch the operand in the fourth cycle. Fetching the operand means exactly whatever is present in memory location 1000 and 2000, it will fetch that. So let's say in memory location 1000 it is X and in memory location 2000 it is Y. Next it will perform. Now here ALU will come into action, right? ALU will come into action. It will perform the operation, that is X plus Y. Now it will fetch where? It will fetch in the memory data register. Okay, it only fetches in the memory data register and CPU takes input from the memory data register. So here ALU comes into action. It performs the addition X plus Y. Then we write back the result and store the result back in R1. So this is what add R1 R2 is. If you remember, I add R1 R2 contains memory pointed by the R1 R2. Then I store it in R1 itself. Then I write back the result in R1. So R1 will be memory location pointed by R1 R2. I will store this result, right? So these many things happen in a simple addition operation. Simple addition operation. You can see so many things are happening, and this is happening in picoseconds. Okay, very small amount of time. That's why there are so many operations. Okay, so I will give you a visual here, and from there we will understand this better. So first of all, I am doing addition, right? When I am doing addition, initial value of PC is 100. Now I have started an instruction. If I have started an instruction, first of all, CPU will go to the PC program counter and it will tell PC, tell me where is my next instruction located. PC will tell you, okay, it is located in 100. So then what will happen is that this PC will transfer its contents in memory address register. It doesn't go directly. Okay, PC stores the value in memory address register. Then once it goes to memory address register, then CPU goes to that address what is pointed by memory address register. It doesn't trust everyone. Okay, so then CPU will go to echo through the system bus. Okay, CPU knows I need to go echo whatever is written in the memory address register. What is written in the memory address register? 100. So CPU will go here in the memory location, and this, for example, let's say this is 100. It will fetch this instruction. So how it will fetch the instruction? So this instruction will be fetched in the instruction register through the data line. Again, this is only step 1. This is only step 1. Okay, so now this instruction comes back here, goes through the system. Okay, this became a symbol. This instruction will come back here, go through the system bus, and it will go to instruction register. Okay, now the PC value will be incremented. PC will become PC plus 1. So this is just the first step. only the first step. First step is instruction fetch. PC value stored. Next, second, what will happen? Second, the control unit, right? I have not drawn a control unit here. So I will have a control unit here as well, CU, okay? CU I will have, it will go to CU, okay? Next will be, it will go to CU. After going to CU, it decodes exactly what do I need to do. CU understand, okay, I need to add R1 and R2. I need to perform addition operation on two operands, R1 and R2, and they are following indirect addressing. Basically, I have to go to the memory locations that are present in the contents of R1 and R2. So see, control unit decodes this instruction, then it sends control signals. We'll learn about this control signals later on to everything. Control unit send control signals to everything, right? To MAR, to MBR, to everything, okay? So control unit understands, okay, I have decoded the instruction, now I need to fetch the operand. So in the third phase, in the memory buffer register, the data, right, data will be fetched back, okay? I will draw it like this, you will understand this better. Through the system bus, data will be fetched back. Now I will say only I have one memory buffer register. This is just a block diagram. I will have multiple memory buffer register, so multiple operands can be fetched, no worries, okay? So the operands will be fetched in the memory buffer register in the third step. Okay, am I correct? Am I in the third step? Right? Yeah. Sorry, effective address. Okay, sorry. They will not go into the memory buffer register in the third step. In the third step, once CU decodes, it needs to understand where does the operands lie. So again, what we know is it is following indirect addressing mode. So basically, what I will do, I will come here. And again, I will understand what are the addresses of my data. So let's assume these two are the data. So these two data will be stored in memory buffer, memory address register. Okay. Again, CPU will instruct, okay, go to this memory address register location and store the data. So addresses I know of the operands. Now what I will do, I will store the data. I will go to this address memory address register and I will store it in memory buffer register. This will be fourth step. And this will be third step. And in the fifth step, what I will do? In the fifth step, I will perform the ALU operation, right? Fifth step, I will perform the ALU operation. After getting the values, I will perform my ALU operation. Okay. This will execute. This is known as the execution cycle. And from here, what I can do again, I will load where I need to store. In the sixth step, I will load where I need to store the particular data. And again, I will go and store the data in some address on memory in the sixth step. So I hope you understood this visualization, exactly what is happening, right, in a CPU. Okay. So it totally depends, like by how much your PC will be incremented. It depends what type of memory you have, how it is it word addressable or byte addressable. That thing is dependent, and that you will know by how much it will increment. Okay. So I hope you understood this whole point, what is happening. Finally, like as I explained here as well, that at execute cycle, the execution unit will simply execute the ALU, it will add the things, and then again it will store back the results. Okay. So here, like the same thing is written only. Not all phrases are required for all types of instruction. Example, a simple register to register operation like add R1 R2 may not need effective address calculation, because I told you that I was going to this memory location, right? Memory location of R1 or R2. This can be like this as well, that add R1 R2. Just hold on. Add R1 R2. What is add R1 R2? Add R1 R2 means that directly add the contents present in R1 R2. Don't go to the memory location present in R1 R2. So let's say R1 had 1000. R1 had 1000 and R2 had 2000. R1 and R2, they both have 1000 and 2000. Previously what I was doing, I was going to this location, memory location, and then from there I was fetching my operand. But right now R1, I'm directly telling you that R1 is the operand. Okay, whatever content is present inside R1, that is the operand. So if that is the case, how will the instruction cycle be? So first, this again will be same only. CPU will ask the PC to give me the address of my next instruction. So PC will tell you, okay, it will load the value of the memory address register, then memory address register through the system bus goes to the instruction and fetches the instruction where it fetches the instruction in the IR. Okay, and then PC becomes PC plus 1. Then what happens? Then IR, then I have CU, right? Control unit outside control unit. So in the second cycle, like in the second phase, what happens? Control unit decodes the IR instructions and then it sends control signal to all the elements. How it does, we will learn this in like in next few lectures. They will teach when you will study about control unit. Okay, so it sends signals. Then CPU, like CU also understands. Okay, it decodes. Okay, I need two operands, R1 and R2. I need to perform addition operation, and this time the operands are present inside the contents of R1 and R2. So what we do is we go inside R1 and R2. So this time registers are present somewhere around here. Let's assume registers to be present here, right? Here I have registers like R1, R2 and so on. So control unit goes to here and it understands where is my operand. Where is my operand? I don't need any effective address calculation because I know it is inside the register itself. So I will skip the third phase. Skip. Okay. I don't need any effective address calculation because I already know it is inside the register R1, R2. I don't need to know any memory address. Okay. What is effective address? We'll learn about this in the next lecture. Don't stress. If you are not able to understand, don't stress. We'll learn about this in the next lecture. Okay. So now I will skip my third phase. If I skip my third phase because I already know my operands are stored in R1 and R2. I already know this. So directly my CPU will take values from R1 and R2 to memory buffer register. This is the fourth cycle. This is the fourth cycle. And in the fifth cycle, data will go from memory buffer register to execution unit. And in the sixth cycle, I will simply store the result. So it is not necessary that all the 6 different phases will occur in a particular instruction. At max, there can be 6 phases. Okay. It cannot be any more than this. Okay. So that is what it is telling. So phase cycle focuses on retrieving the instruction. Execution cycle includes decoding, operand fetching, executing and writing back the result. So sometimes instruction cycle is also divided into 2 components. One is this phase cycle, which includes only the instruction fetch. That's it. And all the other components, right? All the other 5 steps. Like first is control, like it sends control signals. So it decodes, decoding, then effective address calculation. Then what do you have? Then you have operand fetch. You fetch the operands from the memory or from the registers. Then you execute, you perform arithmetic logical operations. Then you write back. So all these 5 things are inside the execution cycle. All the 5 things are inside execution cycle. So like here I have explained the same thing only at phase cycles. What happens at the start of instruction cycle, the processor retrieves an instruction from memory. The program counter contains the address of the next instruction to be fetched. Okay. Once it gets the instruction inside the IR, then PC increments by 1. The same thing is written only, nothing special. Okay. So again, it is like one thing is there. Now, if there is an interrupt, things will change a bit. What does interrupt means? Interrupt means, let's say you are listening to, like you are watching a good movie. Then your mom came and told you, tomorrow is your examination. What are you doing watching the movie? You tell your mom, okay mom, I have examination tomorrow. So I will study for 2 hours. I will finish my syllabus. Then again, I will come back and watch. So your mom interrupted you that you are watching the movie, but your mom interrupted. So you pause that movie. You went to the books, you studied the books, then again came back and resumed the movie. So that is what an interrupt is. I am interrupting the CPU. First I told the CPU to perform some task, then I am telling in between the operation that no, pause it right now, you need to do this is more urgent. So CPU will store that address, what it was doing, it will store that value somewhere, it will go to that what I am telling it to do right now, perform that operation, perform those steps, perform those instructions. Then after finishing, it will again come back and resume its previous operation. That is what a interrupt is. So let's read this. In instruction cycle with interrupt, what is the difference? The processor fetches the instruction from the memory to the instruction register. Fine. The PC increments. Execution cycle, the processor decodes and executes the fetched instruction. As it was executing the instruction, it got to know after completing the current instruction, the processor, it got to know there is an interrupt signal. Processor checks for an interrupt signal. So control unit sends the interrupt signal basically. That is for other discussion. But somehow the CPU got to know after the current instruction has been fetched that someone is interrupting. Your mom, right? Your mom is with a shoe. Like she wants to throw at you. So you got your interrupt signal. Okay, mom is really angry right now. I need to go and study. So you instantly go and went to study. Okay, you instantly went to your table and you started to study because your mom was ready with you with a chappal in hand. Okay, so obviously you went to study. So that is also CPU also gets an interrupt signal from somewhere. Someone sends it. That is for other discussion. So it gets the interrupt signal. It checks the interrupt signal. If it is high, if the interrupt signal is active, so it will stop everything. It will stop everything, right? Now it will stop fetching the next instruction. What it will do? The processor pushes the current PC value onto the stack. So processor actually stores the current next instruction address, right? It will store it somewhere for later use, for later reference. It pushes in the stack, and what it does it control is then transferred to the interrupt service routine. What does interrupt service routine does? It changes the current PC value. The previous PC value, right, has been stored somewhere. Current PC value, I am changing it to 2000. Previously, PC was supposed to go to the next instruction, that is 1001. But I have updated it to 2000. Now you will follow my rule. You will go to address 2000 and follow that instruction. Whatever is written there, you follow that instruction. Now it somehow completes up until 2004. And then I send a signal that, okay, somehow the interrupt has been over. Then I send a signal, interrupt has been over. Now next, what it will do? Now the CPU, as it has identified, okay, I was on an interrupt, now interrupt has been finished. So it will again resume. How it will resume? I had stored the previous PC value somewhere. So I will take that PC value and update it to current value, right? It will be 1001 now. Okay. I will update the PC value 1001 and then again I will resume. So that is what a interrupt cycle works. Okay. It is different. Now remember, this can be different in different architecture. I'm just giving you an example. Can be different in different architecture. How each architecture handles, it depends, right? It depends how each architecture handles its own interrupt cycle. But I'm just giving you a basic example. Let's see with example. So let's assume that I am starting with, I have 4 instructions, right? I1, I2, I3, I4. I have 4 instructions. Now each instruction is 4 bytes long. So the next starting instruction will be 104, 108, 112. And let's assume that this I2 is the interrupt instruction. Okay. So the PC, what it does we start, then we fetch the next instruction. So PC currently has 100, so we'll fetch this is I1 actually, sorry, this is I1. PC will currently fetch I1 instruction. Okay. PC will currently fetch I1 instruction. Then it will execute. Okay. Then it will execute the instruction. And if it receives the interrupt signal, it will check for it. If it does not receive interrupt signal, it will again go back and start. Okay. Again fetch the next instruction. Okay. It fetches the I2. Once I fetch I2, once I finish I2, right now PC, what is pointing to PC? After fetching I2, what will PC point to? PC will point to 108. PC will point to 108. After fetching I2, PC will point to 108. Okay. So PC points to 108. So if PC points to 108, what does it mean basically? So it means that I2 will be done. Okay. And in between when I do I2, at the end of execution of I2, I receive a interrupt signal. Interrupt signal is 1. As soon as I receive an interrupt signal, what I'll do, I have a stack or some place, right? The CPU knows the architecture. I have a stack. So CPU, what it will do, it will store the this PC value 108 here in the stack, top of the stack. Okay, this is stack. After this, what we'll do? After this, what we'll do is I will go to the interrupt service routine. So let's say interrupt has told me to go to instruction present on address to 200 and 200, let's say 200, right? 200, 204, 208. I have 3 interrupt instructions like I5, I6, I7, and after this the interrupt service has stopped. Like we have stopped, interrupt has been done, we have done the interrupt instructions. So here interrupt signal goes low. Okay, so now my current PC, right, PC after this I2, it will point to 200 as mentioned, as the instruction has mentioned in the I2 instruction, it is present. Okay, so it point to here. So CPU will then decode, like CPU will then fetch the instruction I5. It will fetch I5. Next, my PC will be incremented to 204. This will be my new PC value. Then again, my PC will be incremented to 208. After fetching I6, after fetching I7, my PC will be incremented to 212. Okay, but the problem is inside, after fetching the instruction I7, the control unit understands, okay, my interrupt service routine has been finished. Okay, I need to go back to my previous task, what I was doing. So what it will do is now again it will update the PC value has been updated to 212. Again it will update it to what value? The top of the stack, what was previously stored. It was 108. Now again my CPU will tell where do I need to look for the next instruction. It will go to PC. PC is now pointing to 108. So 108 is here. 108 is simply here. So again I will restart from here. So interrupt is like just like an interrupt, just like the name suggests. It will interrupt, it will perform that task, then again you will resume from where you were. Okay, so instead of in normal instruction cycle, we have only fetch and execute cycle. But if interrupt is there, then I have to add another extra layer, interrupt cycle. So it checks the interrupt. If interrupt is present, we will finish our we will not finish our execution. We will again come back here and do all the tasks that the interrupt has told me. Then when as soon as the interrupt signal goes low, I will again resume from where I left in the previous task. Okay, so that is what a interrupt cycle does. So instruction cycle with interrupts. Why is the PC value stored in the stack? The stack operates in last in first out. Like why is it stored in stack? It can be stored anywhere else. It depends on architecture. Generally, previously we used to store in stack, but it depends on architecture. Nowadays, new computers, they can store anywhere. Why is in stack? Like why we used to store it in stack? The reason being, stack is last in first out principle. It follows last in first out principle. What do we mean by last in first out? So if I have placed 1008 in stack, right? This address in stack. So it knows that next time when the interrupt service routine will be finished, if I pop something out of the stack, that will be the last thing that I pushed in the stack, right? If I would have used Q is first in first out. Okay, it follows first in first out. What will be the problem is that if I put 1008, right? So it was put in there last, but Q will pop the first value. So it will pop the 2048. This is not that important. This is important for data structure and algorithm. If you know Q and stack, that's good. If you don't know, ignore this. Okay. Here also I have tried to explain the same thing only, that what is actually happening. Instruction 2, a interrupt has been detected. As the interrupt has been detected, it will go and do that interrupt. So ISR execution start. So let's say that interrupt address is 1104. Okay. So control is transferred to the interrupt service routine. Then after it is finished, let's say at address 1108, the interrupt has been finished, the program execution resumes. So in this particular thing, right, the PC value will again be 1008 because previously it was 1004. The PC value in this, while I was decoding this instruction, it is the, what is the next instruction after this? 1008. So PC value was previously 1008. It will again be 1008 after finishing the interrupt. That's the basic concept of interrupt. So let's do a few questions on this. With that, we will be able to clear our concepts better. Consider the program segment for a hypothetical CPU, 3 user registers, having 3 user registers R1, R2 and R3. So I'm doing all this, right? Move R1 5000, move R2 R1, add this, move this, and then halt. Okay. Consider that the memory is byte addressable. So don't miss this small details. It is byte addressable with 32 bits. The program has been loaded starting from the memory location 1000. So this is the memory location 1000. If an interrupt occurs while the CPU has been halted after executing halt operation, after executing this halt operation, the CPU has detected a interrupt service routine. The return address saved in the stack will be, what will be the address that will be saved in the stack? What will be the address that will be saved in the stack? Okay, they have told me what does each instruction does and what is the length of each instruction. This has size of 2 words, 1, 2, 2, 1, and it is byte addressable, right? So this is the word size. So what is one word equals to? One word equals to the bits of the processor instruction length, right? So one word is equals to 32 bits. How many bytes? 4 bytes. And it is byte addressable. They have told me it is byte addressable. So these instructions, how will these instructions be stored in the memory? Like this. Let me name this instruction, right? Let me name this as, it has started from 1000. Okay. Let me name this instruction as I1, I2, I3, I4 and I5. Okay. These are the 5 instructions. So if I am starting from 1000, okay, it is byte addressable. So it will be 1001, 1002, 1003, 1004, and I will require more. Why? Because this has only length how much? Byte, 1 byte. This has capacity of 1 byte. But it is telling me that this instruction length is 2 words. So I will need how many bytes? I will need 8 bytes for the first instruction, right? So I1, the length of I1 will be 8 bytes. Okay. So it will go on like this, and until 1007, all of this will be filled up by I1 only, because I1 length is 8 bytes. Okay, so I will fill 8 locations. Okay, it is byte addressable, remember. Okay, so I1 is 8 bytes. What about I2? How it is the length of I2? I2 length is only a single word. Single word is 4 bytes, so it will be 4 bytes. What about I3? I3 is again 1 word, so it will be 4 bytes. What about I4? I4 again is 2 words, that is 8 bytes. What is I5? I5 is 1 word, that is 4 bytes. Okay. So it is telling me that after executing the halt instruction, I encounter a interrupt cycle. So if I am executing halt cycle, that means this halt instruction has been fetched. So where will my PC point to if I have executed the halt cycle? The next instruction, the instruction after this. So how many total bytes I have covered? How many total instructions? So I will cover all the instructions from I1 to I5. So what is the total bytes, number of bytes I have covered? So total number of bytes I have covered is 8 plus 4 plus 4, 16 plus 8, that is 24, plus 4, 28 bytes. So total length is 28 bytes. And what is the location of the last instruction, last byte instruction? It will be 1027. Why? Because I have to take into the factor 1000, right? If I do 1027 minus 1000 plus 1, I will get 28. Why? Because between 1000 to 1027 I have 28 different bytes. You can calculate like simple. You do one thing, 1000 go to 1001. How many bytes I have? 2 bytes, right? 2 bytes, because one is 1000 and another one is 1001. That's why I have 2 bytes. So here also one will be 1000 and other one will be 1027. 28 bytes. But PC, this is the location of the last instruction of the halt, right? But PC actually stores the next instruction to be fetched. So halt instruction has been already fetched. So PC will store the next instruction that to be fetched. So PC will store 1027 plus 1. PC will store this value. After halt, next instruction to be fetched. Okay, so this will be equals to 1028. Okay, 1028. So PC value, if an interrupt service routine has been encountered, it will store 1028. So answer will be option D. Option D will be correct. Okay, this was simple question. We could have done it in seconds as well, but I wanted to explain everything, right? I wanted to explain everything. So I1 instruction, right? I1 instruction. So what is the memory location by I1 instruction? Memory location by I1 instruction is, for I1 it is from 1000 to 1007. For I2 it is from 1008 to 1011. Okay, 4 bytes. For I2 it is from 1012 to 1015. Again 4 bytes. Not I2, sorry, for I3. For I4 it will go from 1016 to 1000 and like 2 bytes I have, so it will go until 23. For I5 it will go from 1024 to 1027. So 1028 will be the last instruction that I need to fetch. Okay, that will be the instruction that I need to fetch basically. So answer will be 1028. So I hope you understood this point. Let's go and then solve the next question. This is again the same question, only few things has been changed here. So consider the following program segment. So it's the same only like the previous program only. It is word addressable. Now they have changed. What if I make a word addressable? Now you'll understand the difference between word addressable and byte addressable. With size 32 bits, everything is same. It is just word addressable. Now how will the instructions be stored basically? So everything will be same, but this will be one word. Okay, and what is one word? One word is equals to 4 bytes, and first instruction has 2 words in it. 2 words. So it will be stored. I1 will be stored in location 1000 and 1001. I will start from 1002. Then I2 will be stored. Look, the length of I2 instruction is only 1. Then I3 will be stored. Length of I3 is also only 1. Okay, like this I hope you understand. So I1 will be stored from 1000 to 1001. 2 words. It is word addressable, right? It is word addressable. That's why I am storing it in words. This is one word. One word is 4 bytes, as mentioned by the architecture. I2 will only be stored in 1002. I3 will only be stored in 1003. I4 will only be stored where? I4 will only be stored, like it has 2 words, right? So it will be stored from 1004 to 1005. I5 will be stored. It is again a one word operation, so it will be 1006. So this is where my I5 will be stored. So the PC points to the next instruction that needs to be fetched. So PC will point to the next instruction, that is 1006 plus 1. It will be 1007. So in this case the answer will be simply A. It will not be D. Okay, so many things change if your CPU is word addressable or byte addressable. So just be careful regarding that. Very careful regarding that. Okay, So let's do this last question of today's lecture. So in this question we have, consider the following program segment, like it's same question, right, which we solved previously. So I've just written down whatever we have solved from the previous segment. Okay, these two questions are new. These two questions are new. Okay, this have been already done. So I hope this question will be more clearer to you. Please go through now, go back, watch the recording again of this question. I hope the understanding of this question will be more clearer to you. Okay, so here what we need to find out, assume that the memory is word addressable. After execution of this program, the content of the memory location 2010 will be content of the memory location 2010. So I need to solve this again. So that is that disadvantage. It would have been better if I would have taken this question here only, but that was my mistake. Okay, so what we were doing is we were looping. Basically we're doing the loop thing. This is not interrupt. So interrupt and loop are different. Okay, so one thing I forgot to mention here. So one thing I should mention, interrupt and loop are two different things. And branching also, and branching, just hold on. What is happening here? Why is it not showing? Something is wrong with this. Branching, loop are two, okay, are different things. What does interrupt means? Interrupt means someone has interrupted you. You will go and finish the task first, then again you will come back. Interrupt means I will do some task and resume my previous task after finishing the interrupt task. Okay, next is branching. What does branching means? Branching directly means it will update. I will go and perform a new task and may or may not resume the previous task. It is very dangerous because control unit loses the control. It cannot track anything. Okay, I may or may not return. I may or may not resume. It is not mandatory for me to resume. Branching means I branched out to some other instruction. I may or may not return. And what is the third thing? Loop. Loop means I am repeating certain set of instructions after if a condition is being met. So if there is a condition and that is being satisfied, then I will loop certain number of times. It depends, right? So here actually loop is happening. Okay, this is a loop. Branching means it totally loses the control, although it is also branching. Okay, but this is a combination of branch and loop. So here we don't lose the control. Okay, I hope you understood the branching difference between branching, interrupt and loop, all these three things. Okay, I just copy and pasted whatever we had done previously in the question. That same thing I just copy and pasted. Okay, so we had only done this 71 question. Now I will solve the 72nd and 73rd question. So in 72nd, what they have told me that it is word addressable, and after execution of this program, the content of the location 2010 will be, what will be the content in the memory location 2010? How will I solve this? So first of all, I see that I already know what this is doing. It is just changing the values of register R1, R2 and some memory values. Okay. So if I like I've already written this in first cycle, what is happening? I am storing on the register R1 the location content that is present on the location 3000. What is present in location 3010? That is already written in the given in the question. 3000 in memory location 3000. I have 10. So I am storing that value. R1 is equals to 10. So then what happens? Then I am in a loop, right? If you remember, I was in a loop. So then R2 was equals to the memory location pointed by R3. R3 initially had the value 2000. So I will go to 2000 and store that value. What is present in 2000? 100. So they have told me from memory location 2000 to 2010, I have content 100. Okay. So all these contents are 100. Now, next what I do, I change the value of R2. R2 is equals to R2 plus R1. R2 is equals to R2 plus R1, that is equals to 100 plus 10, 110. So R1 has 10 and R2 has 100 value. I store it in R2 itself. Then what I do is I go to memory location MR3, that is pointed by R3. R3 is pointing to 2000 and I change it to R2. I update the value. Previously it was 100. Now it has been updated to 110. So this value, right? This 100 has been updated to 110. So in after this, I increment my R3 and I decrement my R1. So R3 goes from 2000 to 2001 and R1 goes to 9. In the next loop, I will again come back here, right? Because R1 is not 0. So I will come back here in R2. So now I will point to memory location MR3. What is R3 now? R3 is not 2000 anymore. It is 2001 because I have updated my R3 in the previous loop, right? So R3 is 2001. I will go at 2001 and observe that it is also 100. So this value will be same only. This will be not changing. This will be 100 only. Then I will add my R2 with R1. What is R1? R1 is not 10 anymore. It is 9. The updated value of R1 is 9. So it will be 100, this value plus R1, that is 9. So I will store this value in R2. Then I will go in memory location pointed by R3. R3 is 2001 now. So I will go to 2001 and update it to 109. This will be updated to 109. And then again, what will happen? Again, I will increment my R3. It will be 2002. And then I will decrement my R1. It will be 8. So like this, I will go on. So exactly what is happening? Basically, the memory contents, as I move along, right? As I go down, it is reducing by 1. So when I will reach 2010, when I was 0, it has been reduced to 0. 110, this is 110 minus 0. This is 110 minus 1. So when I will be here at 2010, it will be 110 minus 10. So it will be simply 100. So your answer, the content of the memory location 2010 will be simply 100. Okay, it will simply be 100, nothing else. Okay, nothing fancy, nothing else, 100. What about the last question? Assume that the memory is byte addressable. If the memory is byte addressable, the word size is 32 bits. So one word is 4 bytes and it is byte addressable. Okay, I am storing 1 byte each. So what it is telling me, it is telling that there has been a interrupt that is occurring during the execution of increment R3. So tell me in the comments below, when I am executing this particular instruction R3, the program counter will point to what address? Will the program counter point to this address, increment R3, or will it point to decrement R1? I am not asking you the exact address. Just tell me what will the program counter point to? Will it point to increment R3 or decrement R1 or the previous one, move R3 R2? Go in the comments and tell me. Okay. So the simple answer is program counter will point to decrement R1, right? Why it will point to decrement R1? Because it is executing this particular instruction. So program counter contains the next instruction that needs to be fetched. I am in the execution cycle now. I am in the execution cycle. This instruction has already been fetched. Increment R3 has already been fetched. That is why it is telling me that I am in execution of this. If I am in execution, then obviously the PC value has already been incremented to this decrement R1. So I need to find out the starting address of this decrement R1 instruction. So let me name these instructions. So this instruction is, let's name this as I1. So this is only telling me that during the first time, when I encounter this during the first time, then what will be the address? Only for the first loop. Okay, after that, again it will resume the loop. So this was the first time. Let's assume this as I1, this as I2, I3, I4, I5, I6, I7. This is 7, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, I have 8 actually. So, okay, it's fine. So, what is the memory location of I1? I1 has a memory location of, we start with the memory location. What do we start with? We start with PC value. Initial PC value was what? 1000. They have told me initial program is loaded from 1000. So I1 initial location is 1000. What is I2 location? I2 is the size of the previous instruction. It is 2 words. So how many bytes? One word is 4 bytes. 2 words means 8 bytes. It will be 1000 plus 8 simply. Because this will be from 1000 to 1007. So this will be from 1008 to how many? 1 word only. So 4 bytes to 1011. Okay. What about I3? I3 is this instruction, that is add R1 R2. Okay. So this instruction is again 1 word size. So this will be 1012 to 1015. Then I4, this is again, all these are 1 word instruction, right? So I can take a sigh of relief. Until decrement, all these are 1 word instruction. So I4 will also be from 1016 to 1019. So like I will point everything. This is my I1, this is my I2, this is my I3, this is my I4, and my I5 is going from 1020 to 1023. This is my I5, and that is what I require, right? I require, okay, no, I require I6 actually. So what will be the starting address of I6? Starting address of I6 will be 1024 to 1027. It is 1 word, right? So 4 bits. So starting address is 1024. So my PC will point to this. If I have a branch, right? If I have a interrupt, the PC will point to this. Then what I will do? Then what will happen? PC will push this value, the CPU will push this value of PC to the stack, and then it will go to the interrupt. Wherever the interrupt, it will throw the control to the interrupt. It will fetch the instructions according to the interrupt. So PC will push this value to the interrupt. So 1024 will be pushed into the stack of the interrupt. So answer will be C, 1024. So this is a very, very beautiful question. If you couldn't understand, please go through this analysis again. You will be able to get it. I hope you will be able to get it. Now I think most things are clear. What is happening? Even the first question, right? 71 question is also clear, because there I didn't explain what is instruction cycle. I explained it at the end. Okay, because they are so much interrelated, so I cannot teach everything at once, and if I don't take a question at that point of time, then that concept won't be clear. So that's why I have to take this question. So this is a very, very interrelated subject. So yeah, that's it basically for this lecture. Okay, in the next lecture we'll learn about addressing modes. So next lecture will be totally about addressing modes. Thank you for watching, and I will see you in the next lecture. Until then, happy learning. Hey everyone, and welcome back to my channel. I am Manish, and today we'll start with a new topic of our computer organization and architecture subject. So today we'll start with the addressing mode. What do I mean by addressing mode? Because I know I have given you few hints in the previous lecture that our instruction length consists of a opcode which tells what instruction to do. Then it consists of operands, right? Address of operands. Now those operands, right, are what how will I get that address, right? I had a opcode here, and then I had then I had address 1, address 2. Now what do these addresses mean actually? What do these addresses mean? Are these addresses to the operand, or these are something else? That we will study in today's lecture. Because obviously we cannot study everything in one lecture. We need time, right? So slowly we are decoding everything, uncovering, discovering everything. So what are addressing modes? Addressing modes specify how and where operands are obtained for an instruction. So if I have an instruction, right, and this address 1 and address 2 is there, this address 1 and address 2 by itself is just an address. Okay, I don't know what to do with this address. This mode 1 and 2 actually will tell me, are these addresses actually pointing to a content, okay, or these are something else? Are these pointing to some effective address, and that effective address will point to the operand? I don't know. That will be defined by mode 1 and 2. They determine the method of accessing data or the memory location involved in the instruction. Addressing mode is a method used to determine the effective address of an operand. What do we mean by effective address? I will mention effective address by definition refers to the actual memory location of the operand. Let's take an example, okay? Let's take an example. If let's say there is opcode and there is A, and this A value is 2000. First of all, what does this 2000 mean? I don't know. Okay, it may happen that this 2000 is the address to some other address, and this address is called the effective address, which contains the address of the actual operand that I actually need to perform operations. So it's a tongue twister. This address is the address of the address of actual operand. Okay, so first I have 2000 points me to this, and in this location the content present, this is actually another address that is pointing to the actual operand. Okay, so we can actually get the operand in many ways. There can be many modes. Okay, this is one of the way. This is actually precisely called indirect addressing that we'll learn in today's lecture only. We'll learn on this today's lecture. There can be many modes. This A can be directly 5. Okay, and this can be directly the operand. I don't need to go into any address. This is directly the operand. Okay, that can be also possible if I specify mode, something like that. Okay, so we'll see all those things. We'll see. So mode decides what is this value. Mode will decide. Addressing mode will decide exactly what does this value, what is the meaning of this value. Just like opcode tells me what operations to perform, mode tells me what is the meaning of the value. Okay, is it an address? Is it an effective address? Is it the operand itself? What is it? Okay, now in few architectures this mode may not be present because it is fixed. That architecture has fixed that this thing is what it has been already defined. Okay, in that architecture, that's why they don't have any mode. Few architectures may have that. Just like you had 3 address architecture, 2 address architecture, 1 address, 0 address. In 0 address architecture, if I write some instruction, it already knows from where to get the operand and from on where to store the result. It already knows that. So if I don't have mode, it has already known what does this address mean. It is already knowing that. Okay, so I hope you understood. All of this depends on the CPU architecture. This addressing mode depends on the CPU architecture. Depends on the CPU architecture. Okay, now what does this addressing modes provide us? This addressing mode provides us flexibility. Okay, because sometimes you want your operand directly, you will write your operand directly here. Sometimes you will say that my operand is in some memory location, go to that location. So it provides flexibility. As many modes we will have more flexibility. Okay, so modes provide us flexibility. Just take the example in your own programming language. You have many modes, right? You write int a equals to 5. You can write this as well, right? Int like I have a value variable. So I will first I will this is one way. This is one way. Another way to write the same thing only. I will first declare int a. Okay. Then what I'll do? I will have a pointer P that has the address of A. I store the address. Then what I'll do? I will do star P equals to 5. Is this accomplishing the same task? If you know C programming, you will know it is accomplishing the same task, right? What does this P has? This P has the address of A, and if I do star means go into this address, and if I go into this address, then if I equate that with 5, whatever this that address will be loaded with value 5. That is what it is doing. It is simply doing A equals to 5. Same thing only. So as a programmer, you have options, and you know how important options is, right, in world. It is very important to have options. Okay, not like that, like one boy has many girls. That is a different conversation. Okay, then it is a bad option. Sometimes having many options is a bad thing. Sometimes having more options is a good thing. Okay, it depends from what perspective you are seeing it. Okay, so programmer always wants an option. So he will get an option here. Okay, we want options. That's why mode provide us flexibility. We get more options. So slowly we'll understand like what are each addressing modes. Okay, so actually what happens in addressing mode, during the phase cycle, the instruction is fetched from the memory to CPU and loaded into the instruction register. This we already know. Then the program counter loads the address to the memory address register that is being then fetched by the CPU. Program counter holds the address of the instruction which is moved to the memory address register. Then then what we do, we load the instruction on the data line according to this address that is present in the memory address register, that is being loaded into memory buffer register, or also known as memory data register. This is also known as memory data register. Okay, then memory buffer register to instruction register. So what happens is, then again the like this is telling the phase cycle only. Okay, why is this here actually? Okay, yeah, this telling. Then what happens is the instruction has been fetched to the memory buffer register, that then is being copied to IR, instruction register. The fetched instruction is transferred to the instruction register. This I have taught, right? I have taught already this in the previous lecture. The instruction typically consists of an opcode and an addressing mode. So this is why the control unit comes into the picture. Control unit decodes the opcode, what instruction it needs to perform, what operation it needs to perform. Also it decodes the addressing mode, whatever values, right? This address 1, address 2 I have given. What is the meaning of this? Okay, what it means? Is it a effective address? Is it a operand? Is it a address of a operand? What is it? So here my control unit comes into the picture, right? Control unit decides this. Okay, now during the execute cycle, the CPU decodes the instruction and determines the, not here, sorry, so here during the execute cycle only decode happens. This is only the phase cycle, correct? So and the addressing mode, and determines the addressing mode to locate the operand or data needed for execution. So obviously it will decode and it will understand from where I need to load the operand. Is it an effective address? Do I need are the operands directly given in the instruction itself, or I have to go to some, are the address which are given, they are actually locations, memory locations of the operands? What are these? Okay, so we need to understand this. So there are many types of addressing modes, so we will understand these one by one, don't worry. Okay, at the end I will take an example where I will use all the addressing modes. Everything will be clear, don't worry, just listen to me carefully. Okay, just listen to me one by one. So first addressing mode is implied addressing mode. What does implied addressing mode means? The operand is implicitly defined by the opcode. What does it mean basically? Here, right, if it is implied addressing mode, that means the operand is implicitly defined. I don't need to provide any address as well. That is what implied means. Implied means it is already implied in the opcode. If there is an operation like increment of accumulator, does increment does INC need any other address? By definition, CPU already understands that INC means it is talking about accumulator. I don't need to go to any location or something. INC means it is talking about increment the accumulator. CPU already knows the address of the accumulator. CPU has that information. It doesn't need any address. So this is implied. No need. Implied meaning operand is implied in the instruction. Operand is implied in the instruction. There is no need for me to go somewhere and search for the operand. The operand is implied in the instruction. This means simply me increment the accumulator. I don't need any extra information. Just this opcode is enough. This opcode is enough. Okay. What about immediate mode? What is immediate mode? The operand is given directly in the instruction. So here this operand, right? I directly give it. I don't give the location. I directly give the operand. What does it mean? Let's take this example. Move R1 5. That means exactly what it says. Move the value 5 in R1. Okay. I am directly giving this value. That's why immediate. I'm immediately giving the value of the operand. I am not telling it to, okay, go to this memory location. There will be the operand present. Okay, hide and seek. No, I am not playing hide and seek here. I'm directly giving it the value. I am not playing any hide and seek. Okay. So that's why immediate? It is very fast. Why it is very fast? I don't need any memory access. Whenever, just know this basic thing. Whenever I have to access the memory, it takes me time. Okay, because I have to go to that location, because the signal has to travel through the bus and directly go on the data bus, right? It is time consuming. Memory access is time consuming, but I am directly providing the value, so I don't need to go to the bus and all those things. I am getting the operand directly on the instruction. Okay, so immediate, reason we call it immediate, no memory access required. Okay, next is direct mode or absolute mode. What is direct or absolute mode? So direct, like this, generally I will give you an example when this is used. Generally used to initialize any register or memory address. Okay, memory location. So generally this is used to initialize any memory location, any register. Okay, I can do the same thing only, memory location or register. Like I'm initializing it with value 5. Okay, that is what it is being used. Then is direct mode or absolute mode. What does it mean? Direct mode means the address of the operand is specified explicitly in the instruction. So this address actually means the address of the operand. Whatever, like this, that is what address means, right? Address of anything. This is the address of the operand. So address is explicitly provided in the instruction. I don't provide the operand in the instruction. I provide the address of the instruction. So obviously I need memory access. So this will be slower. Okay, let's just take this example. Move R1 2000. I will not directly copy 2000 to R1. No, this means I will go to the memory location 2000. So this is my memory location 2000. So after going to this location 2000, I will have some value, let's say 10, and this 10 value will be my operand. This 10 value is actually my operand on which I will do some arithmetic or logical operation. Okay. So that is what direct mode of addressing means. Next is indirect mode of addressing. Now what is indirect mode of addressing? So indirect mode of addressing is the most interesting one. Okay, so it plays hide and seek with you. It wants to play hide and seek. So what happens? The address of the operand is specified indirectly through a register or memory location. What does it mean? It means move R1 M1000. Move the value at the memory address stored in 1000 to R1. So actually what happens, like this is still not not correct. Actually this is still not correct. Here I can explain this better. Is that if I have something written like this is not, let's write it only 1000H. If something like this is written, what does this statement mean if it is indirect mode? So let's first assume few things. First assumption is this is my memory, and at location 1000 I have some value 100, and at location 100 I have some value 7. So what does this instruction means if it is following indirect mode of addressing? Basically it means that I will go to this 1000 location, and this 1000 location actually contains the address of the operator. It is not the, like it is if I go look into the content, it is not the operand itself, it is the address of the operand. So this contains, this is actually the contents of 1000H is the address of operator. So why am I telling it is playing, or not operator, sorry, operand. Whenever I say operator, it's just operand. It's just a like fumble from my end. It will be operand. So why am I telling it is playing hide and seek? Because this, right, I have told you previously, this is supposed to be address, but this is address of a address. This is also address. This is address of what? Address of the actual operand. And this 1000 is what? This is the address of operand. That's why it is playing. That's why it is playing hide and seek. Okay. So we have a technical name for it, that is known as the, like, this is known as address, and this is known as the effective address. What does effective address means? The final destination which actually stores this, right? This is the actual address of the operand. That's why this is known as the effective address. We have a name, effective address. So what is this address? This address is the address of the effective address. This address is the address of the content where effective address is stored. So that's why this is 1000. I hope you understood. Like, it's very difficult to me for me to speak and say, explain all this. I hope you understood. This is known as the, this is also called as the effective address. Okay, this is also called as the effective address. So let's do here, right? This is very, very slow because I have to do two memory access. First, I will access this memory location 1000. This is again not the operand. This is just the address of the operand. Again, I will access location 100, and finally I will get my operand. Correct? So I had to do two memory access. So this will be slower. Obviously, it has also its own use case that we'll understand later on. Okay. So that is what it is written over here. So this address, right? This address will point to this particular address, which will contain the effective address, which will be the address of the actual operand. That is what is written. Now, the CPU must perform two memory access to fetch the operand, access the memory location to get the effective address, then access the effective address to fetch the operand. So this is slower, okay, and commonly used for implementing pointers in programming. Okay, this type of addressing mode is actually used whenever you are declaring a pointer. Then this type of addressing mode is used, that is known as the indirect mode. Now there are few variants of this indirect mode. That's it. What is the first variant? First variant is this register indirect mode. Why is it called register indirect mode? What is wrong with this? Sorry, this is wrong, right? I think this should be register direct mode. Yeah, sorry, this should be register direct mode. Like sometimes what happens is we directly call it register mode. Sometimes it is called directly register mode or register direct mode. Register mode is in itself register direct mode only. What does register direct mode means? The operand is stored in a register. So if I add R1 R2, what happens is add the contents of R2 in R1. Basically, whatever the contents of R1 R2 I have, that I will add. Okay, so this is not indirect, this is direct. So this, right, this directly is the address of the operand. R2 is some address, right? It is address of a register. It is the address of operand. R1 is also address of operand. Okay. Next is this register indirect mode. What does it mean? The address of the operand is stored in the register and the operand is accessed indirectly. Again, this is the indirect mode. So what happens if I say move R1 R2 here, right? If I say move R1 R2, what happens is if I write here move R1 R3, not memory. If I write, okay, sorry. Move R1 R3, what does it mean? So R3, I will take an example here. Let's assume this is R3, right? This is R3 and R3 has this bit stored 1010. So I will go to this address 1010. Now this address will have another value 200. Then I will go to this 200 and this 200 is actually the address of the actual operand. Okay, again the effective address concept. So the register contains the address of the effective address. So that is the definition. Okay, the register contains the address of the effective address. Okay, one thing you have to understand that getting the data from register, right, will be very fast. So it will be a bit better than the direct this mode, right, this mode, because here, right, I actually need only almost one memory access. Why one memory access? Because accessing the data from its own CPU register, right, is very faster. So it will not take me much time to access this particular address, this address. Okay, so here this will be faster. I will write here in small space. This will be faster than normal indirect mode. Why this will be faster? Because here we will require only one memory access. Why, sir? Why you will require only one memory access? You told here, sir. You are accessing memory here. You are going to this 1010, right? This 1010 is the register address. This 1010 is the register address. You are telling, sir, this 1010 is the register address R3. Okay, address of R3. You are going there, accessing this memory location. So it will take you time, sir. Why are you telling it will only take one memory location access? This is the memory access that I am doing, accessing the memory location to 200. Why are you telling this is ignored? This is ignored because this is inside the CPU, right? There was a block diagram inside the CPU had few general purpose register. That was the purpose of this. Okay, that was the purpose, to reduce the time. So accessing a register is very fast to the CPU because it is inbuilt with the CPU. It is inbuilt with the CPU. So sometimes we use this. That is the only reason. Okay, that is the only reason we use this, because it becomes very faster. Accessing data becomes very fast with indirect mode. Okay, because there are only few registers, 64, 128 or 1000. That is very low compared to the number of registers or number of address locations for memory. Memory have gigabytes in data. Register are in megabytes. Okay, I'm just giving you an example. So register. Let's just giving you an example. It can be gigabytes as well. I also don't know, but it can be anything, right? But it is lower. That much is sure. Register will be in megabytes. If register is in megabytes, then your memory will be in gigabytes. Just like your hard disks and all pen drive, right? Those things are in GBs and TBs. Memory in memory in gigabytes. So I require more address lines here. It will be more slower. So accessing register is faster. That is the purpose. That is the purpose of register basically. That's why we use register. Okay. So whenever this register name comes up, right? This is actually this third component will always be a register. Okay. Now let's understand, like in register indirect mode, I've explained this further actually in register indirect mode. In register indirect mode, the address of the operand is stored in a register. Address of the operand is stored in a register. The CPU accesses the register to receive the effective address. Actually here, this is a bit wrong. This is wrong. Register indirect mode, the address of the operand, the effective address. The effective address of the operand is stored in CPU. Okay, the effective address of the operand is stored in CPU. The CPU accesses the register to retrieve effective address. Now this access is very fast. This access is very fast. CPU accessing a register, its own register, is very fast. This is very fast. That's why I all told mainly one register access is required. Then it accesses the memory location corresponding to the effective address to fetch the operand. Instruction length is shorter than other addressing modes. Like instruction length will also be shorter. Why will instruction length will be shorter? Because address is stored in register instead of being specified in the instruction. So I can make a shorter instruction length. Let's say in the memory I have gigabytes, like 1024 or 1 TB or let's take this example only, like 10 GB of memory, right? How many address lines I will require? You will calculate. You can calculate the number of address lines if it is a 16-bit processor. You can calculate that. We have learned that, right? So the instruction length will increase because I have to provide the address location there. But if I use indirect addressing mode, I can store that address on some register, and from there I can get that address, right? So like that, I can reduce the instruction length. So that's why we use sometimes indirect addressing mode. That is the that is the advantage of indirect addressing mode. We can reduce our instruction length. This is one of the advantages. There are many advantages. This reduces the size of the instruction, saving memory. There are many advantages. This is one of them. So here the same thing only I have told. Memory access requirements. One register access to get the effective address. This is in the order, I'm just giving you an example. This can be in the order of nanoseconds. And one memory access, this can be in the order of 100 nanoseconds. Memory access requires more time. Okay. Register access, it's just with the CPU itself, so it will require less time. So if I add total time, right, it will be almost equals to 101 nanoseconds, which is almost equals to 100 nanoseconds. So overall, I only required one memory access. Previously, I was accessing the memory twice. So that time was 200 nanoseconds, and it makes a difference. It makes a huge difference. Okay. So I hope you understood this concept. So this can be compared, this register indirect mode. I can compare register indirect mode, and direct mode of addressing, right? Direct mode, just in the second, I think it was in the third direct mode of addressing, where I need one memory access in terms of memory access and time required are almost same. Okay, it is almost similar. Okay, so we can use this register indirect instead of direct mode to reduce our instruction length. That is the advantage. So next few addressing modes are there. One is auto decrement increment mode. This is what, as the name suggests, it automatically increments or decrements something. The register is incremented or decremented automatically after accessing the operand. Okay, operand will be in sequential data. So what will happen is, if I have move R1 R2, what it will do, it will simply what it will do, it will increment the R2. So okay, it is a sequential operand will be a sequential data. So what it will do is auto increment, move R1 R2. So what it does is, first, like this is also address. This is also address of some register. What it will do? First, it will add that this is a post increment. So what does post increment or pre increment means? Post means after. So this plus, right, is after R2. So first, what I'll do, I'll go to the location R2. Go to this location that is being pointed by this register. So R2 currently is, let's say R2 currently is 1000. Okay, I will go to this 1000 location. This is my 1000 location, and I will fetch the operand. This operand I will fetch in R1. So R1 will be now operand 1. Okay, then what I will do, I will increase R2 to R2 plus 1. So R2 will become now 1001. What about the second option, auto decrement? Like first, let's learn about post and pre. So this is pre decrement, as minus sign is before R2. So here what I will do is, first of all, I will reduce R2 by 1. So R2 will be reduced, R2 minus 1. R2 will be reduced, okay, to R2 minus 1. So R2, initially it was 1000, it will be reduced to 999. And then R1 will be equals to memory pointed by R2, that is equals to memory 999. So I will go here at location 999 and check whatever operand is present. This may be operand 0. So this will be because let's assume that it is operand 0. So this value will be stored in R2, R1, and after that program has been finished. As the name suggests, pre means before, post means after. Exactly what is written here. Post increment or post, like this can be post increment or decrement. I can write here slash decrement, or this can be increment. Okay. First do the operation using effective address, then increment the address. That's why this is post. After doing operation, post I increment, just as I did in the first option. And in the second option, pre increment or decrement means first decrement the address or decrement or increment. First do operation, increment or decrement, whatever the instruction suggests, then you go to the address. First do operation, okay, this right, sorry, this right. I can do this thing. Better would be, I will keep this here. Okay, and this right, this will be actually, okay, just move this here, this can be actually, this can be here. Whatever operation they have mentioned. So now this sentence is correct. So first you, pre means first you do that, then you compute the effective address, or post means after. Next, these two addressing modes are the most interesting and difficult ones to understand. Okay, this one is indexed register mode. In indexed addressing mode, the effective address of the operand is calculated by adding the base address from the instructions address field to the value stored in an index register, mainly used to access a single element of the sequential data. So this is actually used mainly in arrays. Okay, you can assume this as arrays, right? What we do is, when I write move R1 10, the instruction inbuilt, it already knows some base address. So base address is defined as 1000. So what this instruction will do, this one, right, this 10 is actually not any address. This is just the index, just like index of an array. This is the index. So what it will do, it will add with the base address this index, then it will go to this location, right? Let's say this is 1000, so it will go to 1010, and it will fetch the operand 11 from that. So like finally the operand will be operand 11. So operand 11 will be stored. So how is effective address calculated? Effective address is calculated base address. We'll get this from the instruction. Don't worry about this. We'll get this plus the index register value. Okay. If let's say this is written as move R1 R2 and addressing mode is provided to be indexed addressing mode, then let's assume R2 has the content as 2. So then where I will go? I will go to base address, that is 1000 plus 2, that is 1002, and fetch this operand. This is my effective address. Previously this was my effective address. Now this is my effective address. This is pointing here, right? Operand 3. So operand 3 will be my operand now. Okay. So that's simple. We just simply add the base address with the index. That is the only thing that we do to calculate the value of effective address. Let's understand this further. So like it is written here, whatever I explained, that is written. The instruction provides the base address. Instruction has the base address. The index value is retrieved from the index register or from here, from the like in the third component. Then the CPU calculates the effective address by adding the base index address plus the index register value. Memory is accessed at the effective address to fetch the operand. Only one memory access is required. Here only one memory access. So because base address has been already specified in the instruction itself, or somehow it knows the base address. Okay. So like that. Does not support relocation. So what does relocation means? The base address is hard coded in the instruction. We cannot change it. So when the program is executing, in that time frame, I cannot change the base address. So that is a disadvantage of this indexed based register mode. So it does not support any relocation. If the memory layout changes, the base address of the instruction must be updated. What do I mean by memory layout? You don't have to worry. It is about OS, operating system. Okay, you don't have to worry. So that's why this is the disadvantage of this. Okay, let's see an example here. If I have written move R1 2000 R2, so this 2000 R2, right here, right, we write R2 only. 2000 is inbuilt in the instruction, that will be somehow encoded in the instruction. Okay, so R2 has, let's assume R2 has 10 value, right, and base address somehow from the instruction I got to know it is 2000. So effective address will be 2000 plus 10, that is 2010. Operand will be fetched from the memory location 2010. Okay, so yeah, so this base address can be provided from the mode as well, right? It can be anything. It depends on the it depends on the CPU architecture. It can be anything. It can be present on the mode. It can be present anywhere. Okay, it totally depends on the architecture. Okay, so yeah, that is the thing about this. Key points: efficient for array handling. So this is using the concept of index based handling, and it is sequential data, so that's why it is efficient in array handling, where the base address is constant and the index changes dynamically. Index here changes dynamically because I can change the index, right? Base address is constant. What address I need to access, that I can change dynamically. Not suitable for systems requiring relocation, as the changes in memory layout need modifying of base instruction. You can skip this. This addressing mode is widely used in programs with array or table operations, because index, right, bit of index, number of bits for index will be very lower. Actual base address may be 10,000, so number of bits required to express this location is very high. But index can be 10, it can be 50, it can be 100, so number of bits lowers. So I reduce my instruction length. Instruction length reduces. Okay, so next addressing mode is the PC relative or position independent addressing mode. This is the changes the disadvantage of the previous mode. What is this? In PC relative addressing mode, the effective address is calculated by adding the current value of the program counter to the offset specified in the instruction. So this is very difficult, right? So PC actually contains the base. Now PC actually contains the base. Okay, PC actually contains the base value, base address of the instruction, and this third component is the offset. So what will be my effective address? My effective address will be PC plus this value, index, or we call it offset. Okay, so this is mainly used for branching. Okay, mainly used for branching. So just hold on a second, I will check if everything is recording. Yes, everything is recording. Yeah, I just wanted to check. Yeah, everything is recording, it is fine. So why is it mainly used for branching? Because in PC, right, PC actually only stores the instruction register address, right? Not instruction register, it stores the address of the instructions. So we cannot use it for simply memory access and all those things. We can, but we still don't use it. Okay, so this time the effective address is actually not called the effective address, it is called the target address. It has a new name, target address. What is target address? target address is the location of the instruction that needs to be fetched while branching. We'll understand this with the example. Okay, that will clear our understanding of this. Okay, so here I've written used mainly for branch instruction where the next instruction to execute depends on the condition, on a condition like branch if 0, branch if not 0, something like that. So here effective address, or also known as the target address, is PC plus offset value from instruction address field. Okay, it is suitable for position independent code because it depends on the PC value and not some hard coded instruction. It is like PC can change, right? PC can change, PC value can change. EA is relative to the current PC value rather than absolute address. This allows relocation without requiring modification. Okay, this code is used for intra-segment branching, meaning branching within the same code segment. What do I mean by this? I will explain later on. Just understand this is used for intra-segment branching. No additional memory access is required for effective address computation because I'm directly accessing the PC. Branch taken. The CPU executes the target instruction located at the calculated effective address. Okay. If branch is taken, CPU will execute the target instruction. That's why it is called as target address or target instruction. If branch is not taken, then CPU next, it will follow the next sequential instruction. Okay. PC is updated accordingly. So let's take an example from here. We'll understand this. Before execution, the PC holds the address of the next instruction to be fetched. PC before. So let's say I am currently executing. It is a byte addressable memory. I'm currently executing the instruction 1000. So what will the PC hold? PC will hold 1001. PC will hold 1001, right? PC holds the address of the next instruction. If I am executing 1000, it will hold 1001. But in this instruction, I have told to branch relative to a offset. This instruction itself contains a value that it is written that jump JMP to offset 10. What it will do? It will go to a target address that is initial PC value plus 10. What is PC value plus 10? 1010. So what it will do is it will update the PC. Now PC will be equals to the target address. I will update the PC. So I was supposed to go to 1001. Now we'll go to 1000. It is unconditional. There can be condition. If condition is met, I will follow. I will update the PC. If condition is not met, I will not update the PC. So that is what it is written. So if PC is updated, right, then after the execution cycle finishes, the next fetch cycle will start. As soon as the fetch cycle starts, CPU will tell, please PC tell me the next instruction location, and PC will tell, here is your next instruction location, that is 1010. It is not 1001 because PC has been updated during the execution cycle of the current instruction. Okay, I hope you got the point. Same thing is written. During instruction decode, the CPU recognizes a branch instruction. Offset from the instruction is added to the current PC value. Okay, I'm sorry. This will not be 1000, right? I'm sorry. Currently PC has what? 1001. So this value will be 1011. 1001 plus 10 is 1011. So it will go to 1011, not 1001. So effective address will be PC before, that is 1001 plus offset, that is 10. Now there will be some condition. If there is no condition, it will directly branch. If there is some condition, it will check the condition. If the branch condition, I will give some condition. Okay. If a greater than 0, then you do this in C code, right? Exactly that condition, those type of condition I will give here. If some condition is met, it will branch. If that condition is true, it will branch. The PC will be updated. PC will be updated if this condition is true. Just hold on. Okay, this PC will be updated if this condition is true. If the condition is not true, if it is false, if it is true, it will follow. If it is false, it will not follow. PC will be same, will not change PC, no change, will not change anything. If it follows, then I will update the PC. If it doesn't follow, I will not change anything. Exactly that is written. The PC is updated to effective address and the branch is executed. If condition is true, if condition is false, PC moves to the next sequential, what was previously there. Here, my PC is basically PC before. I don't do any changes. Here, my PC becomes target address, right? New PC. It changes. So like some example is also given here. So assumption, current PC is 105. Okay. If current PC is 105 and executing instruction, this is wrong, right? I should be executing instruction at 104, right? That's why the current PC will be 4. Sorry. So currently I'm executing this instruction 104 and it contains, like it will contain the next location of the next instruction, right? 105. So at instruction at 105, sorry, this is right, this is the thing, right? Instruction at 104 is a branch. Instruction at 104 is a branch instruction with an offset 4. So what it will do is it will add effective address will be PC plus offset, that is 105.4 plus that is 109. So it will check the branch condition. If it is true, if the branch is taken, if the condition is true, then the CPU executes the instruction of address 109. Okay. If the branch is not taken, that is condition not true. This is not true or false. And if this is if true. If the branch is not taken, CPU will execute the next sequential instruction, that is 105 only. It will not change the PC. Sorry, this is wrong. This should be 105 only. It will not change anything. Okay. So that is what a PC relative mode does. So the address of the instruction to the branch is called the target address, as explained. There can be positive offset or negative offset. So generally, like there is some mnemonic to this. If it is a positive address, I am going forward. That's why it is called a forward jump. If it is negative offset, then it will be backward. I'm going backward to the instruction. So that's why it is a backward jump. So this will be only executed if a certain condition is met.
Advantages: reduces instruction length by avoiding absolute addresses. So instruction length has been reduced because the address is directly stored in the PC. Okay, I don't need to write it in the instruction. Enables code that is independent of memory allocation, because I don't have any memory allocation here, right? I don't have any memory allocation. I have memory allocation. It totally PC value. I'm getting the address from the PC, and PC is memory independent. Okay, and previously I told you that this is intra-segment branching. What does intra-segment branching means? In OS, there are many processes. In OS, there are bunch of processes. One process is here, one process is P1, this is P2, this is P3. And each process has its own PC and has its own all register. So that OS decides that those things are decided by OS. So I can only branch within this process. Okay, I cannot branch from here to here. I cannot do that. Like, let's say in your computer you have Chrome opened and Microsoft Word. Yes, they can interact with each other, but generally if I am doing something in Word, right, I cannot instantly, that process cannot be instantly copied to Chrome. There are a few things that we do, but in general they are independent of each other, just like here. So I can branch only within this block of memory which the OS has allocated. I cannot branch from here to some other process. I cannot do that. Okay, what you know is like you are interacting with Chrome and Word together. That is a high level stuff. We don't need to learn that. That is a very complex thing. Okay, but generally it is intra processing. That means I can only talk between process to process. I cannot go from process P1 to P2. If you couldn't understand this, skip this. It's not important. This is only important for people who understand operating systems OS. Okay, so this is the 9th addressing mode. Next we have is as the base addressing mode. What does base addressing mode means? It is nothing that previously I was giving the base address hard coded in the instruction. Here the base address will be present in some register. That is the only difference. The base register mode, the effective address is calculated by adding the value of the base register to the offset value in the addressing mode. So used for branching between segments where base register provides the starting address. So here I will have a base register that will have a base address. Okay, I will have a base register that will have a base address. What do I mean? Previously, I previously hard coded in the instruction what is my base address. Now I am telling you I have a register that stores the base address. That is the task of the register, to store the base address. And this is this has intersegment branching. Why this has intersegment branching? Previously I told you that all these three processes, right? These three processes will have its own PC. They are three different programs. So each program will have its own program counter. Okay. I'm going to complex things now. Okay. If you couldn't understand, you can skip this. Each program will have its own program counter. Okay. And they are independent. So this will have PC1. Just hold on. This will be PC1. This will be PC2. And this will be PC3. So when I say that add the base address with the offset, I can either do this operation PC1 plus something, PC2 plus something, or PC3 plus something. Okay. So I can only move along this process, right? PC1, like this process can take up so much instructions, like 1000 or 2000. So offset I will give 100. So I will only be flowing in this process P1, PC2 and PC3. So my base address is dependent of program counter, and program counter is different for different programs. Chrome will have different program counter, and your Word will have different program counter. Why? How? The operating system does it like this. The operating system is the god. Operating system decides Chrome will have a different program counter, Word will have a different program counter. Operating system is the god. Okay. If you couldn't understand, skip this because you haven't studied OS. Okay, you can skip this. So here in this, right, in this PC relative mode, actually what happens is that if I read this, that why it was here, right? Intersegment. So here base address is decided from PC. Base address is decided from PC, and PC is program dependent. So I cannot jump between programs. So I have a disadvantage. This is not flexible enough. So I need to jump between programs. You want so many features, sir. So to give you that feature, we have this mode known as base register mode, where base register mode can store any address. Okay, any address. So I can give any address. I can give base register mode. It can store any address. So my base, right? This time my base address can be
equals to PC1 value equals to PC, or it can be PC2, or it can be PC3. Okay, sorry to close this. Or it can be PC3. It can be anything. So I can write PC3, right, as my base address. So I can, if I am at PC1 and I write my base address as PC3, I can branch between programs. So that's why it is intersegment branching. It is used for branching segments where the base register provides a starting address. So I can branch between programs. I have just given you analogy. This is not completely theoretically correct. Okay, don't come into the comments and say me that you are saying this theoretically wrong. I have just tried to give you analogy. Okay, the main concept you should understand. I am not here to tell you everything theoretically correct. Why am I here? To clear your interview, so that you can clear your interviews and you can clear the gate examination. Only these two main target I have for you guys, right? So I want to go to that level so that you can understand the question and you can solve it and you can achieve full marks, right? You can clear the interview and you can clear the examination. Okay, that is my only priority. So don't come in the comments and tell me, sir, theoretically you're telling this wrong. No, I'm not going into that. I'm just trying to explain you so that you get in your head what is actually I'm talking about. So here what happens, I can go from, currently my PC is PC1. So if I write like this base addressing mode, and I tell offset as 10, and my base address register has PC2, so I can go to what, PC2 plus 10. My PC will be updated to PC2 plus 10. So I have branch between programs. I can branch between programs. So that is what inter-segment branching means. Okay. So effective address is same only. This is also relocatable, and PC also relocatable, but that is intra-segment branching. I can only branch between my own segment. Here I can branch between different segments. So I can branch between segments. Here only I can branch within the same segment. Here I can branch only within the same segment, same code segment. I can branch in some other program, I cannot branch, but here I can branch. Okay, that is the advantage of base register mode. So it's the same thing, only we add the offset and all those things. You can read, this is the advantage and disadvantage, you can read. So let's come to a question. So this is a 30-second question. Okay, just read the question, pause the video, read the question and read this question. Okay. Okay, this is the same question only, this is not a different question. Okay, this we can take it as many questions. Okay, just read this question. Okay, this and this, like this is the same question only, this is not different. Okay, and try to implement whatever you have learned this in this whole hour. Try to implement the thing, right? Because I have told you all these are values, and implement using different addressing mode. If it follows immediate addressing mode, if it follows direct addressing mode, register, all those things. Pause the video and try it out by yourself. Okay, let's start to read the question. So a CPU supports following addressing modes: immediate, direct, indirect, register, all the addressing modes, right? Analyze the given instructions. Okay, analyze the given instructions, and what we need to do, just hold on. Given instructions, and calculate the value stored in R1 after the execution of each case. So it will, like, I will do immediate, then I will do direct, indirect, register, and then I will analyze the value of R1. What will be the value of R1 basically? Okay, one more addressing mode was here. I think I missed that addressing mode. It should be implied. Okay, so yeah, that addressing mode was here. I missed the implied actually. Implied is also there. Implied we will not include, because implied means it's just a single instruction, right? There is no destination register or source register. It knows from where to increment or decrement, like increment decrement. So I have skipped the implied one. So we have to find the values of R1 in each case. So initial value, what are the initial register values? Initial register values are R1 equals to 0, R2 equals to 50, R3 equals to 200, R4 equals to 90. All these are initial values. And memory at 100 is 300, memory at 300 is 20, and all these values are there. Okay, what is the instruction? Instruction is only a single instruction, that is load R1 comma operand. Load R1 comma operand is the instruction. So in the first case, I will be using immediate addressing mode. My operand will be 20. My operand will be 20. So what will be the value of R1? Okay, so I will just draw down the register and memory diagram. I will to explain you better. So I have registers like this. Okay, register R1, R2, R3, R1, R2, R3, R4. I have 4 registers, correct? 4 registers I have. PC is 100. So PC, initial PC, it is 100, and R1, R2, R3, R4, what are these? 0, 50, 290. 0, 50, 200 and 90. Okay, next is what? It is like my PC is this, and my base register value, I have a base register as well, that is 200. So this is also a register, this is base register. This value is 300, not 200, sorry, 300. Okay, and my memory values, right? I have 100, I have location 100, 300, 200 and 500. So this location is value 100. Then I have somewhere in between 300, Then I have somewhere in between 500. What else I have? 600 also. No, I don't have 600. I have 200. Okay, I forgot a 200 one. So I'm bringing this down actually. $200. Okay. So at memory location 100, what I have stored 300. At memory location 300, I have stored 20. So this is 300, and at memory location 300, I have stored 20. So 300 has value 20. 200 has what value? 200 has value 40, and 500 has value 60. So this is 40. This is 60. Okay, so these are the values of the memory. So this is the layout basically. These are all the values. Now let's solve the first question. Option 1. So it is doing load operand is 20. Here the operand is 20. So I am doing immediate, and what happens in immediate? What happens in immediate? In immediate, okay, I'm writing the spelling wrong. This E only. I am doing load R1 5, right? 5 is written. Operand is 5 this time. So not 5, sorry, 20. So what will happen? Basically, this operation, whatever is present in this second, right? This is directly the operand. This is the operand. This is the operand. I don't need to do any effective address calculation. So directly, I can write my R1 value will be exactly equals to 20. So my R1 in this case will be 20. So final value in R1 will be simply 20. That is the result. Okay, that's easy. Let's solve the second one. Second one is direct addressing mode, right? Direct mode. I'm using direct mode. So for direct mode, operand is 100. So in place of operand, I will place 100. Now, is this the operand actually? No. This is the effective address. So it is load R1 with 100. Okay. So I will load R1 with 100. So what will happen here is that this is actually address. This is direct mode of the addressing mode. So I will copy this memory and I will go to this address. I will go to this 100 location and see the contents. The content is 300. So I will store 300 at R1. So R1 will be 300 in this case for direct mode of addressing. Then 3 is indirect. Okay. So indirect, again, the operand again is same only, 100 only. Okay. Operand is 100 only. So now the instruction is again, the instruction is same, R100, but this time things will be a bit different. This is what? This is the address of the effective address. In indirect, this is the address of the effective address. So this is my effective address actually. And what does effective address mean? This is the address of the operand. So where is 300? 300 is here. So I will store the content of this. This 20 will be stored in register R1. Now you will have a question, sir, these two instructions are same. How will I know if it is direct or indirect? My friend, so at the starting of the lecture, I have told you something. At the starting of the lecture, we have this particular thing, right? This particular thing. So this mode specifies, tells the CPU that whether I am using indirect or direct or PC relative or whatever. So this lecture is revived around this. Even though I didn't talk about this much, but mainly the CPU understand with this help of addressing mode what type of address it is. I've explained at the starting of the lecture, right? So I hope you understand. Although these two addresses, at least these two instructions are same, but they do different things because different values is being stored in the register. I hope you understood this point. Now let's go to the fifth point. It's not fifth, sorry, fourth question. So in the fourth question we have register mode. Register mode of addressing, if nothing is mentioned, right, it is register direct mode. Okay, register direct mode meaning whatever the contents of R2 that will be stored in R1. Register direct meaning whatever the contents of R2 that will be stored in R1 directly. So we'll copy the register this time. So we are moving to registers now. So it will be load R1 R2. What it will do? Simply store the contents of R2 into R1. So R1 will be 50. So my result is 50 now. What about the fifth case? It is register indirect. Okay. So this time it is register okay. And what is register indirect? Register indirect is like operand is again this time R3. Register indirect operand is R3. Okay, so instruction is load R1 R3. So what this will do is I will go into R3 and this R3 will be my effective address. This will contain the address of my operand. So I'll go to this 200 location, and at 200 location I have 40. So I will replace this 40 with R1. So I store R1 equals to 40. Okay, how many memory access I require? Only one, because to access register, right, I don't need any time, as explained in the previous point of this particular lecture. Let's do the sixth one. What is sixth? Sixth is simply auto decrement operand R3. So what does auto decrement do? Okay, actually this is a bit wrong here. I should have done actually I should have written it like this: operand R3, and I can do this like this. This will be plus. Okay, this is auto decrement, right? So this will be minus. So in the sixth case, we have an auto decrement, right? So what I will do is, what is the instruction? Instruction is load R1 minus R3. Load R1 minus R3. So what we'll do? I have minus first, right? I have minus first. So if I have minus first, so first I will decrement my R3. So first I will decrement my R3. So R3 will become now 199. Okay. Next what I will do? I will go to this memory location 199. Now in the question they have not given me this information. So I don't know. I will simply write R1, register R1 will simply be equals to whatever there is the content in the memory location 199. I don't know. They have not given me in the question. So I will not do it. Okay. It is pre-increment. Sorry, it is pre-decrement. Pre-decrement, as minus sign is at the starting. Okay, so let's move on to the next one, seventh one. So in the seventh one, what do I have? So they have given me indexed mode, right? Index mode they have given me, and base register is equals to R4. So previously I had given, like in index mode, right, what we have to do, we have to provide the base register. In base register mode we don't have to, because there is an implicit base register present in the architecture, but in index mode we have to provide the base register, so it takes a bit of memory access. So base register is equals to R4 in index mode, and index register is 10. So what it is doing is load R1 10, and in the instruction it is already specified that my base register is simply R4, correct, as index is 10. So what is my base address? 90. So my base address is 90. So what is my effective address? Effective address will be base address plus my index. Which is equals to 90 plus 10. Which is equals to 100. Which is simply 100. This is my effective address. So I will go to this effective address location 100. 100 is here. That is 300, right? So R1 will be whatever that is stored in memory location 300. That is, sorry, not 300. Sorry, memory location 100. That is 300. So R1 will be simply equals to 300. Now let's move on to the eighth one. That is PC relative mode, right? PC relative mode. In PC relative mode, operand is plus 400. Okay, in PC relative mode, operand is plus 400. So they haven't provided us any base address. How will I know? The base address is the address stored by the PC. Whatever is stored by the PC, that is the base address location that they have mentioned here. PC is 100, right? PC is 100, as I have written. Okay, I have written here PC is 100. So PC program counter is 100, and it is written that load. What is written? Load R1 plus 100. Okay, load R1 plus 100 is written. Or what is written? Plus 100 is written, right? PC, yeah, sorry, plus 400 is written. Okay, plus 400 plus 400 is written. So if this is written, what will be my effective address? Effective address will be simply PC plus offset. Offset is 400, correct? PC value is 100, so it will be 100 plus 400. So my effective address will be simply 500. So I'll go to this location 500 and I will store these contents in the register R1. So R1 will be simply equals to 60. Okay, this will be my effective address. Now what about the last one, that is base register indexed mode. Base register index mode. So my operand this time is minus 100. It is minus 100. So if it is minus 100, the instruction will be simply it is load R1 minus 100. So now what will be my effective address? My effective address will be PC, not PC, sorry, this time it will be base register minus 100 minus the offset, right? Base register value is 300, so this will become 300 minus 100, so this will be 200. So I'll go to this 200 location and store the value, store the contents, right? Content is 40. So my R1
will be 40. Okay, so this is basically my target address. Okay, so in PC relative mode, there can be one more thing, is branching, that I'm not discussing right now. So branching you can do, that is what I'm not discussing about right now. Okay, so yeah, these are the few results. You can write down the results. Okay, like this, because in immediate mode, right, I didn't have any effective address calculation. Immediate, the operand was directly present, so I didn't have any effective address calculation. I had operand. What was the operand? Operand was 20.
How many memory access did I require? 0, because it was in the instruction. The operand was in the instruction itself. In direct mode, what was the effective address? In direct mode, the effective address was present in the instruction itself. That is 100. Right? Immediate, this was the operand itself. I didn't have any effective address calculation. This is the effective address, right? That was present in the instruction. How many memory access I required? 1. I have to access memory 100. So effective address is 100 in direct mode. Operand was what? Okay, I forgot the operand. Operand is 300. In 100 location, if I go back here, in 100 location, I have value 300 stored, right? So it will be 300. How many memory access? 1 memory access. I have to access the memory location 100. In the third case, indirect mode. In the indirect mode, how many effective address I had? What was the effective address? Effective address, if you go back here, effective address was actually not this. This is not the effective address, right? This was the effective address. 300 was the effective address, and operand was 20. And how many memory access? two memory access, 320 and 2. In register mode, was there any effective address calculation? No. Whatever the contents of register, that are directly copied back to register R1. So what was the content in register R2? This one, right? Yeah, register direct, this one. Here register R2 had 50 content, so operand was 50. And how many memory access I required? 0, because it is very fast to access register. It is inbuilt within CPU. I don't need any, like, it does not cause any much delay, right? It does not cause much delay. So it was simply 60. Okay, not 60, sorry. What was the register? This value, R2 value. R2 was simply 50. So this will be 50. How many memory access? No memory access. Register indirect. What was the effective address? It was load R1, R3. So 200, right? The contents of R3 was the effective address basically. So 200 is my effective address, and operand is 40. 240. And how many memory access? 1. 240 and 1. Okay, and then we have auto decrement. Why 1? Because register access is not a memory access. It does not take much time. Auto decrement. What was the effective address here? The effective address here was my register R3 subtracted by 1, that is 199. My effective address was 199. In auto decrement, the effective address was 199, and the value was whatever the memory location at 199, whatever the contents of memory location 199. So this is 199, and in the question they have not given me what is the value at the memory location 199. I will write it as it is. How many memory access? 1. Index mode. How many memory access? 1. Why? Because in index mode, this was the instruction, right? So this was hard coded. This base address was hard coded. So what was the effective address? Effective address was 100. So I needed to go to this location 100 and then store the value. So effective address 100, content operand 300, and memory access only 1. 100, 300, 1. Okay, this is not PC relative mode. This is the base index mode, right? PC relative mode. In PC relative mode, okay, it was like the base address was stored in PC. How many memory access? 1. Effective address 500, contents 60. 561. Base register mode. So in base register mode, if I am here, okay, base register has value 300. I subtracted this offset, that gave me 200. Then I went to this 200 location and stored this value. So what is the effective address? 200, and also known as the target address. It is also known as the target address. And what is the operand? 40, 240, and memory access is 1. All these have memory access as 1 only. Okay, so these are the like results. Okay, if you enjoyed this particular question, like hit a like button right now and tell in the comments how much you enjoyed this particular concept. So I hope all your confusions got clear from this. Few confusions can be there from PC relative mode because I didn't talk about branching. If I will get a time, I will talk about branching as well with the help of PC relative mode. I will try to do that. So let's now do a few more questions so that these concepts get concrete, crystal clear inside your head. Okay, so let's read this first question. In which of the following addressing mode is the operand not included as the part of the instruction? Operand is not included as the part of the instruction. Which of the following addressing modes? Immediate? No, immediate operand is directly there in the instruction, right? So this is not possible. Direct, yes, operand is not included. I tell the effective address of the operand. So direct is possible. Indirect, again, yes, I don't tell the operand in the instruction. I tell the effective address, not the effective address as well. I tell the address of the effective address of the operand. And register, also in register, I don't directly write the operand, right? I just write register R4. So it copies the content of R4. Okay, it is not a operand directly. All these three options are correct. Let's solve this question. Okay, in GATE also these type of simple questions also come. Theoretical questions also come sometimes. The most appropriate matching for the following pairs. Indirect addressing modes. So indirect addressing mode is used generally where I told you, right, while explaining the theory, we generally use it for pointers. So here I can observe a pointer is present. So although I am not so sure, I will just match these two. This can be true. Okay, indirect addressing mode is used for pointers. I'll just match these two. I'll just check the other two options. Okay, immediate addressing mode. Immediate addressing mode can be used for constants. Why it can be so constant? Int a equals to 5. I directly put a constant value there. Okay, that is the task of immediate addressing mode. So it is looking like that y will match to 3. Okay, I will stop here. Then I will say here auto decrement addressing mode. Auto decrement addressing mode, if you ever have done some programming, you write I plus plus I minus, right? Auto decrement or increment. So this is generally used in loops for I equals to 0, I less than equals to 1, I plus plus, if you remember something like that. So it is generally used in loops. So from what I see in the options, that x is matching to 2, x is matching to 2, y is matching to 3, and z is matching to 1. So x is matching to 2, y to 3, and z to 1. Okay, is something like this option is present? I will check that. Yes, option C is present. So this will be correct. If this was not present in the option, I have to choose the next best option. Okay, then I have to again reanalyze the options and check which one is matching according to the options. Okay, so that you have to do in the examination hall. Sometimes it is true that they can, like, all the options can be incorrect. It can be MTA, but most cases the options will be correct only. Maybe you have thought something wrong. So I'm giving you the explanation as well, how you will think in the examination hall. That also is very, very important. Now let's solve this next question. These are all only matching simple questions, only theoretical questions. So which is the most appropriate match for the items in the first column with the items in the second column? Indirect addressing, it is used for passing array as a parameter. It is generally used for passing array as a parameter. When do we pass array as a parameter? Like you pass, right? You write some func like int a like this, and then you pass func a 1. Okay, and this a is what? This a is the address of first element of array. If you can skip this question, actually, if you are not from CS background or if you have not studied programming, you can skip this question. Okay, func of a1. Now yeah, indirect addressing is generally like this. Is what? This is just a pointer, right? This is just an address that is a pointer pointing to the first element of the address, first element of the array. So indirect addressing will be used for passing an array as a parameter. Next is index addressing. Index addressing will be what? Array implementation, writing relocatable code. Index address, right? We cannot simply write relocatable code with index addressing. It is not possible. I explained in the starting of this lecture, right? We cannot write relocatable code with index address. Why? Because base address is hard coded in the instruction. We cannot simply write relocatable code with index addressing. So index addressing will be used for array implementation. Yes, we can use it to implement arrays. Like index is what? It is just like array has some index, right? A of I. What does this mean? This means a plus I, right? That is the definition of this, a plus I. That is what this means, if you ever know a bit of array programming. Now then we have base register addressing. Base register addressing is used for writing relocatable code. That's why this extra addressing mode came, right? To write relocatable code. Yes, base register addressing is used for writing relocatable code. So my x is pointing to 3. My y is pointing to 2. My z is pointing to 1. Okay, so y will not point to 2, y will point to 1, and z will point to 2. So it will be x3, y1, z2. So option A will be correct. So just be careful. That's why I have explained the theory that why you cannot write the relocatable. If you couldn't understand relocatable, you can go back and watch that portion. Okay, Then we have this question. So match each of the high level language statements given on the left hand side with the most natural addressing mode. Okay, this is what this simply what a of I is equals to b of j. We are using what we are using arrays. Arrays means indexed addressing. So we are using indexing. We are like indexing from one I to j. So this will be index addressing. Okay. Then while star of a plus plus, this is actually using both. Actually, this is using both indirect and auto increment, but we are using auto increment here. So I will choose auto increment is the most appropriate one because I see the next option, right? It is also using indirect. Okay, because I am throwing a pointer. Okay, this is the address of x. So in int equal to star x, right? It stores the address of x. That is what this does. So it will be indirect addressing. Okay, so 1 will be b, 2 will be c, and 3 will be a. Okay, 3a, 2b, 2c, 1b. This option C is correct. Okay, so these are all just the match the following, just like those bacha level type questions. Now we will do few programming questions as well. Don't worry, we'll do few programming questions in the next lecture. We'll do mainly few programming questions. Okay, so let's read the next question. In absolute addressing mode, the operand is inside the instruction. In absolute addressing mode, absolute means what? Absolute means it is the immediate. Not immediate, sorry, it is the direct addressing mode. If you remember, like they can play with name as well. So this is the direct addressing mode, right? Absolute means I'm giving the absolute address of the operand. The operand is inside the instruction. No. When is the operand inside the instruction? It is for immediate, right? Operand is directly in the instruction itself. So this is for the immediate. Addressing mode. Let's read the third option. The register containing the address of the operand is specified inside the instruction. The register containing the address of the operand is specified inside the instruction. So it is talking about the effective address. Okay, not effective address. Sorry, register containing the address is present inside the address. So it is what it is talking. This is talking about the register indirect, because here the register contains the effective address, right? Indirect. This is register indirect. The location of the operand is implicit. We don't mention the operand. Okay, location is implicit inside the instruction itself. No, right? This is for the implicit addressing mode, like increment, decrement, accumulate, or something. This is not this mode, right? So option B, obviously I skipped the option B. That is the reason. Option B is correct. The address of the operand is inside the instruction. Yeah, this is direct, right? I directly specify the address of the operand. So this is the direct mode or the absolute mode. Okay, so option B will be correct in this case, right? So let's read the this question. Which of the following statements about relative addressing mode is false? Relative means like effective address calculation, like indirect address. Relative always means indirect addressing. Okay, it enables reduced instruction size. It is true, right? Why it is true? Why it enables reduced instruction size? I don't need to provide the address on the instruction. The address can be stored in a register that can be big. Okay, I don't need to provide the address in the instruction. Address can be very big. So this is wrong actually. This is true. This is very advantage of a relative based addressing, right? So I don't need to provide address of operand. It enables easy, it allows indexing of array element with same instruction. Yes, we can do indexing as well from relative based in like a relative based addressing mode. So this is also false. Okay, sorry, this is also true. So they are asking what is false. They are not asking which are true. So I'll only take which is false. It enables easy relocation. Yes, it does enable easy relocation because we have seen base index mode, right? Base indexing also uses relative addressing only. So this is also true. So I will cross it. It enables faster address calculation than absolute addressing mode. Is it true? In absolute addressing mode, I have only one memory access. But here I will have one memory access plus something, right? If it is register indirect, then it will be faster. If it is indirect addressing mode only, then it will be very, very slower. Two memory access. If it is register indirect, it will be one memory access plus something, right? Plus something. So it enables faster address calculation. No, it like address calculation is slower, right? We have to calculate the address. It will take some time. So this is false. Hence, this will be my correct answer, because they have asked what is false about relative addressing mode, not what is true. So you have to read the question properly. Okay. Let's go to this question. Which of the following is/are true of auto increment addressing mode? It is useful in creating self-relocating code. Self-relocating code in auto increment or decrement? No, right? I have not talked about any concept about self-relocating code in auto increment or decrement. It's just increments or decrements the value register and then it calculates the effective address. That's it. No. Self-relocating code is only for those PC relative mode based indexing mode. Okay. It is, if it is included in an instruction set architecture, then an additional ALU is required for effective address calculation. Now, is this correct? If it is included in an instruction set architecture, then an additional ALU is required for the effective address calculation. Do I need an additional ALU? The current ALU can perform the increment, right? It can do it. We can keep a additional ALU. We can do it, but it is not mandatory. Okay, it is not mandatory. It requires an ALU operation, correct? Because I have to add one, and it is arithmetic operation. So we will require an additional, we will require a ALU operation, but I will add an extra ALU for that only single operation. Will I do it? That is too costly, right? So statement 2, it is correct in some sense that we do require an ALU operation, but the current ALU, whatever is present inside the system, can also perform, just hold on, can also perform that operation, right? That addition or subtraction, it can perform. It is not mandatory to perform additional. It is not mandatory to have a separate ALU for performing that plus one. Okay, we don't need that separate ALU. It is not mandatory. We can keep it, but it is not that mandatory. So this is also wrong. The amount of increment depends on the size of the data item to be accessed. What does it mean? So, if you have done programming and you have array, okay, char A 3, okay, and you have int B, sorry for the noise of the honking, I'm sorry, int B 2. Okay, just hold on, let the noise of the honking go away. I'm sorry for it. So if I write something like this, if I want to calculate the address, like if I want to write print, okay, print A plus 1 and print B plus 1. For hypothetical situation, let's assume these two are different programs and both has base address A equals to B equals to 100. Okay, both are different programs, but hypothetically let's assume once I'm doing this and once I'm doing this. Okay, if I do A plus 1 and B plus 1, will it point to the same 101? No, right? It will not point to the same value. Why? Because char takes how much space? Each character in C, it is fixed. Each character takes, what I remember, each character takes 2 bytes. From what I remember, okay, I don't remember exactly, or 1 byte, I believe, 1 byte. Okay, and integer takes 2 or 4 bytes. It is not defined. Integer takes 2 or 4 bytes. So if I want to go to the next integer, so if I have a byte addressable memory, so for a char, if I have a byte addressable memory, right? So this will be char C1, C2, C3. This is memory location 100, 101, 102. But if I have int has 2 bytes of data. So this will be my 100, 101, 102, 103, 104, 105 and 106. Okay, so here these 2 bytes are actually storing the first integer. Okay, I1, this is storing the second integer I2, this is storing the third integer I3, and okay, I have 3 integers, right? I have only 3 integers. So now I'm storing 2 integers. So if I want to get the next integer, what will be the address of the next integer? What will be the address of I2? It will be 102. So it will be 102. Address of next integer will be simply 102. Okay, it will not be 101. So 101 is just I1, right? Okay, because I have 2 bytes. So that's why it is correct. The amount of increment depends on the size of the data item that needs to be accessed. It depends, right? If it is an integer character, it depends on the size of the data. So C option will be correct. Only this third one is correct, right? Everything else is wrong. Okay, let's read the next question. So for computers based on 3 address instruction format, each address field can be used to specify which of the following: a memory operand, a processor operand, and implied accumulator register. So if I have 3 address fields, those address fields can be a memory operand. Yes, it is correct. They can be a processor register. It can be R1, R2. We have learned that. We have register direct mode. But accumulator register, it is already implied, right? It is already employed. We don't need to specify special purpose register in the instruction. We don't need to specify special purpose register in the instruction. They are implied. That's why the name special. That's why they are special. CPU already knows it's a special thing. I don't need to specify in the instruction. Okay, that is already, it will be included in opcode. So your option A will be great. Either S1 or S2 is possible. S3 is not possible. Accumulator is already specified inside the opcode itself. So that's about it for this lecture. I hope you have enjoyed the addressing mode. We have learned everything smoothly, and I hope you enjoyed. If you did, please tell me in the comments below, and please don't forget to like if you haven't already liked the video. So I will meet you in the next lecture where we learn few more things about addressing modes, and we'll do more programming questions on addressing modes. Thank you for watching, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to my channel. So today we'll start the lecture 3B of our COA, Computer Organization and Architecture chapter subject, right? So today we'll learn about computable and non-computable addresses. What are those things? So like they are just a classification of whatever we have learned, right? Addressing modes, they are just a classification. So what are non-computable addressing modes? No computation is required to determine the operand address. Just like implied. In implied, the operand is already included in the instruction. Just like immediate operand is included in the instruction. Direct, the address of the operand is included in the instruction. Okay. And in indirect mode, the address is also included, right? You go to some address, okay, that address is in the instruction, and you go to the effective address, and that is the address of your operand, and register indirect all this. Now what is computable? Basically, computable means requires computation to derive the operand. For example, auto increment or decrement mode, right? What you do, you have MOV R1 R2 plus. So what you do is you increment R2, right? So you have to perform a arithmetic unit, like arithmetic operation. Here, generally in case of indirect mode, I had move R1 2000. So what you would have done, you went to the memory location 2000, here some address would have been stored, let's say 100, then you went to this location 100 and you got your operand, right? This is your operand. But did you have to perform any arithmetic operation? No, just memory read, that's it. But here we have to actually perform some arithmetic operation. Like if I take the pre-increment, then you will understand this better. Plus R2, right? So first what you have to do, you have to increment the value of R2. So let's say R2 has 200, so I will increment it to 201. Then I will go to this address 201 and then take the contents of that. That will be my operand. So that is the difference between non-computable and computable modes. Just like index mode, right? In index mode, what do? You have a base. Let's say the base is 1000, right? Then index is given as 10. So what you will do, you will add base with the index. Then you will get your address of the operand, right? You have to calculate the effective address. It's not simply present in a memory or in your instruction. It's not there. So that is the difference between computable and non-computable. So non-computable, which addressing modes are non-computable? All these, right? Register, indirect, all these are non-computable. You don't have to compute anything. It is already present in the instruction or somewhere in the memory location. But in computable, auto decrement, increment mode, index mode, PC relative, base register, all the last four, right? From 7, 8, 9, 10, all the last four, they are computable addressing modes. So like I have already explained this previously. What does addressing modes provide? They provide us flexibility and efficient use of registers and memory. Sometimes I don't want to provide a big huge instruction length, right? Because instruction also has address in it. So it's sometimes what will happen, I will provide the address through a register, so my bit length will be saved, so my instruction length will be reduced, memory will be saved. I have explained this previously as well. So like here it is saying the same thing only, no computation will be required. Okay, and here, right, computation will be required. Auto decrement, increment, you can read all this, it will be required. Like if you want to in index mode, if I want to calculate the effective address, you have to do base address plus index value. In PC relative mode, you have to add the PC value plus offset. Base register mode, you have to add the base register value plus the offset. So like you always have to add something. Okay, so yeah, that is the main thing. And just one more thing is these two, generally these two and this as well, index mode, these are generally used for fetching the operand, fetching the operand or data. And these, right, are generally used for branching. As explained, how do I do branching, how do I do interrupt, all those things I've explained in the previous lecture. So used for branching. This is general case, but it can be used for other use case as well, used for branching. So here the address is called target address in this case. If they call, right, in gate examination in the question target address comes, don't get scared. It is called target address. Why? It is the target instruction. That's why it is called the target address. And here it is called the same as previously, effective address. Effective address. Okay, I hope you got, like, what are the different use cases. So here, like, the comparison between different addressing modes is given. So if you want to quickly summarize, right, you can put in your short notes and revise through this, right? Short notes and revise. I have just given you a summary of what each addressing mode does. So before your examination or before your interview, something, you can like revise this, okay, at once. So let's do few questions from this. So the memory location 1000, 1001 and 1020 has values this. So we'll draw the memory location. So 1000, 1001 and 1020 seems like a byte addressable, but we have to see if they have mentioned it. It has value 18, 1 and 16. 18, 1 and 16. They have not mentioned whether it is a byte addressable or something. Okay, but I will assume it byte addressable. We can assume anything. I think the answer will not change. Move I. Move, like, not I, sorry, it is move 1, I think. It means that you have to move immediate. You have to move this 1 value immediately to RS. So RS will be stored immediately to 1. So RS will be 1. So RS currently is 1. Then we have RD 1000 RS. What does it mean? It means load from memory. Okay, 1000 of RS. Okay, 1000 of RS. It means load from memory basically. So we will load the 1000 value. Okay, whatever is present in the 1000, what content is present inside 1000, it is 18. Okay, so my RD will be basically 18. What is this basically? Can I understand this? Okay, actually they have not mentioned this, right? I think this is using base indexing mode. So they should have actually mentioned. This is a very old question. They didn't mention it. This is using base indexing mode. So from here I can understand that this is my base address. So this is the first type of indexing mode, right? Where this is your base address, okay, and this is your index. So you will not, this will be wrong. So that's where you can go wrong, right? You have to be careful. What they are telling me is to load on RD the contents of memory from 1000, that is a base address plus 1. That is how we hard code the base address in the instruction. This is the 7th, I think it was the 8 indexed mode of addressing, right? So what is present in memory location 1001? It is 1, right? So again RD will also be loaded with 1. Okay, you have to be careful here. You have to be very careful here. Then add I means RD will be added with 1000 add immediate. So whatever the value is, that will add immediate. It is not an address. So my RD value will be changed to, it is RD, right? Yeah, RD plus 1000. So RD now becomes 1001. Okay, then 0 RD 20. So store immediate this value on this memory location 0 RD. So what is this memory location? 0 plus RD. RD is 1001. You store immediate in location 20. Okay, like you store the value 20 immediate. So this will be an operand directly. So memory of 1001 will be simply 20. So basically I will change this value, right? This value will be changed to 20. So what, let's read the options. Which of the statements is true after the programs is executed? Memory location 1000 has 20. No, memory location 1000 does not have 20. Memory location, like only memory location 1001 has 20. Any other location does not have 20. So this last option is only correct because all this is telling that 1020 has 20. No, I don't know about 1020. 1021 has 20. No, 1001 has 20. Yes, we just operated, like we just executed the program and we saw that 1001 will have the value 20. So option. So this is a very good question of indexed based register, like addressing mode. Okay, you have to revise all these things. Let's do this next question. A relative branching mode instruction is located in memory address at 100 and it branches to the address 250. What is the value of the relative address field in the instructions? Okay, so if a relative addressing mode is used, right, they should have told here they are using PC relative mode of addressing. But we will assume, if nothing is mentioned, we will assume PC relative mode of addressing, because if no base address is given, that means it is using PC relative mode of addressing. Okay, so a relative branch mode instruction is located in memory address at 100. So instruction is located at memory location 100. Okay, it branches to 250. So my mnemonic will be B250. Just I'm writing just for sake of the understanding. Okay, that this value, this instruction is located in memory location 100. Okay, and it says that branch to location 250. Take the next address from location to next, not the next address, take the next instruction from location 250. What is the value of the relative address field in the instruction? What is the value of the relative address field in the instruction? So they are asking what is the value of the offset. Offset. If no base address given, address or base register given, then assume PC relative addressing mode. Okay, so we have to assume PC relative addressing mode. Now determine the value of the program counter before fetching the instruction. Like, what is the value of the relative address field in the instruction? So what will be the value here of the offset? What will be the value of the offset? So what is my final instruction location? 250. So I know in PC relative mode the target address, here my target address is 250, and in PC relative mode the target address is equals to PC plus offset, program counter value plus offset. It is equals to 250. So obviously, what will be the offset value? What will be the offset value? So currently, what does the PC is holding? Currently, this instruction is being fetched, right? Once I will fetch this instruction, then only I will understand that I need to go to 250 location. Else, if I don't fetch this instruction, so how will I understand I need to branch? So obviously, I have fetched this instruction. So currently, what I am doing? Currently, CPU has fetched the instruction B 250. Okay, CPU has fetched the instruction B 250. Now I have taught you in instruction cycle, if some instruction is fetched, that means my PC is holding what? PC is holding the next instruction. Hence PC points to the, sorry, not holding the next instruction, PC is holding the address of the next instruction. PC points to the next instruction. Basically means it holds the address of next instruction. It holds the address of next instruction. Okay, so here my PC will hold the address of next instruction. What will be the next instruction? It will be 101. So my PC value is actually 101, right? Because this instruction has already been fetched. Else, how will I know that there is a branching? How will the CPU understand that there is a branching without fetching the instruction and decoding? Once it decodes, then it understands, okay, I have a branching, I have to change the PC value. So obviously, fetch has been occurred in the instruction cycle. This instruction has been fetched. This has not been implemented, but it has been fetched. So obviously PC value will be 101. So PC will be equals to 101. So what will be my offset? 101 plus offset equals to 250, right? I have to branch to this instruction location 250. So offset will be 149. I know many students will make a mistake. This is the part 1, that they will write 150. 150 will not be the correct answer, because I have explained what exactly happens in instruction cycle very well. So you will not be that student. You will not make this mistake. You will write the correct answer only. That is 149. 150 will not be correct. It will be incorrect answer. Okay. Now let's go to the part B. This was the first question. Okay. part 1. Let's go to the part 2. Now if I go to the part 2, what do I observe? So I need to tell the value of the program counter before fetching the instruction. So even before the instruction has been fetched, so this branch 250 instruction has not been fetched. So what will be the value of the program counter? It will be this value, right? Because next instruction is this only. This instruction I will fetch next. So obviously it will be this instruction. So before instruction fetch, I'm supposed to fetch the instruction located at address 100. I will fetch this, right? Now, before fetching, obviously I will fetch that instruction. So PC will point to that instruction PC will point to that instruction which will be fetched next, right? So the instruction branch 250 will be fetched. Where is it located? 100. PC will be equals to 100. Now, what are they telling me? After instruction fetch, determine the value after fetching the instruction. I've just explained. As soon as we fetch the instruction, right? Instruction has been fetched. The CPU and control unit, it decodes the instruction. So as soon as the instruction is fetched, the task of program counter is done. So it will increment. It will then point to the next instruction that is supposed to be fetched. That is 101. After instruction fetch, it will point to the next address, that is 101. Till now we don't know that in the instruction itself there is a instruction, like in the instruction itself it is telling us to branch to instruction 250, location 250, branch to 250. Okay, till now we don't know because we haven't decoded. So after execution of the instruction, after decoding, then the CPU will execute, right? After execution, what it will do? It will basically change the PC value, because PC currently was pointing to 101, but we will not point to 101 because CPU has directed, man, I want to, like the instruction has told me to start from location 250, branch to location 250 for taking instructions. So you change your own value. PC will change its own value to what? Location 250. PC will change its own value to location 250. Okay, so it will change its value to location 250. So after execution phase, PC will be basically location 250. It will point to that instruction where I want. It will point to the target address. Okay. So I hope that you understood this concept about target address and like all branching and all those things. So if you did enjoy this concept, if this concept of PC relative mode of addressing got clear, please do hit a like button in the below and let me know in the comments below how you are enjoying this whole lecture. Okay, so here we have a C structure. So if you know C coding, C programming, then you can do this, attempt this question. Else you can do this after doing C programming. Obviously I can't teach everything right at once. So we have a structure called data. In a structure or data contains basically marks, which is an array of 100 integers. So marks is a array of 100 integers. Okay, and we have one only single character, that is grade. Grade is a character, and we have another int that is some number, C number. Okay, I don't know what this stands for. This is some C number, and this is the name of the structure is student, right? For a student, particular student, this is the structure. The base address of student is available at register R1. So base address of student available is register R1. The field student.grade, like we access a field by using the point operator or dot operator. Student.grade can be accessed efficiently using what? Post increment addressing mode, P decrement addressing mode, register direct addressing mode, index addressing mode, XR1, where X is the offset represented in 2's complement 16-bit representation. Okay, so what is grade? Grade is of character type, right? And I want to access it. So in memory location, how it will be stored actually? Let's go to the memory location and let's see how it is stored. So if I have a memory named student, what we will do is first of all I have a array of 100 integers, and let's just take an example. Let's take each integer is of 4 bytes. Okay, and each char is of 2 bytes. Each carry is of 2 bytes. Okay, so first this student block, right? In this student block, first it will store 100 integers. So if I start from address 100, okay, if it is a byte based addressing, right? So each integer has 4 bytes. So total I will have here 499 location. So all these are integers. Okay, all these are integers. All these are integers. Now next what I will have character. Next I will have character. What is that character? Grade. I will have a character named grade, right? Then another integer named C number. So the grade character is of 2 bytes length. So like here I will have character that is grade, and then I will have so what will be the final location? So starting location of this will be 500, and then it will end to 501 because it is of 2 bytes. So this is the 1 byte and this is the other byte. Then I will have a field name as C number. Okay, and this location will be 502 and it will go on until 4 bytes, right? We will have 4 bytes because it is an integer. So I will have C number, right? So it will start from 502. Okay, and it will end to 505. You can check, right? You can check 502, 503, 504, 505, 4 bytes. So this is the case study, right? This is how my data is arranged. Now they're telling me that which one is the most efficient way of accessing the field grade. If I it is telling me the register R1 is containing the base address of student. What is the base address? Base address will be this, right? Base address will be this. Base address is R1. It is the address of the first element of the student. Okay. Now if I increment R1 plus, will I be able to reach to my grade? No, increment and decrement operators, they are generally helpful in similar type of data like arrays of integer. If I do R1 plus, right, what it will do is it will just point to the next element of the array, that is 104. So R1 plus, if I just do, it will point to 104. So in the option A, generally we use increment and decrement mode of addressing. We use increment and decrement mode of addressing generally where the data type is similar. Then we use the increment and decrement mode of addressing. Okay, else we don't use it. So here, yes, it is similar data, but I am not trying to access array of integer only. I'm not trying to access this variable marks. I'm trying to access grade. So if I increment, it will only become 104. I will not be able to access my memory. Okay, hence post decrement also, option B, from this option B also gets rejected, right? Option B also gets rejected. It is telling me pre-decrement. So both are not useful. So option A and B are automatically crossed out. Register direct mode of addressing. Register direct mode. Register contains it contains the base address. Okay, it contains the base address. I don't have the offset. I don't have the address of the grade. So this R1 only contains the base address. Okay, so obviously this one is also incorrect option. Let us read the last one. Index addressing mode XR1, where X is an offset represented in 2's complement 16-bit representation. So obviously we have only one option left. This will be correct. Okay, and it's okay if you could not understand these particular thing only up until this, right? Okay, you can ignore. Why? I will explain. So what does this do is, we know as a user, I know where my character will be. Character will be at 500. So I will provide base address, I know. So X I will provide as 400. Okay, if I provide X 400, so my R1 plus 400, R1 plus X will be equals to, should have been equals to 500, which is 500. Actually we are getting 500. So I will provide the offset. Now what is the next portion string? So this option is correct, we can access. And how many memory access we will require? Only one memory access, basically only one, right? Because register access is very low, so mainly only one. So this is the efficient one, and this is the only one which is giving the correct result. So what do they mean here? So you can design your CPU whatever you wish to. Okay, there will be some encoding and decoding. It's to your convenience that you have designed the architecture as so that the offset represents a 2's complement. What is 2's complement? We'll learn later on. If you have not studied number systems, don't worry, I will teach number systems, but it will take me some time. If you give this video enough likes and views, then I will obviously post the number system on YouTube, else I have to think of something else. Okay, so I give my offset, I can directly give my offset as 400, or you can give it some decoded format. Like I can give a complement of this. What will be the complement? Like 10's complement is just the opposite. So complement of this will be, I will subtract everything by 9. So this will be 599. So I can give the offset like this as well, and from there I can do the computation. CPU already knows how to find the actual offset. Okay, CPU knows. CPU will have some algorithm. Okay, I will encode and CPU will have some algorithm to decode the offset. That is up to the user's choice. So I don't care. So this part, this depends on the user, whatever the user wants, how he wants to encode the data. Okay, so it is not that of that much importance to us, but this is the most important one. If I do index based addressing mode, then it will be able to access the data known as grid. So this is a very good question and conceptual question. Okay, let's move on to the next question. So consider a hypothetical processor with an instruction type of LWR1 20R2, which during execution reads a 32-bit word. So one word is 32 bit. Okay, one word is 32 bit, and from the memory stores it in a 32-bit register R1. Okay, so the R1 is also a 32-bit register. It stores in that. Okay, it stores in that. The effective address of the memory location is obtained by addition of a constant and the contents of R2. So then what we do, we compute the effective address of the memory location obtained by addition of this constant. Like this is just what it is telling us. It is just the index based addressing. It is not telling anything new, right? We already know this. And the contents of register R2. This register R2. Okay, fine. Which of the following best reflects the index addressing mode implemented by this instruction for the operand of memory? Is it immediate addressing? No. In immediate addressing, what happens? The operand is directly present in the instruction. So this is not immediate addressing. Register addressing. In register addressing, the contents of the register is like the operand itself, right? No, here we are adding something, right? We are adding something with the register content. No, that is not the register addressing. Register indirect addressing, this is also called as a register direct addressing. If you tend to forget, it is also called the register direct addressing. Okay, register direct addressing. Register direct addressing. Okay, next we have register indirect scaled addressing. Now this is like, although they have provided name scale, but it is still the register indirect addressing. What does register indirect addressing say? It states that the data content that is present inside the register, it will point to an address. And with that, on that address, I will go to that location, and that location will contain the effective address of my operand. So this is also not correct. We're adding something, right? This is also not correct. Last one is base index addressing, which is obviously correct because we have a base that is present in the R2 register, and then we are adding it. So simple, that index based addressing mode that we already know. Okay, it is not telling us something new. We already know this. We have already learned this. So sometimes theoretical questions do come in gate examination. Okay, you have to be aware of that. So let's do the next question. A machine has 32-bit architecture and with one word long instructions. So one word again is 32 bits, and it is of 4 words. Okay, 4 words. Sorry, if not 4 words, sorry, 4 bytes. It is of 4 bytes. It has 64 registers, each of 32 bits long. So I have 64 registers. If I have 64 registers, how many address bits I can have? Like this, right? Once you do the question, this should be your inbuilt in your hands. That always when you read the question, 64 registers, how many address bits should I have? This calculation should happen simultaneously. Okay. So how many? It should be 6. Okay. I should have 6 address bits. Next is it needs to support 45 instructions which have an immediate operand in addition. It needs to support 45 instructions. Okay, have we? I think we have done this question already. Okay, I think this question has already been done. Okay. We have already done this question. So I won't be doing this. This question is already done previously. This question is already done, right? We have done this question previously. It was 168, I think, if I recall. So this question has already been done. So let's read the next question. So we have a 3-word machine instruction. This is a 3-word machine instruction. The first operand, destination, AR0, uses index-based addressing mode. So this uses index-based addressing mode, where, like, of course, from the operand itself, we can understand that A is the base and R0 is the index or the offset. Like whenever we are talking about target address, we talk about offset, and whenever we are talking about the effective address, we are talking about the index. Just that's just the notation, nothing else, right? So the second operand, source, uses indirect addressing mode. So this is using the indirect addressing mode. Okay, so basically this is the address of the effective address. A and B are memory addresses residing at second and third words. So A and B are memory address residing at second and third word. Okay, so and the first word of the instruction specifies the opcode, the index, register, destination, and the source and destination addressing modes. Okay, so I will write few things down. So I have 3 words. So this is 1 word, 2 word, and third word. So the first word, like the second word, contains the base address A, and this contains the address of effective address, that is B. This is the first and second word. So this, sorry, second or third word, and the first word contains the address, contains the opcode, what operation needs to be performed. Then it contains the address of the index register. It contains index register, that is, it contains R1, correct? It contains R0, and also it contains the addressing modes of source and destination. Also the mode, addressing mode, right? So these 3 information the first word contains. Next, what are they telling? Okay. During execution of add instruction, so during the execution, they have specified during execution of add instruction, the 2 operands are added and stored in the destination, that is the first operand. So basically what we are doing is, we're going to this location R0, and we're going to star base this location, adding these 2, and then storing it in AR0. Star means I'm like going to the location of the pointer. B is like a pointer. If you understand C, you will understand this. Let's skip it. Just understand that I'm going to B and getting the contents, right? So sorry, actually it is not the address. So what we'll do is, I will draw the memory here. So this is some location B, and B will have some effective address C, and I will go to C. Okay, and it will have some value D. Okay, or I can write X. So this X value will be added, basically X value will be added, and it will be stored in the same memory, that is AR0. So first operand is the destination. Okay, first operand is the destination. The number of memory cycles needed during execution cycle, they have taught about during execution cycle. During execution of the instruction, how many number of memory cycle needs. Now one thing I know, your instruction cycle consists of 2 things, fetch cycle and execution cycle. So they are explicitly asking how many memory access I need in the execution cycle. So what are they asking? They are asking how many memory access I will need in the execution cycle. Okay, so I will exclude memory, I will exclude fetch cycle. So during fetch also instruction needs to be fetch, right, from the memory. We will exclude that. We will exclude that. Okay. So here, how many times am I actually accessing the memory? So to do this, first I will need to access a R naught. So for me to access R naught, it will not take me any memory access, right? But to access a R naught, I will need a one memory cycle. So a R naught will be somewhere here, right? R naught is a register, so for that I don't need any memory access. But a R naught, so a will be somewhere here, right? In the memory, a will be somewhere here, and R naught will be somewhere here. Okay, this will be like a plus R naught, correct? So I will need, first of all, I need this operand, right? So I need one memory access here. Then this B, right? I need to go to this location address B. Okay. Then if I need to go to this location address B, I have to do one memory access here. Then again, this C actually is address. This C is affected address. So again, I need to access another memory here. Again, I need one memory access. Finally, I get my two operands, X and B, right? Okay, I get my two operands. So I finally get my two operands. Now, what other memory access I required? Now I have got my operands. So first is operand fetch. First we need to fetch the operands. Operand fetch. To fetch the operands onto the my memory data registers, how many memory access do I require? I require 1 plus 2. This is for index based addressing, and this is for indirect. In indirect, we require 2 memory access. I have taught you in the previous lecture. Indirect addressing mode. This is for the operand fetch. I got the operand, right? Now I need to write back the result. Write back. Okay. Write the result. Why do I need to write back the result? I need to write it back on this A R naught. This is using again indexed based addressing mode, right? So again, how many memory access I will require? 1. So this will be 3. This will be 1. So total memory access I require is 4. So answer of this question will be simply 4. Okay. Now, if they would have written here instead of execution cycle if they would have written in the whole instruction cycle, can you tell me in the comments below how many instructions, how many memory access I will require? Okay, I told you the hint, like indirectly I have told you the hint. How many instruction cycle will I require? Tell me in the comments below. Okay, tell me in the comments below how many instruction cycle will be, what I'm telling, not instruction cycle, how many memory access will I be requiring if I include the whole cycle? Okay, tell me in the comments below. Okay, so this question is again pretty good question, like many concepts of memory access gets clear from this question. Okay, let's read this next question. Consider a RISC machine where each instruction is 4 bytes long. So like one instruction is 1 word. So 1 word is equals to 4 bytes. Conditional and unconditional branch instructions use PC relative addressing mode. So they use PC relative addressing mode. For branching, we use PC relative addressing mode with offset specified in bytes to the target location of the branch instruction. Further offset is always with respect to address of the next instruction in the program sequence. That we already know. PC relative based addressing mode, the offset is always with respect to the next instruction that needs to be fetched. Okay. Consider the following sequence. I is add this, I plus 1 is this instruction, I plus 2 is this compare, I plus 3 is branch. So this is I think this is the branch instruction. They haven't told you, but this is the branch instruction, R1 offset. Don't worry. In nowadays, they will tell you what each instruction means. Okay, they will tell you. Don't worry about this. So it is telling me branch to R1 with offset. Okay. If the target of the branch instruction is I, the decimal value of offset should be. So what should be the decimal value of offset? How do I find out? How do I find out this? Okay. So basically, I need to branch to this value, right? I need to branch to this. Currently, I am executing this instruction. Currently, I am executing this instruction and I need to branch to this value. If I need to branch to this value, what is the PC value here? If I'm executing this instruction, I plus 3 instruction, what is the PC value? PC value will be simply I plus 4, because I am currently executing this instruction. This instruction has already been fetched in the instruction register. So PC value has already been incremented. Fetch cycle has already been occurred. Currently I am in the execution phase. I have already executed I am executing the instruction. So I have already fetched the instruction. So PC has already been incremented. So it is pointing to the next sequential instruction, that is I plus 4. Now they have told me that each instruction is exactly 4 bytes long. Each instruction is 4 bytes long. So if I start from I, then what will be the, let's take an example. If I start from 100, what will be the address location of the fourth, I plus 4? What will be the address location of I plus 4? So if I start from 100, the first instruction will take 100 to 103, as it is 4 bytes long. The next instruction will take 103 to 107. Okay, as it is 4 bytes long. Again, the next instruction, so not 103, sorry, it is 104. The next instruction will take from 108 to 111. The next instruction will take from 112 to 115. Okay, this instruction will take from 112 to 115. So I have 4 instructions, and from 115, so this is where my PC is pointing, from 116. So my PC will point to this. Now there is a simpler way of getting to this value as well. What you can do is, base is 100 plus you multiply this, I have 4 instructions, so 4 times the length of each instruction, that is in bytes, that is 4. So you will get to 116. So either way you can get to this value. You can take a smaller example and understand this better. Okay, so I got to my 116 value. So my current PC value is 116. So I know if I'm using PC based relative mode of addressing, so my PC plus my offset should be equals to my target address. What is the target address? It is equals to 100. Okay, just I have taken an assumption that I am starting from 100. You can take anything. Okay, you can take unknown as well. I will get simply cancelled. So now my offset actually is independent of base location of the instruction, right? So that's why it is known as relocatable code. So offset equals to what it will be? It will be minus 16. Okay, offset will be minus 16. So minus 16 will be answer. Minus 16 will be answer. What is PC? PC is 116. 100 minus 116 is minus 16. So why did I specify previously that it my PC is relocatable? Why did I specify? Because actually your PC contains what value? I have just assumed I to be 100, but I can be anything. So it will be I. Current PC will be I plus 16, correct? And what it should be equals to? So not this. Sorry. What should be my target address? Target address should be I, and it is equals to PC plus offset. So offset is equals to I plus, not plus, sorry, I minus I plus 16. So regardless of the initial value of I, it will be it will be anything. Okay, it does not depend on the location of the instruction. So here offset is independent of location of base address. Location of base address, that is location of instruction. So that is the advantage. That's why I have mentioned in starting that PC based relative mode and base index relative mode are both is relocatable. Why? Because it is independent. The offset is independent. I am not hard coding the base address file, right? It is independent. Okay, so it can vary. If the location of this instruction I changes, so will the I plus 16, but my offset will be same, right? If I want to branch to this particular instruction, I will branch to this instruction. It doesn't matter what is the address location of this particular instruction. If I want to branch to this previous instruction, right, it doesn't matter where it is stored, I will still branch independent of where it is stored. Okay, that's why it is relocatable code. That's why we say it relocatable code. I hope you understood the concept now very well, okay, with this example. So let's do the next questions. Okay, so this is the last question. So let's do it. So the instruction of a CPU is opcode mode reg r. Okay, so this is the instruction, this is the mode, and this is the register basically, and this is opcode, and this is one memory word. The mode and reg r together specify the operand. So these two specify the operand, whether it will be indirect mode, a direct mode, all those things. Reg r specifies a CPU register, and a mode of mode specifies an addressing mode. In particular, mode 2 specifies the register r, reg r contains the address of the operand. So it contains the address of the operand. Basically, reg r contains the effective address. Address of the operand, and after fetching the operand, the contents of reg r are incremented by 1. So this is just a mode that they have defined. After we fetch the operand, what we do? We increment reg r plus 1. Okay, reg r plus 1. An instruction at memory location 2000 specified mode 2, and the reg r refers to the program counter. So what is the address of the operand? So what is the thing? An instruction at memory location 2000. So at memory location 2000, okay, at memory location 2000, I have an instruction which states that mode will be 2. Okay, and reg r refers to the program counter. So reg r is pointing to PC. Okay, reg r is actually equals to PC. Basically here itself they have told, like in this instruction itself, I think they have told me that the instruction has specified mode should be equals to 2 and reg r should be equals to PC. So they are telling me what is the address of the operand? What will be the address of the operand? Like here, this is the operand, right? No, this is not the operand. This is telling about the operand. This is the effective address of operand, whatever the reg r contains. So reg r is equals to PC, and I know it is equals to effective address of the operand, which is the address of the operand, right? So currently, I have fetched this instruction, right? If I have fetched this instruction, then only I will be able to know that yes, the mode is 2 and reg r is PC. Then only I will be able to do it. So if I have fetched the instruction, then what will be the value of PC? So currently I have fetched. I was supposed to fetch this instruction. I have fetched. So this instruction has been fetched. Then only I am able to understand that this instruction tells me that mode, you need to make mode 2, and you need to make reg r as PC. So if I fetch this instruction, then what will my PC point to? They have not mentioned any word size or something. I'll assume it to be byte addressable, and I will write here 2001. Okay, I will increment it by y. That's my only way, because they have not mentioned how many bytes each word is. So PC, current PC value is 2001, right? Because after fetching the instruction, my PC, I have instantly incremented my PC. So what will be stored in the reg r? Reg r value 2001 will be stored. And what is this value? This is actually the address of the operand. This is the address of the operand. Correct? So obviously from here I can say that address of the operand, part A of the answer will be 2001. So address of the operand 2001. Okay, this is the part A. Let's read the part B. Assuming that it is a non-jump instruction, what are the contents of the PC after the execution of the instruction? After we execute the instruction, what are the contents of PC? So the contents of PC they are asking. So after we execute the instruction, basically what we'll do is the PC value will be only 2001 only, right? After execution of this instruction, after we execute this instruction, okay, after we execute this instruction, reg r value is added to 1. Okay, after the execution of instruction, reg r value will become 2002 actually. Reg r value after execution, reg r value will become 2002. because after each instruction end, right, it becomes 2002, but your PC value will be just 2001, right? Because I have just executed this instruction, I need to still fetch this instruction. After fetching only, the PC value will increment. Okay, after fetching only, the PC value will increment. PC value won't change after execution. Okay, after fetch of the instruction only, PC value will change. So that is the most important point that you need to understand. Assuming this, so what is the address of the operand? Just let me read this question once again. Contains the address of the operand. After fetching the operand, the contents of rejar is incremented by 1. So this is before fetching, right? So yeah, so here the value of the, what happens, the address of the operand is 2001, and as soon as I fetch the operand in the execution phase, rejar, so this happens, rejar becomes +1. This happens after operand fetch. So there was one particular stage, right, in execution cycle, which was operand fetch, if you remember, which was operand fetch. So after that operand fetch, what we do, we increment the rejar value. So if they are asking me the rejar value after the execution cycle of the instruction, it will be 2002. If they are asking me the PC value after the execution of instruction, it will be 2001. And if they are asking, like they have asked, what is the address of the operand, okay, it will be 2001. So answer will be 2001 and 2001. Okay, you have to be careful. If in place of PC they would have asked rejar, it would have been 2002. Okay, so I hope you enjoyed these type of questions, and that's basically it for this portion of your COA, computer organization and architecture. I have tried to complete most things on computer architecture, and like if you give this video enough support and likes and views, then obviously I will try to bring the pipeline instructions, which is very very important for gate and obviously placements, most important topic. So I will bring that next. It all depends on you, how much you guys support the video. So yeah, I hope you enjoyed the marathon. If you did, please go in the comments below, like the video, and please go in the comments below and like write in the comments that how much you enjoyed the concepts and the video. Like I have tried to bring this in a very short form type, right? Because like in 11 hours, almost 11 hours, we have covered a lot of things, and it's not like I have skipped anything. I have not, trust me, I have not skipped anything. I've tried to interlink everything so that you are getting multiple concepts at once without like giving you too much of information at once, right? I've tried to explain everything lucidly. Sometimes it may happen that you're not able to grab that concept because many things are interrelated here. So what happens is later on once you proceed on the subject, right, you know a bit of things, then you come back to the previous topic, you understand it better. So yeah, I hope you enjoyed this whole lecture, whole marathon, and I hope to see you in the next lecture. Until then, happy learning.